At the moment, let us continue this session. Maybe if there are less people here, then whosoever is here can do the stagnant practice. If only one person is there, we'll set up the Google link so that others. By the way, did you receive the email for the nicer?
No.
Invitation that you were reminding me. See, this is what I sent the email, but from your content matter, no placement percent दिखा रहा है on my desktop because I also was I'm supposed to get the email, na? Because even I also did not get the email. I sent it yesterday.
It is शुरू हुआ.
Oh, I thought it's a nice idea.
It's so interesting.
Oh, I see. Okay, then cut paste and send it again. Okay, sure. No, Ravi বলছিল যদি এখানে কম লোক থাকে we should keep a Google Meet live in case এখন তিনজন আছে so I think it's perhaps fine.
So now I think it's already 9:24. Let me call Priya. That this is there.
The speakers are there.
Speakers Krisano I can see, but Bahadur.
Let's just see.
Yeah, regarding this, did you send this institute?
हाँ वही तो अरे
You have not added any. Why are the institute faculty there?
this is not তোমার নেই
না আমি মানে
না পাইনি that's what I was talking to.
Institute পাইনি তো
হ্যাঁ but
কেউ পাইনি.
the mail is sent from Young Currents Matter so Ravi
কিন্তু তোমার সেখানে অ্যাড্রেস নেই.
No, but how will you get this is your mailbox? সেটা তো আমি Young Currents Matter পাঠাই
না school.niger.ac এর আলাদা করে পুট করেছো. তুমি তো ফ্যাকাল্টি ডট
No, this is a separate and access separate. Internet access. This is for everyone. That everybody, this is not for nice. পাঠানো হয়েছে but the point সেটাই আমি বলছিল যে ওই Young Currents Matter is not added to the physics. So ওখান থেকে physics এর মেল পাঠাই.
Hey, somebody is controlling this one. Like, yeah, Arijit Shah are opening. Okay, now I make it closed.
Who are the speakers? Arijit
Bahadur Singh.
Bahadur Singh, Aftab Alam, Arijit Shah and Krishanu Rajadri.
क्या हो रहा है?
क्या हुआ?
No, if I do it and then okay.
Hello everyone. Hi, Bahadur here from TS.
Hi.
Yeah, so I am making this co-host the Arijit Shah made it.
So Bahadur will make all the 4 speakers and the session chair as co-hosts simultaneously, so that one can do the talk immediately after the other.
So who is the other one? Aftab is not there so far. Let's see.
Who else is there? Bahadur is there. Arijit is there. Krishnan Rajadri is here.
Yeah, I made.
Okay, and then Priya and this Aftab.
Aftab is not here.
Yeah, good morning, guys.
Good morning. Arijit.
Oh, Arijit. Good morning.
Yeah, good morning, everyone. Who's there?
Good morning.
Oh, Priya, are you in? What is happening? Why my mobile is?
Priya ki phone call hai?
He is joining.
After I don't have his contact number.
I don't have it.
Maybe it will join. After I will go there.
Live is there. Yeah, but it's cool. Maybe it was a wrong thing. Let's do it. Yes. This is the link.
ठीक है आई थिंक कुछ आई थिंक कुछ বলছি এটাকে মিউট করে দাও মিউট করে
This one, yeah.
and the meeting is being recorded, right?
No, it's not recorded.
Record, start record. That triangle. Yeah.
Okay. Now this is on.
So anyway, let's ask. Hi Bahadur, this is Anamitra. Maybe you can keep your screen shared.
All right. Okay. Sure. Okay.
It is cyclical. So we are waiting for the session chair. Once she comes in, we'll start.
Sure. Sure. No problem.
After
No.
Okay. I hope my screen is visual and I am audible.
Yeah, your screen is visible. Maybe you can move the cursor to see if it's visible to us if you want to. Yeah, that is fine.
Okay.
It's working.
All right.
No, let's start.
It's okay. I think this is working. Okay.
Priya is there. Okay, sir. More. Yes.
Hello, Priya. Hi. You can hear me?
Yeah, Priya's voice is not audible.
Yeah.
Can you hear me now?
Yeah, we can hear you. Hi, Priya. So thank you for sharing this session. I think only one speaker in your session, Aftab, hasn't yet joined. So others we have made into co-hosts along with you. So they should be able to just share their screen one after the other. So just let me just thank everybody for sort of participating in this meeting with enthusiasm and with all this corona etc. happening in the background. So with that, let's start. The first session will have 4 talks and will be chaired by Professor Priya Mahadevan. So Priya, the floor is yours.
Yeah, thanks. Thanks. At the outset, I'd like to thank the organizers for putting together a nice lineup of young investigators across the country for this meeting. So without much ado, let's get started. The first speaker is Bahadur Singh from TIFR, who will be telling us about topology, symmetry, and magnetism and quantum materials. So Bahadur, I'll just give you a warning at 18 minutes,
Okay.
so that I think you have 20 minutes of talk time and 5 minutes is for discussion. Thanks.
All right, thank you. Okay, thank you, Professor Mahadevan, for introduction. Let me thank the organizer for putting this nice event together and having us here. I am Bahadur from TFR Mumbai. All my group is working on predicting topological materials as well as the silent characteristics of topological states. All work, or you can find us on the TFR websites. So today I'm going to talk about topology, symmetry, and magnetism in quantum material. We know that any scientific breakthrough is enabled only when we have access to high quality materials. So in this regard, I will walk you through our various prediction and their experimental realization. I'll try to be brief, but if you have any questions, please feel free to stop me in between. Before I start, I have worked across the globe with various experimental as well as theoretical groups. In this talk, I'm going to present work basically done in collaboration with Coaching Chang at NTU Singapore, Amit Agarwal's group at IIT Kanpur. Experiments are mostly done by Jahid Hassan's group at Princeton and Madhav Newpen at UCF. Also, the transport experiments is performed by Faisal Tafti's group. Okay. With that introduction, let me give the outline of my talk. I will briefly introduce the basics of topological band theory, and I will walk through our methods of choice like density functional theories or various other approaches which we are developing over the years. Then in the second part, I will talk about the role of bulk crystalline symmetry in defining states. So I will talk specifically for two states, mirrored topological crystalline as well as rotational topological crystalline insulators. I will also walk you through how symmetries over the surface shape the surface state energy dispersion. So we have very exotic kind of states such as saddle lights with one-Harvey singularities. And then in the third part, I will go for the topological magnets, where I'll see how the interplay between crystal symmetry topology and magnetism drive unique electromagnetic responses, as well as, if time permits, I will show our first theoretical prediction and experimental realization of ferromagnetic topological insulator. Finally, I will summarize my talk. Okay. Topology, although this is just a preliminary slides to introduce, it's a branch of mathematics basically that used to study the geometrical properties of the objects that are invariant under smooth deformation, including stretching, bending, but not tearing and gluing. Here, smooth deformation is an important because that what we bring in physics correspondence is the adiabatic continuity, where we shape the systems slowly. So just if we look over these two objects, one is sphere, other is white glass, they are topologically invariant in the sense one can transform this sphere to wine glass without introducing hole or without cutting it. But this wine glass is not equivalent to a donut because there is no hole into it. Okay? So however, this donut is again equivalent to coffee mug. Now, then how we describe object on the terms of topological invariance. So how do we define the topological invariance? So that is given by a very famous theorem like Gauss-Bonnet theorem that gives us a language of converting this geometrical curvature into the invariance. So it's given by just Gauss curvature is equal to this Euler characteristics and 2 minus g basically. This g is the number of holes in the object that define. Similarly, after the realization of integer quantum Hall effects, there were various theories proposed up to explain it. Then there's famous theory was TKKN that shows like similar to this Gauss curvature, we have Wavy curvature, and then this total Wavy flux over a Brillouin zone for occupied band is basically either gives us this number, which is called Chern number. It is 0 for normal insulator or non-zero for integer quantum Hall effects. So in this slide, we just show that the geometrical property of block wave functions are basically essentials to define topology in condensed matter physics. With this background, although we are electronic structure guys, so let me give a brief introduce how we can see within an electronic structure a system is trivial or non-trivial. So any telltale signature for any system is non-trivial, is it should have an inverted band ordering with respect to some normal order. So here with just showing with these systems, now let us first focus on this in middle of this green and blue bands. If we ignore this band, it's moving, okay. If we ignore this this blue region and green region, then basically whole three region we cannot distinguish which is right or left. Or which is trivial or non-trivial. Therefore, the information of this coloring is important. So what color represent here is basically the wave function, and it's the way with gamma 6 or gamma 6 plus or 6 negative represents the symmetry properties, how this wave function transform under symmetries. So these are irreducible representations. So when we start moving these two bands with some external perturbation, they close at critical point and reopen inverted, where we can see this green color goes to conduction band, whereas blue comes to valence. So this is not equivalent to what we have in left side. And if we look over this surface, it has a very fascinating surface state. We cannot be destroyed as long as we we retain the bulk band inversion. So in going through this phase transition, at the critical point, if we combine with various other symmetries such as time reversal, inversion or rotational, then we can stabilize this critical point over a whole phase space, and we realize the topological semimetals, which we know Bragg semimetal, which having time reversal as well as inversion symmetry. So each point is fourfold degenerate. If we break the time reversal or inversion, this can split into the while nodes where each point has a well-defined chirality, and then we can have a very nice Fermi arc states. And if in a system has a planar symmetry such as mirror symmetries, then these touching points can close around a loop in K space, and then we have a nodal line semimetals. Okay. So with this one, let's see how the journey of these topological materials goes through when we bring the crystallography into it. So after the first realization of bismuth selenide, or we can call the Z2 topological insulator in time reversal systems, people start looking over how symmetries played a role. And in condensed matter, we all work with symmetries extensively. So we have 32 point groups, and when it combines with protein Bragg lattice, we end up with 230 space groups, as well as 17 wallpaper groups in 2 dimension. Now in these papers, it has shown like we bring about 478 symmetry indicators. So we have this amount of topological phases in insulators only. Okay. Now we have a magnetic space group 1651 and 528 magnetic wallpaper groups. Similarly, we have metal, semi-metal, chiral crystals. So if we see, this is a whole new area which is named with on the condensed matter physics and material science that can shape various cross connection between various fields. However, one of the major problem I would say here is, although we realize so many topological states, but it's very difficult to realize them in experiments because there are no ideal single phase materials. So how do we really get to know to access all these states? So for that, we have to get into basics of what topology is about. It shows about something discrete properties, which is enough. So topological field works on a phase which where less is more. So we start asking this question, how to get more from less. So in order to do that, we bring it under the umbrella of quantum materials, which brings different branches under same umbrella. So if this is the just wave of the emergence of quantum material is started around 1980s by two discoveries, one quantum Hall physics, which use quantum topology or wave function topology, or in parallel we have high TC superconductivity, where the strong electron correlations plays a role. So over the years, the field developed, and we are now sitting mostly on this reason where we are finding out how pronounced, how to determine the states and what are their responses and how they can be utilized in the future applications. So in this, what we try to do in our work is basically, I start asking out how this topology couples with various degree of freedom, how it couples with spin charge orbital lattice to give us the new responses. So basically, we are trying to awaken two different kind of quantum interaction in a material. Before I start further, let me give you an overview what we do and how we do. We mostly utilize the first principle theories, existing first principle theories. However, we all know like those are computational expensive, although they are numerically more accurate, but they are limited property calculator in the sense like we have some codes specified, we can use that. However, in order to predict something robust and compare with experiment, these are not enough. So we have to find out some smart way to use it. So what we are trying to do is we are generating the material specific tide winding models of K.P models, and then adding our interactions or calculating vary curvatures, as well as calculating the anomalous Hall conductivities and all those kind of things in this approach. So over the years, this has been turns out very efficient, the approach to predict as well as the compare with the experiments in a robust way. Okay. With looking over, let's first see how topology couples with the crystal symmetry. So we know that crystal symmetry is defining properties for our periodic solids. The basic symmetry, we always talk about mirror symmetry. So mirror protected TCI. So basically in these systems, band inversion happens at the mirror planes. So this is the first topological crystalline insulator in tin telluride class of materials. We find it has a, so here we have this highlights the mirror plane. and band inversion happen right across on these L1 and L2 points, which are mirror invariant. So what happens is in these systems, the mirror band inversion happens on even number of points, and if we calculate the Z2 invariance, that comes out to be trivial. So then we start looking over another numbers, and it finds that we can define the Chern number. We can define a mirror Chern number in similar the sense of integer quantum Hall state, and that turns out to be 2, and that gives us the even number of Dirac cones. So these are the simulated surface spectrum, which shows clear Dirac dispersion along gamma 2x, which is just projection of mirror plane over surface. And then these are the corresponding RPS map, which nicely correlate with the form surface. Now recently what we find is because since this crystal symmetry is the defining property here, and with temperature, this crystal, there are fluctuations, then we can basically tune the surface state of these crystalline insulators. And our recent work just appeared in few days back, where we discussed the anomalies of temperature evolution of Dirac states in this one. Okay. So now we have additional other symmetry is rotational symmetry, where band inversion happened at rotational axis. So they bring about the rotational anomaly, and we have actually n number of Dirac cone on them. However, when we start looking over, we know like all crystallography, we have many rotation symmetry. So how to isolate these systems with respect to our existing materials? So we start looking over material with very low crystalline symmetries. And in this, we end up with looking for the monoclinic crystals having C2H point groups. So if we just look over its character table, it has unity obviously, and then we have C2 symmetry inversion and then mirror plane. And if we look over, these are just two cartoon pictures. This shows if suppose we have a band inversion happening on a mirror plane, then what happens to surface state? They either exist on 001 plane or 100 plane. Whereas if rotation, we have a rotational TCI, that should happen, surface state should reside on 010. So basically, although we have C2 and mirror, but they are not interfering with each other because each surface has a different surface states. So then we start looking for the experimental realizable materials, and we find this tantalum diarsenide class of system, which has C2 rotation and mirror eigenvalue. And we find, although it's simple ionic model suggests it's an insulator, but due to large bandwidth of D bands, say there is it's a semi-metal character. But irrespective, this system shows a local band gap at each K point. So we have invariants like 0, 1, 1, 1. And if we look for its symmetry indicators, then we will find out like we have here the rotational invariant 1. Okay. So if we look for its surface dispersion, this is along high symmetry direction. Since system is a weak TI, it has a Dirac cone here as well at gamma. But if we look along the L2 gamma direction in this one, we find there are two sets of Dirac cone, which is existing just near to this gamma L direction, which has the type 2 dispersion, which is basically verified by changing the energy dispersion across the Dirac point. So this is basically the first example of type 2 Dirac fermion in any topological crystalline insulator. More recently, more recently we find another dual topological class in platinum germanium class of systems, which also shows this very nice topological crystalline insulator state. Now another example here, I would now, so far what we discussed is how bulk symmetries are defining the states. Bulk symmetries are defining the state. Now we start this question like how interplay of surface symmetry and band topology leads us to interesting properties. So basically we know like although bulk define the topological state, but the local energy dispersion of any topological surface state that rely on the surface state symmetries. So in order to exploit that, we start looking like how local symmetries over surface will shape the surface state. And we find that depending on the symmetries over surface, if it has a symmetries C2 or less than C2, then system can have all kind of fancy surface state like saddle-like Van-Howe singularities. And I'll just discuss an example of this one. To realize that, we again look for the low symmetry systems, we go with the orthorhombic. which have C2 rotation symmetry. This is a bulk band structure without spin orbit coupling. We can clearly see along gamma 2x, these are crossing. And if we explore it over brilliant zone, it forms a nice loop on my or kz is equal to 0 plane. With spin orbit coupling, since system also has inversion, they gap out and system transition to topological insulator. But interestingly, what we find is if we see this is the bulk projection of nodal line over surface, we find like a fancy surface state which has electron-like dispersion along x to gamma direction like kx, and it has a hole-like dispersion along this one. So this is something which we call saddle-like state, and we have associated one-away singularities. And if our Fermi level is tuned to lie along this one-away singularity, then system can show very fascinating correlated states such as antiferromagnetic, ferromagnet, or even superconductivity. So idea of earlier realizing it, how to realize a topological superconductor. So we look for the saddle-like surface states. Okay, and what we find is we over giving the low energy Hamiltonian, we find this kinetic energy term if we have this eta which is greater than 0, that defines up the okay, sorry, I don't know what's happening. Okay, that defines the saddle-like energy dispersion. So basically, necessary condition for any topological surface state to have this kind of dispersion is our rotation symmetry should be less than 3. And we have various families of saddle-like energy dispersion now. We also determine the first TCI with saddle-like energy dispersion, which is basically in this platinum Hg selenium class of materials, where we find very two sets of nodal structure, have a very rich nodal structure, but if we go over surface, it has a Dirac cone dispersion below the Fermi level. So if one can just tune by gating or something this Fermi level, this can be a rich candidate for realizing various correlated phases. And interestingly, this particular phase, saddle-like surface state in this material has been confirmed by experiments recently. Okay. Almost time.
You have 2 more minutes. You have 2 more minutes of talk time, and then.
Okay, 2 more minutes. Okay, thank you. Okay, it will long, but let me wait. Okay, so basically now again, so we know like with the initial, like moving about how the magnetism brings into picture. We know like predicting any correlated state within density functional theory kind of framework is not that easy because we are basically dealing with single particle picture. So how do we find out the robust state in a material, robust state within our existing first principle theories? So in order to that, when we know like various symmetries, magnetic ordering shape the symmetries of a material. So we need something which is very robust, but at the same time we have a tunable. So what we find is if we have a Dirac semimetal and if we introduce magnetism, it's split into a Weil semimetal. Okay. So this is the first route which is extensively looked on. Or we look for, let's see if we have a Weil semimetal in non-magnetic system, and if we shape its magnetic or Weil fermion by applying some external magnetism, or if we can shape out these, then this will be very robust in the sense like the topological state or Weil semimetal is basically shaped by the non-magnetic symmetries, whereas magnetism tune these nodes. So this and then we propose like this rare earth magnet of the cerium aluminum germanium class having a ferromagnetism, inherent ferromagnetism, and they realize this particular state. So just quickly going over since time is short. So we start with the discovery of this lanthanum aluminum germanium, which we proposed as the first type 2 Weil fermion semimetal, where we basically realized the Weil fermion in experiments. So this is without spin orbit coupling. There this crossing happens along various mirror planes. It has also coexisting Weil nodes, spinless Weil nodes. And if we include spin orbit coupling, it gap out along high symmetry direction, but it gives us 40 Weil nodes along the mirror plane, along the brilliant zone. Okay, and if we look over its dispersion, we have various Weil nodes. We have a W2, which have type 2 energy dispersion and lies right across the Fermi level. This is corresponding RPS and our first principle maps. We can see they have a corresponding nice overlap along KZ direction. And if we see over this particular KX and KY map, and just try to zoom it at one point and change the winding energy, and we note any type 2 wire nodes, it's an intersection point between an electron and hole pocket. So if we change the winding energy, one pocket should go large and other pocket should contract. And that exactly happens at winding energy. This is electron pocket and this is hole pocket. And at this one, this shrink and the other pocket goes large. Okay. So definitely this is a touching point between electron and hole pocket. And if we go across, start looking across its dispersion, we can see along X direction, along Y direction, this is a tilting of the Dirac cone. And along KZ and KX, it has a linear dispersion. And these are our simulated, calculated energy dispersion, and these are the RPS map, and they are matching quite nicely. So with comparing with both theory and experiment, we shows this is the first Dirac's wire semi-metal where we have the tilted energy dispersions or the type 2 wire nodes. Similarly, recently what we find is if we look over another materials, cerium, aluminum, silicon, it is also wire semi-metal having a low number of wire nodes. It has 24 wire nodes similar to the first class of semi-metals. Here and with magnetism shapes the distance between the wire nodes. And if we look over the experimental data, which we performed at the group at Boston College, this is our simulated anomalous Hall conductivity, which shows a signal around out for in-plane magnetism, but out of plane magnetism, it has zero anomalous Hall conductivity. But experiment, it seems something very bizarre. This is along, if magnetic field is applied along in plane, so it shows just normal kind of behavior. Whereas for out of plane, while theory predicts it's zero, it shows a very robust loop shaped kind Hall effect. Okay, so this is purely, we find like by tuning various samples, is find like this signal only happens in the samples where wire nodes lies close to the Fermi level. Although the complete understanding of this phase is still undergo, but our initial analysis shows this is coming out to be due to proximity of Fermi arcs near the wire nodes that giving rise to this anomalous loop shape Hall effect. Okay. Then this is a whole family picture where we can have all kind of exotic wild fermion in this materials. Similar now, if we go for, we can also shape this state topological magnets by employing the various mirror plane symmetries in the system. And in this paper, we basically try to show how nodal line lying on different mirror planes can combine to give us very rich links called Hopf link or outer chain, inner chain state with having very extensive surface states that elongate through the full brilliant zone. Okay, since I have a short of time, I'll just quickly go through it. So we look for this wide
You've run out of your
okay.
You've run out of your time even for the questions. So maybe you should just wind up with the conclusion, or
yeah, sure. So basically in this, and then we try to compare theory versus experiments, just using that using the mirror plane as the symmetry argument, and then just to try to design the state. We find this cobalt, manganese, gallium is basically a wild node, line node semi-metal, and where we try to show the bulk surface and transport correspondence, and which is actually one of the important breakthrough with can give us to a robust prediction of topological magnets within first principle. This is just another candidate which we show this manganese 1813 system that shows a ferromagnetic topological insulator. It has gap in the bulk, and if we see the surface state is also a gap due to local magnetism, and this can be a candidate for axion insulating state. Okay, with that, let me thank you. I'm sorry for a long talk, but yeah. So basically what we try to show is using first principle framework combined and topological band theory, I try to convey how crystal symmetry and magnetism coupled to gives us new physics and phenomena. I gives an example of topological crystalline insulator and how local surface symmetry shape the states. And briefly, I talk about topological magnets in this material. Thank you. I will happy to take one question.
Yeah, thank you, Bahadur, for a very nice talk. So if anyone has any questions, may I request them to raise their hand or okay, there's Sorin who has a question. Okay, Sorin, go ahead, unmute and ask. Yeah.
Okay, so yeah, this question is about, I think you made a comment about this saddle-like topological surface states. They are good for hosting superconductivity. Why did you say that? I mean, can you clarify?
Okay, let me see, because yeah, I go so fast over those. So okay, so basically, if we look for any high TC superconductors, for example, in cuprates, much of the earlier theories were thought to be coming from the Born-Haber singularities around the top. So basically, here what we are talking about, if we have a surface state and Born-Haber singularity, it can, in principle, host these states because we have very high density of state at these saddle points. This can also lead to various other correlated phenomena. So only because of the saddle point Born-Haber singularity we are saying. And the second point is, moreover, these are topological surface states. So there is definitely, these are spin split, so they can have odd pairing. And in basically in this paper, we have tried to show like they have type 2 Born-Haber singularities that can give us to this odd pairing. And then they are the candidate for superconductivity. Yeah.
Okay. Thank you.
Thank you.
Yeah, I had okay, there's one more question. Go ahead and.
Bahadur, nice talk. So you, at some point you mentioned in the early part about the anomalous signatures of thermal effects in on Dirac states. It also relates to the question Shorin was asking that if you are also proposing Banach singularities, that's fine, but I mean, if you do realize a high TC superconductor, one has to worry about temperature effects as well. So can you briefly comment on this issue of what is the state of affairs there?
Okay, that's a nice question, but probably I don't know exact answer. So basically, if I understand your question, you are talking about how the thermal effects disturb the Born-Haber singularity and the superconductivity. Is it?
Yeah.
So basically, in this system, this turns out like the thermal effects do playing a role in tin telluride class of material, whereas here we are not very clear how those happens. And moreover, if we here, as I mentioned, we have to tune this Born-Haber singularity to Fermi level to look for those states. So the exact answer and comment I will not know exact at this point. So.
That's sure. Thanks.
Definitely, it's true.
Yeah.
Like that, if we have effects on thermals, have effects on the superconductivity or all these correlated states. Definitely.
Okay. Sure. Thank you.
Yeah. So I had a related question to that. So how many? I mean, so basically, you're suggesting that the surface state is driving an instability, but right? I mean, or some sort of instability. It could be superconductivity or something else. So how many systems do we know where the surface? I mean, if SR2RUO4 or that class of superconductors, people do talk about the Van Hove singularity being close by. But how many systems do we know actually where the surface state is driving the instability?
Okay, very nice question. Of course, if we go for this one, at present, to my best knowledge, there is no clear system which shows like surface state is driving that. But I mean, over 2-3, I mean, not that, it's just 2-3 months back, there is a system where bismuth, tellurium, selenium-2, they do shows like the charge density wave is driven by the surface state nesting. So to my knowledge, I just know one system. So that is the whole area here.
The surface state nesting is driving the bulk to go charge ordering. Is that what you're trying to say?
No, it's over surface. Because bulk anyway is the insulator, so I don't know if that can drive, but over the surface, since it's metal over the surface, so its metallic states is deriving the CD charge density wave over surface.
Okay.
Yeah, and actually that's
the
whole, we were trying to push the whole area, like how do we realize this correlated state using the surface states and topological.
Sure. Okay. Okay, thanks once again for a very nice talk.
Thank you.
And with that, yeah, we'll go on to the next talk. We're running a little late. So the next speaker is Aftab Balam, who will be talking on broken symmetry driven topological phase transition in strontium silver arsenide. Yeah. So Aftab, can you share your screen?
Yeah.
Yeah. So Aftab, I'll warn you at 18 minutes that you have 2 minutes of talk time,
Sure,
so that
sure.
you can wind up in about things, so that leaving ample time for questions.
Please, yeah, thank you. Is my screen visible, Priya?
Yeah, it's visible.
Okay. Yeah, thanks, Priya. And most importantly, I'd like to thank the organizers, Anumitra, Ashish, Kush, and Ravi, for arranging this nice platform for quantum condensed matter theory, facilitating the opportunity to bring in people from several expertise all over the country. Okay, so my talk today is going to be focused on a few interesting, one interesting quantum material, which we studied recently. These theoretically predicted materials are now being synthesized experimentally by our collaborators. So just to give you a perspective about what I'm going to talk about, in general, it is well known that materials are conventionally divided into three types: metals, insulators, semiconductors. However, recently, through the lens of topology, materials are found to be reclassified as either topologically trivial or non-trivial. Now, why non-trivial materials are important? Because these semi-metals and metals exhibit novel low-energy fermionic excitations, of which the most extensively studied are the Dirac and Weil fermions, some of which are being introduced by Bahadur in the previous talk. And depending on the inherent symmetry of a particular compound, the crossing points can be several fold. The Dirac and the Weil fermions are four-fold and two-fold degenerate, arises from four-fold and two-fold degenerate crossing points. So new materials going beyond Weil and Dirac semimetals with higher band degeneracies have been proposed, and these materials exhibit unusual transport properties, including high carrier mobility, large magnetoresistance, anomalous Hall effect, etc. Although these different fermionic behavior are realized separately in specific crystalline materials with different lattice symmetries, finding their coexistence and especially the transition between them in a single material is not very common. And this is one of the purpose of today's talk, where I will show how symmetry plays a crucial role in achieving such topological phase transitions in a single material, which is strontium silver arsenide. This work is done by two PhD students, Chanchal Burman and Chiranjit, and in collaboration with Biswarup from IIT Indore. So as discussed, topological quantum materials bring in new possibilities, not only from fundamental physics point of view, but also in other applications such as spintronics, quantum computing, novel magnetism, and superconductivity. Interestingly, however, the lattice symmetry plays a crucial role in dictating these properties. And one of the fundamental questions is what exactly defines the states of a topological material? Is it a Dirac semimetal, Weil semimetal, or something else? The answer lies in its point group symmetry. The central concept is that two bands, which are composed of atomic orbitals, will cross each other at any k point in the Brillouin zone. The degeneracy of that crossing point will be protected by the side symmetry group of that point, and the band hybridization will be restricted by the group orthogonality relations. So these are some schematics of the band concept of their topological materials. The extreme left one is a band diagram for a simple regular insulator. The middle one is where you have a closing of the gap. And the right one is a topological insulator where you have something called a band inversion. The surface states usually are conducting in these materials, which are shown in the right diagram. Now, apart from these normal metals, Dirac semi-metal, and Weil semi-metal, there are also recently introduced or recently predicted triple point semi-metals. So, Dirac semi-metal, for example, arises because of a four-fold, band crossing, which is shown here. You can see this crossing is a four-fold, in nature. The Weil semi-metal are a pair of crossing points which are doubly degenerate H. However, triple point semi-metals are triply degenerate, which arises because of the band crossing of a doubly degenerate and a singly degenerate bands. So, as I mentioned, the Dirac fermions arises because of the four-fold degeneracy, Weil fermions because of the two-fold degeneracy, and triple point because of three-fold degeneracy. And there are certain symmetries which usually are respected. For example, in Dirac semi-metal, it is protected by inversion, rotation, and time inversion symmetry. For Weil fermion, they are respected by broken inversion or time inversion symmetry. And triple point semi-metals, more interestingly, arise from a non-centrosymmetric system with a specific type of symmetry. Now, in quantum field theory, we do have the corresponding quasi-particle of corresponding to DSM and WSM. However, for triple point semi-metals, there is none. So this is one of the new, introduced topological non-trivial fermions in the condensed matter systems. So there has been several studies on each of these types of quantum materials, Dirac, triple point, and Weil. But they are all found in different materials with different symmetries. What I am going to show is that how can we tune symmetries so that we can find all these three phases in a single compound. So SRAGS is an interesting system which has a hexagonal space group P63/MMC. It has a D6H point group symmetry with a C6V symmetry along gamma 2A. It respects six-fold rotation, six mirror plane, and center of inversion. So the diagram below is the corresponding Brillouin zone and the 100 surface Brillouin zone. This particular compound has already been synthesized experimentally a long time back. So there is no question of formation of these. However, the topological aspect of this compound has never been explored. As far as the symmetry goes, if we look at this particular three-dimensional structure from the top, one can actually view this compound as a stacked layer of graphenes, where the strontium 2+ cation is stacked between silver 1+ and arsenic 3- honeycomb network, as you can see here. It can also be seen in this form, where there are beautiful arrangement of strontium, silver, and arsenide. And if you really analyze this structure, you can see that there are certain symmetries which holds. Just to illustrate that, the C6-fold rotation is respected in this compound, because if you take this particular structure and do a C2 rotation about x-axis by 180 degree, you actually arrive at this arrangement, and then you subsequently do a C6 rotation about z-axis by 60 degrees, you actually come back to the same as you started. So this actually is an illustration of how six-fold rotation is being preserved. So with this symmetry production, we actually simulated the band structure of this compound. This is the band structure without spin orbit coupling, and these red and the blue bands are the S and the PX, PY kind of band. We have also simulated the band structure with spin orbit coupling, and that actually splits up the band at gamma point, giving a gap here. And there is a Dirac point along gamma to A direction, as you can see. A more zoomed in view is shown in the below figure, where KD is the point where this four-fold Dirac point is occurring. And the right plot is just a band structure in the in plane, KXKY plane. And you can see that there is a Dirac point just below the Fermi level. Now, this is the band structure for a pure compound, SRAGAS, where you can see that there is a band inversion between S and PXPY bands. The band contribution near the Fermi level are mostly from arsenic S, arsenic P, and silver D. So this is the parent compound, which shows a Dirac semi-metal behavior. Now, if we think about this compound and try to see if we can induce another kind of topological non-trivial nature, one of the way is to break the symmetry. And if we can break C6V symmetry and sigma D mirror symmetry, one can, and also the inversion symmetry, one can actually think of achieving a triple point semi-metal, because that's one of the requirements where C3V symmetry needs to be preserved. This can be done by alloying this compound by copper. So we have done that by alloying at the putting copper at the silver side, which is actually the most preferable side for copper. If you do that, then you arrive at this structure, which actually preserves the C3V symmetry. And this is just a similar illustration how C6V symmetry in this case is broken when you replace one of the copper by silver. Once you do that and do the band structure calculation for this 50% copper dope system, you actually arrive at a band structure with triple points. You can see this is the zoomed in view of this same band structure, where you can see there are two triple points, TP1 and TP2, and both these nodes are actually triply fold degenerate. These are just a more zoomed in view in the KXKY plane for the same triple points, TP1 and TP2, and you can see that these bands are indeed triply degenerate. So just by alloying by 50% copper, and if it indeed respect the ordered arrangement, you can actually break certain symmetries and induce a triple point semi-metal behavior. One can also think of breaking further the symmetries by doing a 25% copper alloying, which actually breaks C3 and all mirror symmetries. It, however, restores the center of inversion and CS along gamma 2A. So this is just a ordered structure for that, and we have checked various configurations for this 25% copper alloying, and this is the energetically most stable one. And if you simulate this 25% copper alloying, you actually can get a topological insulating phase. And this is just the band structure along gamma 2A. And you can see there is a small gap. This phase is also confirmed by calculating the parity eigenvalues at time reversal invariant points with a topological index of Z2 equal to 1, which indicate that this is a topological insulating phase. We have also tried to understand these phases using model Hamiltonian by fitting this K dot P Hamiltonian to the low energy band structure and calculating these parameters. And depending on the values of different parameters, such as D, which is the inversion breaking term, B is the C3 breaking term, and BK is this, one can actually realize all these phases which I have discussed. So one can actually calculate the Dirac semi-metal band structure, topological insulating band structure, and Weyl semi-metal by breaking the time reversal symmetry by applying magnet. These are the corresponding surface states for the Dirac semi-metal phase and the corresponding topological Fermi arcs. And the the figure D and E are basically the same, the surface density of states and Fermi arcs for the triple point semi-metals. And these are the typical form of the Fermi arcs, which people have found in other triple point semi-metals also, where there is a loop kind of thing. The right figure is the the surface density of states for a topological insulating phase, where there is a small gap that you can see as as highlighted by this rectangle. Now, there was this question that although the parent compound SRAGase is indeed experimentally synthesized in the past, however, what about the alloys which we have studied and which are the new compounds? So, in order to make sure that these compounds also stabilize, we calculated the phonon dispersion for all the three, and all the three shows no imaginary frequencies. So both the end compounds, in fact, both the end compounds SRAGase and SRAGCU are already experimentally synthesized. So these alloys also are expected to be synthesized, and the experimentalists who are trying to synthesize this indeed found a stable phase. The stability is also checked by calculating the decomposition enthalpy of these compounds, which came out to be negative. So, in summary, SRAGase can serve as a host material to showcase various topological phases, such as Dirac semi-metal, triple point semi-metal, Weyl semi-metal, and topological insulators, all in the same material. And such theoretical discovery of new promising materials is interesting not only from the fundamental perspective, but also provide a unique approach for future experimental investigations. And as I said, this proposal is already made to the experimentalists to verify the present findings. I'd like to acknowledge these funding agencies, the HPC Supercomputing Facility at IIT Bombay, DST SERB, and AIMS Laboratory. Thank you.
Hi Priya, I think Aftab is done with his talk. Maybe she's having connection issues.
She may got disconnected or what?
I think there is maybe while she connects back, maybe.
Yeah, please go
Yeah,
ahead.
we can call it. Yeah, so I don't know. I mean,
So I can.
So maybe Ashish, you can start. There are 3 questions at the moment.
So I have on my questions that what are the nominal valencies of this thing? Okay, yeah, it's there. Okay.
Yeah, sorry, I got there were some network issues, so I got through now.
So it's okay.
Okay. Yeah. Sure.
So
Yeah. Who would like to? Yeah, go ahead.
So I am curious that this what are the nominal valency and that electron count on the copper state?
So in this compound, SR is in 2+ state, Ag is 1-, and arsenic is 3-. So the charge neutrality is there.
Okay, and copper, the d electrons, what are the count on that d electron? Any idea?
You mean silver?
After the doping, no, after the doping with 50% and 25% doping of copper.
So I think after the question is, I think what Ashish is trying to ask, depending on the valence state of copper, the correlation effects might be important or not important.
Yeah, that is.
So what is, I mean, even at a nominal level, what is the copper D level occupation when you do 50%? So that's the question. Ashish, that's what you are saying.
Yeah, that is.
Yes. That's right. The electronic correlation is indeed important in this case, and we had done a more accurate calculation using, hybrid calculation in LDA plus U. It indeed breaks the topological nodes in the pure compound SRAGAS. So it makes it very narrow band gap semiconductors. But if you slightly change or rather, if you apply small pressure, one can realize this, Dirac node again. So
Okay.
the whole idea of this, work was to showcase that, under the same vertical, under the same compound, you can actually play with the symmetry and arrive at different topologically non-trivial phases. So, that's one of the reasons why we approached experimentalists to, cross-check these findings. There are some other studies also in the literature where people have shown this kind of symmetry breaking induced topological instability. But yes, the correlation is important.
Okay, sure. Yeah, thank you.
Yeah, Bahadur, you have a question? You can go ahead.
Yeah. Thank you. Just follow up on the last question. So you showed 20% copper doping. You realize a topological insulator, which we have to do if we break the C3V rotational symmetry, right? Because then only we can transition it from triple point to. So I'm actually, since you did this supercell calculation, I'm just wondering, how you break your C3 rotation? Sorry about a too technical question, but I'm just wondering about.
No, so the 25% doping actually breaks. It actually breaks the. It breaks the C3 symmetry,
right?
But it again restores back the center of inversion, and that's how you actually goes to a topological insulating phase. The center of inversion needs to be maintained, which you can't if you have a 50% alone.
Okay, all right. Okay, thank you. And second,
Go ahead.
Yeah, and second is you said your experimental collaborator are growing it. So is there any update like this alloying is made, or what's the status?
Okay, so they are able to make this compound. The synthesis part is done, and they indeed found for the 50% alloying case, and they indeed found same space group as we have simulated here. So that's a good news. However, the further measurements are ongoing.
Okay,
I'm just keeping my finger crossed to see what they find.
Indeed, thank you.
Manoranjan?
Okay, very nice talk. I have one simple, I'm just curious. So about the triple point, what kind of band are these? Is this the 3 bands? Are these spin up, spin down band, or can you please explain that?
Okay. So by the way, this band structure is a spin orbit coupled band structure.
Okay.
Right. So in a way, in this particular figure, they are coupled. I have not resolved them for spin up and spin down.
Okay.
But usually, these are, arsenic S and P and a small contribution from silver D, which gives rise to this 3-fold degeneracy.
Okay, so that means just 3-fold degeneracy is enough.
Exactly. So you can see in this small, is my slide visible, right? Let me figure. So you can see in this small inset, this lambda 6 band still remains doubly degenerate. However, this lambda 4 and lambda 5 got splitted because of the symmetry, and they they are each single degenerate band. So these points where they are crossing, so say lambda 4 crossing lambda 6 is a triply degenerate band, and so
Okay.
as the other one.
Okay. Okay. Okay.
So this
Great.
breaking of lambda 4, lambda 5, the splitting is happening because of certain symmetry, which is broken because of this copper alarm.
Okay. Okay. One more simple question is, do you know any compound where this nodal line as well as this triple point coexist?
Nodal line and triple point.
Both the coexistence of both of these two. I'm
No,
just curious.
I'm not sure. I'm not. Although one of my students is working on topological phonon aspect of it, and there they found some coexistence of topological nodal line and this kind of triply degenerate point. But they are on the phonon side. They are bands itself.
Okay. Okay. Phonon bands.
Yeah, and this is a KMG boron system.
Okay. 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 Thank you very much, Aftab.
Yeah. Okay. Jyotirma, you have one quick question. Can you make it quick?
So, sir, about the triple point. So, you told here that for non-syntosymmetric case, some kind of symmetry is generating this kind of triple symmetry. I mean the triple point. So, which kind of symmetry is generating this kind of triple point?
Sure, I think I just mentioned it. So, first of all, for a triple points, triply degenerate point, the center of inversion needs to be restored. So, forget about this particular compound. If you take any other material, the center of inversion needs to be restored, and there is a CS symmetry along gamma to A, which needs to be restored. All the other symmetry may be broken. And that's what the trick we used here, that we analyzed the structure and found that if I replace one of the silver by copper atom in a 2 by 2 by 2 supercell, you can actually show that these C3 and all mirror symmetry is broken, but the inversion is restored. So that is from the symmetry argument. Of course, the theoretical, analysis of all these symmetry-induced phases is straightforward, but finding it in a real material is not really trivial. But in this case, you indeed found that. So yeah, these are the symmetry requirements that you need to have for a triple point symmetry. Okay. You can look at some papers on molyphosphide and tungsten carbide, which are some of the systems which are experimentally synthesized and measured to show these kind of triple point symmetries.
Okay, thank you, sir.
Okay, and the last question by Swaroop, and then yeah, Swaroop, can you unmute and ask? No.
Yeah. So after this very nice talk, I just have a quick question. I was just wondering, for this copper alloy, you use some magnetism in the system.
Did you what? Sorry, Swaroop?
Did copper, when you broke by copper or you did the alloying, did copper has any magnetism?
No.
No. So copper does not contribute to the magnetism.
No. This is a purely non-magnetic system, both the parent as well as the substituted alloy ones.
Okay. So copper in D10 configuration.
Correct. Although it is d orbitals, but it doesn't contribute any magnetism in this.
Okay. So there will be no correlation effect then.
Yeah, well, there are some correlations, as I said in the beginning, but that is not really because of the magnetism, but the very, but the thing is, the correlation is very weak in this case.
Okay. Oh, thanks.
Okay, with that, let's thank Aftab for a very nice talk and move on to the next talk by Arijit Saha of IOP Bhubaneswar, who will talk to us on higher order topological systems. So Arijit, I'll just warn you at 18 that you have 2 minutes
Yeah.
of talk time, and then yeah, thanks.
Yeah, is my slides visible?
Yeah, but it's not in. Yeah, now it's fine. It's
Yeah.
okay.
Okay. Yeah. Thank you, Priya. So let me start by thanking the organizers for giving me the opportunity. So it's nice that this is a topological session in the morning, and so it will be continuation to the previous talks, previous two talks. So in this talk today, I am going to talk about higher order topological systems, and the previous two talks was mostly based on the materials and DFT based. But here I will mostly talk about the model systems because I'm a model person. And so this higher order topological systems are a bit new. And so these are these 5 publications so far is our contribution so far in this field. And this work has been done with the collaboration of my student Arnab Kumar Ghosh and another postdoc at Tanay Nag from Germany, and both of them actually have contributed largely to this project. And we're still working in these systems. So at the beginning, actually, I would like to be slightly briefly overview about the systems because these are new, and then I will shortly feature our works, at least not all the works, the most recent one. So before starting, so just give me the outline of my activities. So my main activities are going on with my 4th student, and so this Shayan has worked on this correlation effect in topological systems, which definitely I am not going to talk about, and he has submitted his thesis very recently, and this work in this area has been done with the collaboration of Anamitra, one of the organizer of this conference. And another student, Pritam, is working on the wild physics and more very interesting subject, a new subject, which is the interplay of topological magnetism and topological superconductivity, basically Skyrml and Majorana interplay physics, with the collaboration of Ashish. And Arnab, and basically is the main person with whom I have started working on this higher order systems. So yeah, and so we have basically started working on the dynamical version of the Floquet generation of this higher order systems. So before going to the Floquet or the dynamical version, so I should talk about the basics of this topology, of the higher order topology. So let me start with the outline of my talk today. So first, I will give an introduction to the topological systems to start, and then why this Floquet band engineering is interesting in these topological systems. And then I will flash about our recent work, which is how to generate this higher order topological system by some periodic driving in 2-dimension and 3-dimension, to starting from a lower order topological systems. And if time permits, then we can talk about the superconductor also, but let's see how far we can go. And then we summarize and conclude. So to start with the basic phenomenology, which my previous 2 speakers have talked about also. So these topological insulators, the last decade has been devoted in studying different aspects of this interest of this the modern subject. So which are band insulator in their bulk, and due to the presence of strong spin orbit coupling, they can have very non-trivial gapless modes at the boundary. So for a 2D topological insulators, you can have one-dimensional edge modes, and where the spin and momentum are locked. So these are helical states because of the upspin is coupled to the right mover and the downspin is coupled to the left mover, or vice versa. So as spin orbit coupling preserves the time reversal symmetry of the system. So this edge modes are basically the Cramer pairs, and these are really robust states in the sense that if you put an impurity, so backscattering is forbidden, because to have the backscattering, not only the momentum direction but also the spin has to be reversed, which is not possible if you want to do it here. So in that sense, they are robust. And also, this bulk band of the systems has to be characterized by some topological invariants, which some of them Bahadur has already talked about. And similarly, in 3D, you have a 2D surface states, which are non-trivial, and they follow this 2D surface states looks like a massless real spectrum. So the first experiment, the realization of this system in 2D, was this mercury telluride quantum well sandwiched between two cadmium telluride materials. So where you can see that the electron band in this cartoon, the electron band and the whole band, due to strong spin orbit coupling, when you change the width of this well, you have a band inversion. So due to this band inversion, somehow the positive band gap goes like conduction band and valence band gets inverted, and you have a zero mode due to this inversion transition. And to remind you, the basic models was proposed. The first model was the Ken-Meyle model, which in 2D, which was based on graphene. So this model has a electron hopping type and intrinsic spin orbit coupling, because the spin orbit coupling is very important to have these topological systems. And if you look at the H-state spectrum of this 2D system, you can see this edge modes with the upspin and downspin along the boundary. And similarly, one can write a model for the 3D. So because after the Ken-Meyle model, another model came, which is the Barnaby-Hu-Chang model. So this is basically the 3D version of it. So where one can see that you can have the signature of the 2D surface states. As a material, the Bismuth solenoid was the system which was following the 3D topological insulator properties. So anyway, so these are the basic history of the basic topology. So in around 3 years back, so in this paper, by the science paper, so Barnevik, Binalkazar, Barnevik and Hughes, they proposed that you can have a different kind of topological systems. So like in 3D, if you have a 3D system, so these are 2D surface states, which if you think that these are kind of first order topological insulator, then what can happen is that not only the surface, but here the hinge of this 3D systems. So you can have non-trivial states along the hinges of this 3D system, or you can have, so these hinge states are gapless propagating states, but you can also have zero-dimensional localized corner modes along the corners of this 3D system. So similarly in 2D, you can only have the corner modes, because the boundary, the first order boundary is edge, sorry. So the second order boundary, second order topological states are the corners. So in principle, I can define that to define a higher order topological system, I can define it as a system which has a d minus n dimensional boundary states. So for example, if so d is the dimension and n is the order. So for example, if d is, let's say, 2 and if n is 1, then you can see that you have 1D H state, which is the usual first order topological insulator. But if you have d n is equal to 2, then you will have this zero dimensional corner modes. So which is second order topological insulator or 2D higher order topological insulator. And similarly in 3D, so 3 minus 1 will give you the 2D surface states, but 3 minus 2 will be the hinge modes as it looks here. Or in 3D, it will be D3 minus 3 will have this coordinate states. So this is the definition of the higher order systems where you have new kinds of topological modes along the hinges, which are propagating, but also you can have zero-dimensional localized modes at the corner. And so, like the first order topological insulator, one can have classifications of this, etc. So which I'm not going to discuss. So rather we can see that how to understand this in a model, in a simple model, how to understand this, at least some part of it. So, so this paper by Schindler group by Titus Newport, so they showed that suppose if you have in 3D, if you have this model, let's say, so where M is the mass term in the model, so T is basically hopping and lambdas are the spin orbit couplings. So now you add a new term in the system with the amplitude delta 2. So what this term does, it breaks both the time reversal symmetry and the C4 rotation in a square lattice in the system, but it preserves the combined C4 tau symmetry. So that is fine. So the beautiful this model says that if delta 2 is 0, if this mass term, if this term is 0, so then within this regime of the mass term, it describes a first order 3D topological insulator. So you get 2D, you will get 2D surface states. So if you look at the phase diagram of this model, so delta 2 is this symmetry breaking term and M is the mass term. So in this plane, if delta 2 is 0, you have a normal insulator to first order 3D topological insulator phase. But if you introduce non-zero delta, then you have a higher order states and this higher order topological insulator states. And this higher order topological insulator, at least in this model, one can have only the hinge modes. So this model describes a three-dimensional second order topological insulator where this you have chiral hinge modes because you have broken time reversal symmetry also. But we can also have helical hinge modes that I'm not discussing. So you need to have other kind of slightly different mechanism. So the thing is that why this hinge modes are coming, one can intuitively understand that what happens if you look is that if you look at this picture and so the bulk of the system definitely is insulator or capped, but what happens is that due to the presence of this this term, so I'm sorry that this is a typo, so this actually this gap this lambda should be of the order of this delta 2, but whatever. So what can happen is that if you look at these two surfaces, so let's say xz surfaces and yz surfaces, you can have a different mass changes along the two surfaces, at the two adjacent surfaces. And we know from Jacobi theory that if you have a two mass term which is opposite along the two interface, then at the interface around the interface, then at the interface you will have a zero mode. So this zero mode, appearance of this zero mode is kind of consequence of the Jacobi theorem along the from the surface point of view. So you can see that not only the bulk is gapped here, also the surface has to be gapped with a different sign so that you get the hinge modes here in 3D. So how to get the 0D corner modes? That is another one is to see slightly more different story for that. But if you do the same thing in 2D, you will get the corner modes. The mechanism is, I mean, the intuitive understanding is same. This is along the two edges. Basically, your mass term will be different, opposite. So, like first order topological systems, one is to ask the questions that how to characterize these bulk bands of these systems. So one can actually calculate or generate, or one can actually invoke different kind of topological invariants. So for the first order topological invariant, actually from one can show that the dipole polarization is basically describes the first order topological insulator, where A is the very connection. So similarly, if you have for this second order topological insulator, you have vanishing dipole polarization, but you have a finite or half quantized quadrupole moment. So these are higher order in the sense, so you have a finite quadrupole moment, and this finite quadrupole moment induces some H polarization and effectively the corner modes. And similarly in 3D, you have to calculate some octopolar moment. So, but here at the bulk, both the dipole polarization and quadrupole moment is 0, but you have a finite octopole moment. So to have a true higher order topological systems in 2D and 3D, you really have to see that whether this quadrupole moment and octopole moment is actually half quantized. And so, and from intuitively, you can think that for this 2D second order topological insulator, we have gapped edge states and in-gap corner states, and the bulk is definitely gapped. And for the 3D case, you have both the bulk, both the surface and the hinge states are gapped, so that you have in-gap corner modes. So this, so the calculation or the, so this is a paper by Benalcazar, Barnaby, and Hughes, where they have discussed, at least for the static case, what are the, how to calculate this invariant, the formalism, which is, this paper is a very extensive long paper, and it's not, so yet we follow this paper, and usually one follows this paper to understand this topological invariance. So now whether these systems are just theoretical prediction, is there any understanding from experimental point of view? The question is still the we have still, the thing is that we are still in a lot to do, lot more challenges, but at least I can show, I can flash few experiments, like in a van der Waals stacking of bismuth halide jets. Very recently they have seen the evidence of higher order topological states by the RPACE, and also in bismuth. And there are also mechanical systems like classical system, for example, circuits or acoustic systems, where this kind of topological states can be engineered. But at least the models that I showed you is, I'm not saying that the models are absolutely related to these experiments, but at least one has some motivation to start with that from this experiment. So although explaining this experiment needs different theory, I guess.
Yeah, Arijit, you have 2 minutes of talk time.
Yeah, sure. I mean, I want to motivate first.
Okay, good. Yeah, sure.
Yeah. So I think I can skip the superconducting part. So let us see that why this Floquet business is important, because we want to generate this higher order topological systems by the external drive. So so why, I mean, so if you think about this Floquet driving irradiated system, so it starts from the basic graphene, which is trivial gapless systems. Or so what happens is that if you take a gapless graphene and if you drive it by some external irradiation, so this cartoon, let's say you have external irradiation of this form. So what happens is this driving, even the frequency of this drive is very large compared to the bandwidth, it opens up a band gap. So it generates kind of at the Dirac point some Halden-Master. So graphene to start with, which is a trivial, it becomes a topological insulator. Also the same you can do it for a semiconductor or for a gap system. There actually you will have, and if your frequencies of the order of bandwidth, you have a lot of resonant transitions along these contours. So which actually gives rise to the dynamics in the problem. So what happens is that even in graphene, so so if the frequency becomes smaller or compared to the bandwidth, not only at the Dirac point, you will have new dynamical modes at the finite energy, let's say at 0.5 in this case. So this new dynamical states actually gives rise to the field of Floquet topological systems. So to start with the semi-metal or trivial system, actually one can engineer a topological system by an external drive. So in our work so far, actually our motivation is that the question to start with, that can we generate the higher order topological modes and hosting these dynamical higher order modes in presence of external periodic driving, and if I start from a lower order topological insulator. So my static system is a lower order topological system, and I will give some periodic driving in it, and by that can I generate this Floquet higher order topological systems. And these new modes, which I showed here, like in graphene, you get these dynamical modes, which is the edge mode in case of graphene, or in case of 2D topological insulator. But so can we do it for the higher order case also? So to start with, I mean, in this case, we have taken not a external electromagnetic wave, rather we have taken a simple step drive. So let me show that actually you can really to start. So our starting model is a static 3D topological insulator or 2D topological insulator. And if I drive it, so this is a phase diagram. You can see that in this phase diagram, you can have a phase where both the zero mode and the dynamical mode, which is called the pi mode, can coexist. And you can have phases where you can have a trivial mode, no mode, the trivial, only the zero mode and then trivial, or the pi mode alone, or the both can coexist together. And if you see the local density of states of the system, you will see that you have corner localized modes in the local density of state. And in the quasi-energy spectrum, if you see, you can see that in the quasi-energy spectrum, so all the edge modes are gapped. So bulk and edge modes both are gapped. But if you look at the spectrum in a open boundary condition along both the directions, you will see that you not only have this corner modes at zero, which is the zero mode, but you can also have finite energy at pi. You will have the new modes you can generate. So these are the equivalent dynamical mode that I showed for graphene, and in this case, so that means that to start from a lower order topological system, I can generate the from a lower order or first order topological insulator, I can generate a higher order topological insulator, which can host the corner mode in 2D. So similarly, one can generalize this 3D, which is much quite harder problem. So in 3D also, you can see that you can have the hierarchy of all. You can have the hierarchy of higher order modes. So both zero mode and pi hinge mode in 3D second order topological insulator, and also you can have 3D third order Floquet topological insulator, where both your hinge and your bulk, your hinge and surfaces are gapped, and you can have the corner modes at 0 and in pi. So I think, so I just want to give you the flavor that yes, I mean, like if we start from a semi-metal, I can generate a Floquet topological insulator. Similarly here, if I start from a first order static topological insulator, I can engineer a Floquet second order or third order topological insulator with this dynamical mode, which is the Floquet higher order topological insulator in that definition. So we also checked it with the mass kick protocol, and mass means here theoretically the mass, we have given a kick to the mass term in the system, and there also you can see that as a function of the frequency of the your drive, you can have a phase transition where you can have this 0 mode and pi mode emerges. And also you can tune in the phase diagram, you can also tune a number of 0 mode and pi mode if you lower your frequency, let's say. So, but anyway, so if you want to look at the details, you can look at this recent archive. Yeah. So also we have done the same for superconductor, so which I don't want to go into. So at least to summarize, and what is the take-home message from this talk is that if you take a first order topological insulator, they have conducting propagating states at the d-1 boundary, which are the 1D edges or 2D surface. But if you take a d-dimensional higher order topological insulator, they possess d-n dimensional boundary modes. So in particular, if you take a 2D second order topological insulator, which will have only 0D corner modes. But if you take a 3D second order topological insulator or third order topological insulator, so you will have respectively 1D hinge, propagating hinge, or 0D localized corner modes. And to characterize this bulk topological invariant of this bulk of the systems, you have to calculate, or you have to find out the quadruple moment or octuple moment with certain symmetries. And so far, the experimental realization is in solid state materials and acoustic systems or classical electrical circuits, but there are a lot to be found out in the, as far as I know, in this so a lot more experimental challenges. And regarding the dynamical version of, or the Floquet version of this higher order systems, we know only one experiment so far, which is even in acoustic systems, not in material. And this new bulk boundary correspondence also can be generalized in case of superconductors, which is called higher order topological superconductor, which I have not discussed. And this also the dynamical version of this higher order modes can be generated with periodic driving, starting from a first order or lower order topological insulator. These are called Floquet higher order topological insulator systems. So what are the issues that still remain is that the 0 pi modes, or the phase where both the 0 pi modes exist. So the characterization, topological characterization of this phase. So actually one really has to find out that the dynamical quadruple moment or dynamical octuple moment. So we are working on that. So far we know that we can calculate the dynamical quadruple moment if you have certain mirror symmetry in the system. But at least our Hamiltonian breaks the mirror symmetry, so it's slightly more harder. So in that case, and also the dynamical octupolar moment, which will topologically characterize the 3D third order topological insulator, which is the most hardest part. And then the effect of strong disorder on this Floquet phase, because already the concept of Floquet Anderson insulator phase exists for first order or lower order topological systems. So now if one can investigate, it is a lot more investigation that is a Floquet higher order Anderson insulator phase exist or not. And then also the transport signature of this Floquet hinge modes. So if you want to look at my publication, this is the archive link. And at last, I would like to thank for your attention and patience. Thank you.
Yeah, thanks, Arijit. So anyone who has a question can unmute and raise their hand. Just a second. Anybody? Yeah, whoever from the School of, you wanted, I don't know who it is, from the School of Physical Sciences account. Yeah, can unmute.
Hi, I think this is Anumitra. The School of, because we are the host, I think it shows as School of Physical Sciences.
Yeah, so since it's 4 of you or 5 of you, I don't know whom I'm supposed to say it.
Yeah, so I think it's me, Kush and Ashish. If we ask questions, generally it will show up as like this, through
Okay,
this
fine.
portal.
Yeah, okay.
Okay, so Arijit, nice talk. One question in this Floquet drive, you're doing it in what kind of regime, in the sense of adiabatic or sort of Non-adiabatic.
At least in this step drive, let's see the drive will let me show you. So in this step drive, the frequency will not matter actually, because this J1 prime or J2 prime, so your time period or frequency is there already. So you can go to all the frequencies you want.
I see. But it would not matter how quickly the step rises, because I was thinking, in a step, if you Fourier transform, it will generate all sorts of omegas. But you are saying that the J's themselves have omegas in them?
Yes, these are dimensionless parameters.
But there's a frequency dependent parameters per se.
Yeah, there is a time period. So in that sense, frequency is there.
And there is no issue with continuing your state. So the system would respond equivalently for slow, fast driving. Of course, this is a step drive.
This is a step drive, and you will find the evolution operator after time t. That's it. So this is kind of, yeah. Yeah, you can find the evolution operator after the full time t, and from there the effective flow Hamilton.
Okay, so you are doing an exact theory anyway, so it doesn't matter, you're saying.
Yeah. At least for this drive. But if you take an external periodic drive, I mean, like laser, then definitely one has to worry about.
I see. Okay, sure. Thanks.
Yeah. Saurin? Yeah.
Okay, so actually, I wanted to also ask Aftab similar questions, and this is what is triggering this question. So, Arijit, my question is, when we think of higher order topological insulators, we talk about the quadrupole and the octopole moment, and now when it comes to Berry curvature, the usual kind of Berry curvature we talk about is these monopoles, right, which come from some description of spin half in a magnetic field.
Yes.
So that's a and that corresponds to two-level system. So band touching point of two bands.
Yes.
Now the moment you start thinking about something higher, you have to think of not a spin half but a spin one. Let's say 3-band touching will give rise to a quadrupole moment. A higher number of band touching will give rise to higher, octopole and so on. So I was curious, how does that band touching picture? Do you need that somewhere? And
yes. So
how does
you need it actually. So
where does it come? So can you tell us where this multiple band touching comes in?
Yeah, it's here. So if you look at, so yeah, this is for the superconductor, but let's forget about it. So here actually we calculated the quadrupole moment as a function of this, let's say, some parameter which will drive the transition. So you see that when the quadrupole moment becomes half here, quantized, there actually you have a band touch.
But how many bands are touching? I would imagine that you will need more than 2 bands touching, because the description of 2-band is a spin half, that's a monopole, and description of 3-band is a spin one, which can have quadrupole, because a 2-band touching doesn't have a quadrupole moment.
I agree. So yeah. So we have 8 bands in this model. So
I see. This is the minimal 3-band model. I would imagine for a quadrupole moment, the minimum band touching you need is 3, and that is what comes back to Aftab's model. That's why
I think you need minimal 4-band model to have this.
You need 4, is it?
Yeah.
In principle, I think quadrupole moment you should be able to manage in 3, and it exists. I don't know how
it exists. Yes.
It can be accessed through a model.
Yeah. So the minimal model is actually 4-band. Like even in the higher order topological insulator model I showed you, this model, it has a 4-band model.
And somewhere in the parameter space, you have this touching of this.
Yes.
The transition must be through then 4-band touching.
Sure, 4-band touching.
Okay.
We'll check once again after your question, but I'm sure.
Okay. Thank you.
Yeah, Yogendra.
So can you hear me?
Yeah.
I have a general question. Is there any field theoretic understanding of this higher order topological insulators?
Yeah. So okay. So field theoretical understanding, not as far as not in detail as far as I know, but you see that this at least this higher order topological insulator here, the underlying field theory should be a non-abelian gauge theory. Like the theta term, or like if you think about the Berry phase, So the Berry connection usually here is basically it's a matrix. It's a non-abelian Berry connection. So somehow the underlying field theory, I am not very sure about the field theory because I don't know, but I have not seen.
Okay, thank you.
But this is my intuition. With the theta term, which should be non-trivial, not like the usual chance.
Yeah, and Diptiman?
Yeah.
Yeah.
Okay. Yeah. Okay. Thanks. Arijit, nice talk. I
Thank you.
just had one question. So there was a figure you showed where there were like 8 zero modes somewhere with the delta function kicking. Yeah, this one.
Yeah, this one is for the superconductor, which I have not done. But yeah.
So is there a limit to how many of these zero modes you can produce?
Yes, you can actually control by a magnetic field how many you need.
Okay, but can you produce more and more of these by?
Yeah, at least with this drive. Yeah, that's a good question. So at least I mean, yeah. So if you see this phase diagram of this periodic drive here, actually you can if I extend my parameter space, you can have more basically.
Oh, I see. Okay. Yeah. Okay. Fine. Because in a different model, we found that. With
yes, I know your work. If you change your frequency, if you lower your frequency, you get more Majorana modes in your work. Yeah, that I know. So yes, that's a relevant question.
So you can do that. You can do that here also.
Okay.
Yeah.
Yes.
Okay. Thank you. Yeah.
Okay, so we again thank Arijit for a nice talk and move on to the last talk of the session, which will be given by Krishanu Roy Chowdhury from Stockholm University, who will be talking about supersymmetry, topology, and entanglement. So this is a 15-minute talk. So I'll warn you at 10, Krishanu, so that you have 2 minutes of talk time and 3 minutes for questions.
Hi, am I audible?
Yes, you have to go to the full screen mode. Yeah. Okay.
Yeah. So can you see my slides moving?
No.
Is it still not moving?
Your slides. We can see your slides. You have to go into slideshow mode.
Yeah, I am in the slideshow mode, but if I change the slide, do you see it's moving?
No. Because we are seeing it in the the presentation mode. We are not seeing the slideshow mode. So
yeah. So now I have moved into the slideshow mode. Do you see it in the slideshow mode now?
No, we don't. One thing is you could just click on, on the panel on the left and change slides. Or if anybody has a better suggestion.
So do you see my slides now, like in the slideshow mode?
Now it's fine.
And is it moving now?
Yeah.
Okay, do you see my collaboration slide?
Yeah, we do.
Okay, cool. Okay, so I think good morning, everyone, and thanks to the organizer for organizing such a nice platform. So in this talk, because it's a short talk, so I will give you a glimpse on one of our very recent exploration. I will basically highlight a route to realize topological mechanics from models of spin liquids, which is electronic models, and the route will be the supersymmetry. Let me first thank my collaborators, Jan Attic and Simon Trebs from the University of Cologne, and Michael Lawler from Binghamton University. With this, let me start from the place called topological mechanics, which is partly flashed in previously in Arijit's talk. So this field has recently received a tremendous surge, where people are trying to realize electronic responses, topological responses in electronic system, but in mechanical systems. So they are devising mechanical analogs of those electronic systems, which show similar topological responses. The field was actually kicked off by a seminal paper from Charlie Kane and Tom Lubensky in 2014, where they explained the following: that if you take a mechanical frame particularly if you're interested in the isostatic limit of the frame, where the number of zero modes are exactly balanced by the number of self-stress modes in that frame. So when the frame is isostatic, their difference is zero. So this index, which I call a Maxwell-Caledine index, is zero. And this can be re-expressed in terms of the total degrees of freedom in the system and the total number of constraints. So the example of isostatic lattice in 2 dimension will be a Kagome lattice. In 3 dimension, it could be a Pyrochlore lattice and others. But what Kane and Lubensky did, they started from a much simpler model. They started by looking at a 1-dimensional model where you can see the topological mechanics of the bulk is rigid here when you change, but you have a very soft floppy modes at the edge. So they called it a mechanical analog of the SSH model, even though that's not quite correct. It's not a mechanical analog of the SSH model, but it's a mechanical analog of the Kitaev superconductor, Kitaev chain of topological superconductor. Then from Kane and Lubensky, this work was extended to higher dimension, where particularly there was a work from the Huber group in ETH, where they tried to realize a model of topological insulator in a system of classical pendulum. So in the next slide, you can see that this is the system. If you now perturb the masses on the edge, there is a flow along the edge only, and the bulk remains relatively rigid up to the system size and the finite penetration depth. And the 2 polarizations here in the mechanical system coming from the vibrations of the pair of strings, you can see, and they are resembling the 2 spin states of a helical edge state in a quantum spin Hall insulator. So that's the first mechanical analog of quantum spin Hall insulator realized in a system of classical pendulum. But and then there exist other works which I think Arijit also flashed. They realize things in electrical circuits, in acoustic systems. But basically, what they all tried to do by proposing these topological mechanical systems is a matrix correspondence. And the matrix correspondence is the following: you take your Newton's equation, which we all know, it's governed by the dynamical matrix called D, and then you do a square root to write down Schrödinger's equation. So here you have a Schrödinger's Hamiltonian. That's the quantum mechanical system for me. That's a one-to-one mapping from a classical mechanical system to a quantum mechanical system. If you closely look at these Schrödinger Hamiltonians here, it has a particular block of diagonal structure. It belongs to the symmetry class BDI in the tenfold classification of electronic insulators and superconductors. But what I'm going to show you in this talk is that there exists an exact supersymmetry correspondence between a system of fermions and the system of bosons, because of which you can realize certain fermionic systems in mechanical systems, which inherits the topological properties of the fermionic system. Okay, so let me start with introducing a few basic ingredients of supersymmetric quantum mechanics, which is required for this talk, even though the audience might be well educated about these ingredients. So I start with a non-Hermitian supersymmetric charge operator, which is this Q for me. So it entails a system of fermions and also a system of bosons. They need not be the same in number. So this matrix, which is sandwiched between these operators, this R is an arbitrary complex matrix, and that can be a rectangular matrix as well, if the number of fermions and bosons are not same. So, and then if from this supersymmetric charge operator, if you compute the supersymmetric Hamiltonian, you see that the Cauchy Hamiltonian gets decoupled into 2 free Hamiltonians. One is a free fermionic Hamiltonian, the other is a free bosonic Hamiltonian. And the 2 Hamiltonians are these are of the following structure. One is given by R dagger, and the other is R dagger R. And of course, you immediately realize that they have similar spectrum up to the 0 mode. So all the finite energy eigenmodes between these 2 matrices are exactly equivalent, but the 0 modes can be different because the null space of R can be different than the null space of R dagger. So they can have different number of 0 modes, and that's also related to the topology of the supersymmetric charge, which we know as the Witten index. But I'm not going into the details of this thing. Rather, I'm directly coming to how I can implement this supersymmetric structure and propose a topological mechanical model. But the mechanical systems which we encounter, these are defined by space-phase coordinates, these Q and P, and they are they satisfy some commutation relation, these are real bosonic operators. So naturally, we expect their supersymmetric partners to be real fermionic operators, which we know as Majorana fermions. So here, what we do now, we construct a supersymmetric charge, which now involve real bosonic operators and real fermionic operators in this following fashion. You can see I have two flavors of bosonic operators, Q and P. So I will need two flavors of Majorana operators, which I'm calling A and B. So at the moment, these are just two flavors for the Majorana operators. And then the supersymmetric charge is defined in this way. So what it is doing, that it's coupling this B-type operator with this P operator via an identity matrix, and the A-type operators with Q via this connectivity matrix. So if you now compare it with the form of the non-Hermitian supersymmetric charge, which I flashed a couple of slides back, I wrote an R matrix, and then if you now rid of the R matrix from this supersymmetric charge, it is in a block diagonal form. So that's particularly simple form. And then if I calculate the supersymmetric Hamiltonian, the resultant free Hamiltonians will also be simple. The fermionic Hamiltonian is now a Majorana Hamiltonian, and the bosonic Hamiltonian are now given in terms of this P's and Q's operator. They are quadratic in this P's and Q's operator, and there will be familiar consequences of this bosonic model. But now there is another aspect which is important here, is that if I now give these two flavors a lattice structure, so now I'm introducing a lattice in this problem, and I'm saying by Majorana fermionic Hamiltonian, the Majorana fermions in this supersymmetric charge are residing on a bipartite lattice. So that carries these two tags A and B. Then I can actually interpret this fermionic Hamiltonian as a hopping model of Majorana fermion on a bipartite lattice. Okay, but then what happens to the P's and Q's operator? So if you look at the supersymmetric charge, you see that the B Majorana fermions are connected to the P operators by an identity matrix. So that means the P operator must sit exactly where the B Majorana fermions are sitting. And the A operators, the A Majorana operator is connected to the Q via this connectivity matrix, which is also the hopping matrix for the Majorana fermionic Hamiltonian. So then the A operators should be connected to the Q operator via this hopping. So that means the Q operator should also sit on exactly where B is sitting, because A's are connected to B via this hopping matrix. So what means, if you look at this picture then, so my A and B Majorana fermions are sitting on two different sublattices of a bipartite lattice, but the Q and P operators are sitting on one of the sublattices. If you change the tag A and B here in the SUSY chart, then both the operators will shift to the other sublattice. But the crucial identification is that the bosonic, the two bosons are sitting on one of the sublattices when I introduce lattice structures in this supersymmetric charge, where the Majorana fermions are hopping between the two sublattices in the problem. Okay, so now having realized, okay, and here this R is formally known as the rigidity matrix of the mechanical systems. This A matrix is often called the compatibility of a mechanical systems, and A transpose A together is called the dynamical matrix, which I showed to you in the beginning. So what this R matrix basically does, it connects mechanical systems to Majorana analogs, supersymmetric partners of each other, and vice versa. So if you can give me a fermionic Hamiltonian, a Majorana Hamiltonian, then via this route, I can give you a mechanical system which will inherit the properties from that Majorana Hamiltonian. And this will be the last part of the talk, where I will give you some example. But before going to the mechanical example, let me highlight one important point, is that so far I have quantum mechanical bosonic operators P and Q. I can take the classical limit, where I will replace their commutations via the Poisson bracket, and then I can realize a mechanical system. This is a very familiar looking mechanical system that it's a system of mass and springs. The springs are encoded in these, the spring constants are encoded in the D matrix, and the mass is taken to be unity. And then you can of course get the spring constant by solving this D matrix, or of course from the input of this A matrix. So the upshot is that if you give me a Kitaev model or a Majorana model, which is characterized by A, then I can give you the mechanical system where the springs are uniquely determined.
Okay, You have 2 minutes of talk time.
Okay, yeah, sure. So let me now go to the example. So I will be super quick here. So we know that there exists a famous model of Majorana fermions. It's called Kitaev model. It's a model with a Hamiltonian with bond-directed spin exchanges. And then you can solve this this model exactly analytically by casting the spins in terms of this Majorana fermions via this Kitaev trick. And then this model has a phase diagram, which realizes both a gap spin liquid and a gapless spin liquid phase. So if you now follow the supersymmetric route, you will be able to design a mechanical system which is sitting on one of the sublattices of the honeycomb lattice, as I showed to you. And now, if you construct this mechanical model from the Kitaev Hamiltonian, and I want to see that what is the response of this mechanical model which I have constructed. So for that, what I want to do that if you shake the central site here for a given frequency, you will see that there will be a pattern in the real material. If you take a finite system, there will be a pattern if you shake these central site. If you shake it at a different frequency, you will see that the Fourier transform of the pattern will change. So at various frequency, you realize various patterns, and if you stack them, you basically get the frequency spectrum, the phononic spectrum in the mechanical system. What is interesting to note is that you see that there is indeed a gapless mode in the mechanical system. That's not a Goldstone mode. It's around this K point, and also there exists a gapped phase in the mechanical system where the system develops a low energy rigidity. So unless you shake the system beyond a certain frequency, the system will absolutely show no response. Okay, so we can continue to this another example of higher order topological insulator. I think the interplay of what Arijit was mentioning between the dimension and the order of the surface modes is sort of summarized in this picture, that you can realize different order of topological insulator in different dimensions. So I take a very simple model of topological insulator, but that's now involving Majorana fermions. I start from a square lattice. I take 4 sites in the unit cell. So I have zone folded the structure. Now I apply a pi flux. So that sort of make degenerate bands and Dirac cones. If I now introduce staggered hoppings, I get a gapped bulk, which quantized quadruple moment. And then if you change the hopping parameter, this gamma and lambda in this model, then you can realize 2 different phases of this model, which is the trivial and the topologically non-trivial. The topological non-trivial phase is characterized by a quantized quadruple moment with a corner mode response. And this is exactly what you can do in the mechanical system, which you can derive from the square lattice Majorana model. So if you construct this mechanical system here, and if you now do the exact shaking and derive the phonon frequency in that problem, you will see there exist 2 different modes, 2 different phases. One is the gapless phase, the other is the gapped phase. And you can see that in the trivial, in the topologically non-trivial phase, there are soft corner modes, which are actually topology protected. So the topology is, let me give just 1 minute to describe the topology. So we know the fermionic Berry curvature takes the following form, and it's important to characterize the topology in the fermionic systems in terms of this, what is called this baryology. But if you go to the bosonic system, the baryology changes. So if you just calculate the conventional bosonic Berry curvature here, you will get no response. You will do not see any quantized invariant coming out. But if you actually add this additional covariant derivative induced by this supersymmetric charge, you see that there is indeed a bosonic quantum mechanical invariant, a bosonic topological invariant, which is protecting these topological response in these mechanical systems. Yeah, I think with this, I would like to take questions.
Yeah, thank you, Krishano. So the talk is now open for questions.
Hi, can I ask a quick question?
Yeah, go ahead.
Yeah. So, Krishanu, so you talked about this equivalence of this mechanical model to the Kitaev model, right? So I assume this holds both in the gapless and the gap phase of the Kitaev model.
Yes.
Okay. So in the gapless phase of the Kitaev model, if I then turn on a sort of a small magnetic field, the problem turns non-abelian. Is there some simple analog of seeing that kind of physics in your mechanical model? I mean, So in principle, you can tune this rigidity matrix R, which I told you, because so I'm in the abelian phase of the
of the Kitai model. And yes, it is possible to actually tune your R matrix so that you have you have a different models, different Majorana fermion model, which includes now the block diagonal terms, because you see that now my Majorana model only includes block of diagonal terms. And then that will lead to a mechanical system, probably with charged coupled oscillators. But we haven't yet solved the mechanical analog of the non-abelian excitations in this problem.
I see. Okay, because I was just I was just wondering what's sort of the signature in your mechanical quantities, right?
Yeah,
okay.
That's something which are under investigation.
Okay.
Yeah. Okay. Saurin, you can unmute and ask.
Yeah, Krishanu, yeah, thanks for the wonderful talk. I mean, making connections to very different subjects, classical to quantum. So you mentioned supersymmetry. Is there a possibility of spontaneously breaking supersymmetry by the state, not by the Hamiltonian? And what happens in that case?
Yeah, I think so far I am talking about systems where supersymmetry is unbroken. So you have you have normalizable zero modes on one side that might not have a supersymmetric analog. Yeah, I do not know of an immediate example where I can spontaneously break this supersymmetry, but then I'm not sure that what will happen to the zero modes, etc. Then this Witten index or something is not a very conclusive.
Yes, that's why I'm asking. Then is your topology in danger? That's why I'm asking.
No. The finite topology. No, it's absolutely no, absolutely not. Yeah. The topology for the finite modes are still there in place.
I see. But we always understand topology into somehow obsessed with zero mode and connecting it to topology.
No,
right? You are saying that obsession can be left aside.
Yeah. There are topology in the finite energy modes as well, and these are holding that.
I see. Okay, maybe this requires a discussion. Fine. Okay, thank you.
Yeah, Yogendra, can you unmute and ask your question?
Yeah. So, can you say anything about, something about excitations in this Kitai model analog?
What excitations? Sorry, what excitations you are saying?
Excitations in the Kitai model analog, like.
Well, these are Majorana fermions, and I'm discussing the. I mean, if you do this pattern constructions for the Kitai model, the emergent spinons are Majorana fermions, which are coupled to the Z2 gauge field. Of course, what I haven't told you is that the Z2 gauge field is frozen for my system. So I'm restricting myself within a particular flux sector, and I cannot capture the flux fluctuations in this model.
There are no magnetic excitations analog in
No, I'm still not in the. I'm still happily roaming around in the abelian phase and not fully explored the non-abelian phase. Yeah, that's something which is worth considering to know that what are the mechanical analogs for those things, because there are several interesting phenomena going on in the non-abelian phase. Yeah, but I'm still in the abelian spin liquid phase.
I mean, even in the abelian, you have these fluxes, so you cannot access those in the mechanical system. That's
no, I have frozen those fluxes actually. So I am in the, because if you look at my Kitaev, the Hamiltonian, the Kitaev Majorana Hamiltonian, which I start with, that's really the simple looking Hamiltonian where the flux are already frozen to. So if you look at this fermionic Hamiltonian, the flux are no more present here. So I have taken a particular frozen configuration of flux in the system to derive this quadratic Majorana Hamiltonian.
Okay. So there is a constraint in the Majorana representation for the spins. So is there any such thing for your case, or do you need any constraints to limit the system? Or
no, you can even go to the higher spin. I mean, there exists other spin 3/2 model where you can realize this kind of Majorana problems in other lattice geometries. So there exists, for example, the system of spin 3/2 on Sastry-Sutherland lattice where you can cast that into Majorana fermions, and you can realize very like chiral spin liquids. You can also have higher order insulator of Majorana fermions there in the same model.
Oh, but there is a constraint, right? Like in the
there is a constraint. So but I have already taken that into account in the sense that I start with the quadratic Majorana model to start with. So you have already taken that constraint into account when you have derived the Majorana fermion models from the spin model.
Okay. Just by freezing flux, you can. Yeah.
Okay. We just moved to the last question by Deeptiman. Deeptiman, do you have a question?
Sorry, I forgot to unmute. Okay, so nice talk, Krishanu.
Thank you.
So this idea is very nice, using supersymmetry to generate a mechanical model. Now, if I remember correctly, supersymmetry quantum mechanics even allows, not anharmonic oscillators to have a supersymmetric structure. I mean, it doesn't have to be quadratic. So if you did that here, you'd probably get, you might be able to generate nonlinear theories, meaning things which are not quadratic in P's and Q's. And with supersymmetry, is that a possibility?
I mean, of course, I mean, one thing which we want to sort of explore a direction that my supercharge here, if you look at this supercharge, I mean, for example, if I look at the supercharge, which is the quantum mechanical, the version of the supercharge that's particularly quadratic in terms of fermions and bosons. So you can modify this supercharge operator, of course, because there exist interacting models of Majorana fermions and Kagome lattice where they have proposed that model by deriving from a supersymmetric charge.
Oh, okay.
Yeah. So there is a paper by Michael Franz and others where they have actually written down a supersymmetric interacting Majorana model on a Kagome lattice. But they haven't coupled it to any bosonic systems to realize whether there is an interesting bosonic analog of that system or not.
Right.
Yeah, it could be that you get this kind of nonlinear terms if you do that.
Yeah, so it might be interesting to see what the mechanical analog.
Yeah, absolutely. Yeah. That's an interesting direction which we are trying to explore now.
Okay. Thank you.
Yeah.
So with that, we come to the end of the session. Thanks, Krishanu, for his interesting talk and all the other speakers of the session. I hand it back to the organizers.
Hello everyone, and let's thank all the speakers and Priya for chairing this session. We are running a bit late, so and I do not see Rajdeep as yet. So is it okay if we start the next session in 5 minutes? I think that will save us some time because we'll also have to have this poster session discussion with the students end of this session. So all the students should stay around. And so I guess in 5 minutes, so what at the moment 11:35, maybe 11:40 we'll start. In interest of saving time, I would suggest the speakers of the next session to be around, so I'll add them as co-hosts so that people are ready for the talk. Is that okay? Okay, so
you want us to say okay, so then it's okay.
No, that's okay. I realized, I'm not teaching a class, so sorry. So you don't have to say okay. I was in that teaching mode. All right, so I think we'll begin in at 11:40. So the speakers of the next session, please stay around. I will just add you guys as co-hosts.
তুমি একটা কম্পিউটার সেকশনে বের করো যে ওই মেল আইডিটা অ্যাড করা আছে চেক করতে মনে হয় ওখানে ওরা গন্ডগোল করেছে মেল আইডি অ্যাড করে
No, but how he got the email? He must have gotten an email now. Without the email, how did he get the link?
He got the he's joined
Okay, Sumiran.
সেটা থাকতেই তোমরা পাঠিয়েছ
Devashish, maybe you can keep your slide share.
Yes, hi. I hope you can hear me and also see me.
Yeah, I can see you. Hi.
Okay. Great. Hi.
Okay.
Hi, Anamitra. This is Devashish. So let me share the slide so that you see it. Let me know if you can see it well and good.
Yeah, I can see your slide, Devashish.
Perfect. And if I move it, you also see the change, right?
Yes. Yes.
Okay, perfect. Then I'll just keep it
That
in
is
this.
so we'll start in about 2-3 minutes time.
Okay, good. I'll just mute myself for now, and whenever this introduces me, and I
Ritik Mandal, yeah, you just add made them just add the last question.
Ravi. Yes. Yeah. Mute.
So let's start then. Rajdeep perhaps will be a bit late. We're trying to contact him. So for now, I'll sort of take over. Welcome all. The first talk in this session will be by Debashish Banerjee, talking on quantum link models to explore novel aspects of these theories. So Debashish, the floor is yours.
Thanks a lot for the introduction, and a special thanks to the organizers for the opportunity to present my work here. So even though I'm not from the condensed matter background, much of my work in recent years have straddled topics which are of common interest, and I hope to make some of you interested as well. Right, so the talk will be in 3 parts. I will start by reminding us about the role of gauge fields in nature, both at high and at low energy, and point out where do these quantum link models fit in the game. Right? Then we will we'll examine some of these particular models and maybe one or two of the physics features associated with this model, with these models, and then I'm going to conclude by giving an outlook. Right? So as you were aware, right, so one of the very important microscopic theories, right, in our quest to understand strong interactions is a non-abelian gauge theory. It's called quantum chromodynamics. Right? So this, so the non-perturbative formulation of this theory on space-time lattice was pioneered by Ken Wilson and methods to compute physical quantities such as the masses using ab initio techniques. Right? And you have this, so this method has been pushed relentlessly to perfection to the end that you have this figure on the left-hand side with the hadron spectrum where some very minimum inputs, right, such as masses of some of the strong interacting particles, you can compute the masses of the rest of the other particles, and you have impressive agreement with experiments. Right? These are the red points with the bands. Not only that, people have actually used this method to predict new phases of matter, such as the quark-gluon plasma, and which are, you know, this is an intense experimental investigation in various parts over the world. Now, coming back to condensed matter physics, many of you are, you know, are experts in this better than I am about how the notion of emergent gauge fields, right, are crucial to describe lots of phenomena that occur in condensed matter physics. So, one of the very pedagogical examples is that of frustrated magnets, where the emergent gauge fields are essential to describe the physics associated with the degenerate ground states that happen in water ice and spin ice, for example, the pyrochlore materials. Some of these materials are expected to host these very elusive and very interesting spin liquid phases, and these phases are you know, gauge theory descriptions, as many of you know. I noticed that the phenomena here occurs at energy scales of around 10 to the power minus 10 MeV, whereas the one I was talking about in the previous slide was happening at about hundreds of MeV. Right? So where do these quantum links fit in? The quantum links fit into the game because they provide a framework for us to construct microscopic models, right, which at the same time attempts to answer or attempt to, you know, reproduce the physics at very high energies of interest to traditionally particle physics, and on the other hand, of also physics at low energies or at low temperatures, ground state physics, also of interest in condensed matter physics. Now, these models are not particularly new. They have been studied both in the particle physics communities and in the condensed matter communities by these names of the people you see in blue and red, respectively. However, you know, the studies are going more or less disjointly. It's only in the last 10 years or so that you know, one has really identified that these are really the same things that we are looking for, and this fact has been exploited in order to understand the physics of the systems better. So I think the most major achievement of the quantum link models is that they are able to realize continuous gauge symmetries with discrete quantum link operators, right? So that even when you're working with gauge fields, you can have a finite dimensional Hilbert space and locally, right, for every gauge degree of freedom. And this not only extends Wilson formulation of gauge theories, but also gives, you know, like novel physics scenarios. Okay? Not to mention the other experimental opportunities and the theoretical opportunities. This I will not go into; will take us too far away. So let's try to understand how a quantum link model is different from the standard Wilson formulation of a lattice gauge theory, right? So for this, I'll take the very canonical example of fermion, like a single component fermion, which sometimes we call staggered fermions, but it's a single component fermion coupled to an abelian gauge field in one spatial dimension, right? So you see this chain, right? And you also see there's a staggered mass term for the fermions, right? Which makes the fermion sit on this odd sides. And then you have a fermion hopping term, right? This makes the fermion hop from Y to X. Now, normally when fermion hops, it hops, but when it's coupled to a gauge field, right, you have gauge degrees of freedom which are sitting on the link, right, between this, for example, between the 5 and 6. And when I say it's a U1 quantum link model, it's a U1 gauge theory, right, Wilson, then the gauge degree of freedom is a quantum rotor, right? So, so these are angular momentum operators that you should think about, and the electric flux of this theory is associated with the LC component, right? So, in this particular figure that you see, all the gauge links are in the zero electric flux component. So what happens is that when the fermion hops, right, from this 5 to 6, the fermion can only hop, and when the hop is allowed, it will also change the state of the gauge field. So in this case, the gauge link sitting in this bond 5-6 also gets excited to the state +1 of the electric flux. Right? So this allows the interpretation of the operator U, the gauge field operator, as a raising operator of flux. So U goes to U acting on state 0 gives to state 1. U dagger is a lowering operator. 2 to 1, and so on. And obviously, because it's a quantum rotor, right, you immediately recognize that the Hilbert space locally is infinite dimensional, right? So you can use these angular momentum eigenstates, right, E to be 0, plus minus 1, plus minus 2, and so on, to label the gauge field states. And the fermions are, of course, occupied or unoccupied, the single component fermions. Now, since E and U are canonically conjugate operators, this allows, of course, they satisfy a commutation relation, as we are all familiar. So, and these are the commutation relations you have. Now, the first two of the commutation relations are very essential in the sense that they allow you to define a set of local operators, which I call G of X, and these are just the Gauss law operators. And you can show, so this is just the, you see the discrete divergence of E minus the fermion density rho of X. And you see that these operators commute with the Hamiltonian, right? So there are an extensive number of operators which commute with the Hamiltonian, and that's exactly what the gauge theory means. The theory is highly constrained, but nevertheless, it's not an integrable system, right? And so the Hilbert space is, gets divided into various super selection sectors, and so now you must specify these local values of G of X, right? which are the physical states, which is the sector that you want to look at. Right? So this is how the Wilson theory works out. Now, when you talk about quantum wave model, the only thing you do, right, is to do with the gauge field, first of all, and you replace the quantum rotor, right, by a different degree of freedom. So you see, in terms of the operator, I have not changed anything in this Hamiltonian. I have just denoted the gauge fields by operators Q and E, right? So, and in this case, in this particularly simple abelian gauge theory, I'll just tell the answer. The answer is that you use a quantum spin X. So what you do is that you have three operators. You identify the SZ component with the electric flux, and then the gauge field U and the gauge field dagger. U dagger is the raising and the lowering component of the gauge fields, right? So this identification, as you see, allows the same commutation relations as before. At least the first two are the same, and it turns out these first two components are very crucial to show that the gauge invariance works exactly as in the Wilson case, right? So this is very important. And so now you've defined your Gauss law operators in terms of these new electric fluxes, right, which are the SZ components of the quantum spins. But you have the same number of operators with the same symmetry, and they commute with the Hamiltonian. So the gauge structure of the theory is unchanged, even though the Hilbert space on which this operator acts changes, right? So this, of course, leads you to the idea that what we have done is that we have reparameterized this infinite dimensional Hilbert space in terms of a different operator, so this quantum spin operator, now with 2s plus 1 dimensional Hilbert space. And for each value of this parameter, right, you have a different theory. So if you're working with spin half, you have a 2-dimensional local Hilbert space, right? So these are the two states. If you're working with spin 1, you have a 3-dimensional Hilbert space, and so on, right? So, of course, this immediately tells you that one way, which is not, by the way, the most elegant way, one way to reach the Wilson limit for some people in the particle physics community, reaching the continuum limit is a big deal. So one way to do that would be to take increasingly large representations of S. But in many other cases, you may be very happy with taking a finite dimensional representation, and you generate these very interesting effective field theories, which describe Pennes matter systems, right? So for the rest of the talk, I'll stick with spin half representation, right, so that I make it clear right away. So now let's see what happens if you go to higher dimensions, right? So let's say you are in 2 spatial dimensions, and you know that the most important addition that you can make is to add the magnetic field term, right? So the magnetic field term is a spatial plaquette operator. And in the case of the square lattice, the simplest operator you can write down is this loop, right, which spans a 4-body term. So you have a U dagger, and the U dagger, right? And the reason why this is the simplest is because when you look at the divergence of the Gauss law, right? So divergence of the electric fields, I'm sorry, on the square lattice, right? This is the G of X. This is the operation expression that I have. So you find that the U plaquette is by far the simplest term that commutes with the Gauss. Okay? This is not the only term you can write down clearly. For example, Rockshire and Kivelson, who are exploring these models from other perspectives, they wrote this lambda term, which is the square of this fundamental plaquette term. Now, before we proceed, right? So notice that this structure of already reduces the Hilbert space quite a lot. Right? So normally you would have said, look, I have 16 such states, right, meeting at a given site. Right? But now it's no longer so. Now, because you have to maintain a Gauss law constraint, right? If you say that I don't want any charges sitting on my sites, right? And if you're working with a spin half system, like I said, in 2 dimensions, you have 4 links touching a side, right? And this means that to have charge 0 on the vertices, you have only 6 allowed configurations, right? Similarly, for charge 1, you have only 4 allowed configurations. For charge 2, it's only 1 configuration, right? So the Gauss law plays a very important role. And for example, if you're going to study the partition function or the phase diagram at finite temperatures, besides this exponential of minus beta h, you also have to take into account the Gauss law, so this projection operator, right? So what happens for this particular theory, right? I've already motivated kind of this theory. So in this theory, the Hamiltonian has 2 parts, right? You have the h of j and the h of lambda. And again, you notice that you could have had 16 terms, right? You know, okay, each link has 2 states. However, the operator, this h of j, is it's a very highly restrictive operator. It only allows 2 non-trivial states to survive. And these 2 non-trivial states have either a clockwise or an anti-clockwise flux going around the plaquette, right? So in this example, you see an anti-clockwise flux going around, which when Hj acts on it, it converts into a clockwise plaquette, right? And h of lambda, as you can imagine, it's a square of the basic flipping term. So if you have an anti-clockwise circulation, you get a clockwise and then again an anti-clockwise, right? So it remains so. So now, for example, it should become obvious that h of j and h of lambda tend to compete with each other, right? If, for example, I give you this particular state, which is in the top right, you see I have arranged the fluxes such that all the plaquettes are flippable, and then h of j comes and hits this particular plaquette, right? So what happens is that this plaquette remains flippable, but of course in the other orientation, so anti-clockwise becomes clockwise, but the neighboring plaquettes, right, have become non-flippable. This you can convince yourself easily. So this means that, the consequence of this fact is that as you look at the phase diagram as a function of lambda, you have different symmetry breaking terms. And as it turns out, when we studied with the quantum Monte Carlo algorithm, specially constructed for this purpose, already quite a while back, that you have 2 different phases, right, which are separated by a very weak first order phase transition. This is important, very weak, because we don't yet understand why it's so weak, right? So in the phase when lambda is much less than lambda c, you have a phase where all plaquettes are equally flippable, right? Whereas on another phase when lambda is greater than lambda c, you have a phase where only half of the plaquettes are flippable, but that too in a very staggered fashion, like the ones that I showed you in the shaded portions, right? So so there's some more studies regarding the weakness of the phase transition, but let me not go into that right now. But let me point out that because the translation symmetry in this model is continuously broken, right, this gives rise to novel phases which we call crystalline confinement, right? So crystalline because translation symmetry is continuously broken, and confined because we are talking about a 2+1 dimensional pure gauge theory, right? And in this gauge theory, it's confined, right? So this means that if you place a static charge and an anti-charge, by when I say static, I mean the charges cannot move; they don't have any dynamics, right? In a confined theory, you expect that there will be a tube, there will be a confining flux tube which joins the static charges, and as you pull the charges apart, right, you put in energy. You need energy to pull them apart. This is what confined means. And this is what will happen in a Wilton type theory. Now, in this theory, it shows this is a more remarkable effect. So what you see on the figure are the energy density profiles, right, on a 64x64 lattice at a very low temperature, especially for the slide A, B, and C. And for slide D, it's a situation at high temperature, energy density at high temperature. So the profile, the energy density profile, and the figure A is the case when lambda is much less than lambda c. When I told you both plaquettes are equally flippable, right? That's what gives this uniform color on the energy density, minus 0.5. But interestingly, you see that there's not one strand, but rather 4 strands, right, joining these 2 charges. And by using effective field theory methods, you can identify them with the fractional half charges, which act as domain walls between various symmetry broken phases. What's even more interesting is that the matter, the phase which lies inside these tubes, right, is the phase which is stable on the other side of the phase transition. So if you were to change your lambda to greater than lambda c, you will see that the phase which was hiding inside these strands now becomes the bulk phase, and the phase of uniformly the reddish color, which was the bulk phase, now becomes confined in the strands. And this particular figure P, right, is the situation that happens close to the phase transition. You could be very easily mistaken for thinking this almost resembles the Coulomb phase, but it turns out that it's not so. This model has a residual string tension, but it's extremely low, right, in accordance with the fact that it's a very weak first order phase transition. Now, even more interestingly, right, you can make these concepts also play a role in one of the central models of finesse metaphysics, namely this square lattice quantum diamond, right? So this model was, proposed by Anderson already much long back in the 60s and the 70s as a candidate to describe the non-Néel phases of anti-ferromagnets. And you can show there's a one-to-one mapping with the model that I described to the square lattice quantum diamond model, provided you're willing to make the connection that the Gauss law superselection sector, right, which we just spoke of vacuum charges, is now no longer vacuum, but it has a charge of +1 or -1 depending upon whether the site is even or odd. Right? So these filled red sites are charges +1, right? These filled red ones, and the empty blue ones are the charge -1. Right? And moreover, you get to see that whenever you have a flippable plaquette, right, like the example that I'm showing you here, you have a pair of parallel dimers. In this case, you have a pair of vertical dimers, which when acted upon by the flip term, it becomes a pair of horizontal dimers, right? This is exactly the flipping term, the kinetic term in the quantum diamond model that I'm sure all of you are familiar with, right? You also have to make the mapping between the electric flux and the dimer variables, but this is really trivial. So you can map the Hamiltonian and the Hilbert space of these two models in a one-by-one, in a one-to-one fashion. Now, those of you who work with or at least studied the quantum diamond model for a while, you know that there has been a lot of understanding, a lot of speculation about the failures of this model, primarily because it's kind of difficult to come up with a quantum Monte Carlo algorithm to simulate it. At least what is known is that if you make lambda very large and negative, you get into one of these columnar phases, and these columnar phases are simply classified by these stacked dimers, right? You can have the dimers which is stacked either vertically, like you have over here, or you have horizontally, like the ones the blue phase, and they can be in various positions. So there are 4 phases in all. There are 4 kinds of columnar phases you can write down. And using our Monte Carlo methods, what we were able to show that while the columnar phase is very stable, the plaquette phase essentially arises only as domain walls between the 2 columnar phases. So in this figure, which I'm trying to, of which you have a cartoon on the top, and the rest are energy density profiles, right, at certain values of lambda. So the middle one is at lambda to 0, and the last one is at lambda close to 0.9, which is very close to the Rochard-Kibelson point for those of you who know it. But even generally, I want to point out that you see that what existed as a very sharp domain wall, right, in an initial cartoon state, has now acquired a life of its own, right? Because you see that that these domain walls have become thick bands, and they form what are called the plaquette phases, right? So if you examine this carefully, you will see that you have a bunch of 4 plaquettes, one of which is the most flippable, and then you have some neighboring which are less flippable, and then a 4th one which is even less flippable. So this is what plaquette phases are. They characterize certain broken symmetries and so on. Right? So you see a very nice features of this model coming out. Now, more recently, we have been studying the effect of including fermions in this model. Right? So strictly speaking, we cannot do a quantum Monte Carlo method yet. For at least let's say we've not done it yet. Because fermions have sign problems and so on, and it's difficult to do this in 2 dimensions. So, but this is a tensor network study based on which is done on ladders which are infinite in one direction and finite in the other direction of about 4 lattice spaces wide. And you see, this is the Hamiltonian that you have this hopping term, right, as usual. It's a staggered hopping term actually, because you have this factor fxy. Then you have a mass term for the fermions, and then the usual gate splitting term. And what is rather interesting is that the mass term of the fermions provides a coupling to tune the model between the quantum link phase and the quantum dimer-like phase. Right? So if, for example, mass is large and positive, you are sitting in a quantum link-like phase, whereas if the mass is negative, you are sitting in a quantum dimer-like phase.
Hi, Devashish. So
yes.
Just to warn you, we have 4 minutes left with including everything.
Absolutely. Okay, I will stop I will just stop now. Right? So yeah, so this is this model is very interesting, and I rather in the interest of getting more questions, I will not continue too much with this. Right, so this is something under study which is almost final, and you should see this very soon. I just wanted to point out that there is a kind of a interesting spin liquid-like phase which we don't know yet. But yeah, let me not go into that, and let me just conclude. So I hope that I've given you some interesting aspects of this model, right? Both condensed matter and particle physics I didn't talk about. But let me also point out that these models have very interesting dynamical aspects, right? Some of which will be talked about in the talk on Thursday by Arnav. So yeah, with this, I'd like to thank you, and these are some of the collaborators who I've been working with in the recent years. So maybe this is a good point where I stop and take questions from you.
Hi. Thank you, Debashish, for the nice talk. So Rajdeep, in the meanwhile, is also here. So I'll transfer the session to you, Rajdeep.
Okay, thank you. Anybody? I see a lot of raised hands. So sorry for being a bit late. Diptiman has his hands raised. So Diptiman, you have a question? Diptiman, you can unmute.
No, I think Diptimanda's hand was raised from the last talk. He probably didn't put it down.
I see.
So,
I see.
yeah.
So then I'll go to Krishnendu. Krishnendu, you have a question.
Yeah. So Debashish, can you hear me?
I can hear you.
Yeah. So regarding that phase diagram, this phase diagram that you showed, just
maybe this
the previous slide. Yeah. So how robust is this spin liquid phase, and how do you? To what extent of certainty can you talk about a spin liquid here?
Yes, we cannot. Yeah, so we cannot be very certain. So let me tell you why we think something interesting is going on. So first of all, when the J term is very large, right, then this is kind of not so interesting because it's basically changing the one constraint to the other. But when J is small and M is also small, right, then it means that the fermions have a lot of chance to hop around. So it really disorders the system quite a lot. So this is the intuitive understanding that we have. And then what we do is, if we look at the correlation functions, we look at the correlation functions of the fermion number density, and we see the correlation functions of the flipped, the plaquette operators, and we clearly see that there are regimes in this, which is how we've drawn our shapes. But the correlation function seems to fall off very slowly. Right? This is an exponential. This is a log scale that we see. So we suspect that something very interesting is going on. However, it's a tensor network method with finite lattices. So it has to be a lot of
Sure.
So I have to, there are red flags there.
Sure, I understand. Thanks.
Sure.
Arnav has a question.
Yeah, Devashish, can you hear me?
Mm-hmm.
Yeah,
I
so
can,
you had a slide which was titled fractionally charged strings. Could you just go to that? Yeah, this
yes.
So are you basically looking at tube-like systems here or two-dimensional systems?
So this particular thing is for tube-like systems, but you can do the same thing in two-dimensional systems. Where
Okay. So if they're tube-like systems, then I can at least understand how morally you can get a Q equal to 1/4. But if you have a 2D system, how can you get a fractionalization here?
Yes, I didn't show that. So what happens is that if you have to look at a similar figure like this, right? So here, this is the quantum link model, and here you have these two charges, right? But they each are plus minus 2, and you get 4 strands, and you can show that each of these 4 strands have different symmetry realizations. Then couple it to your effective field theory and techniques, you identify them to be each carrying spin half. Now, in the case of quantum diamond model, this happens, this entire thing repeats itself, but there are 8 strands for charge plus minus 2. And once you start looking at these profiles carefully, you identify that there are 4 different plaquette phases through which the system goes, and each strand then carries a quarter flux.
No, I
didn't show the
understand
figure
that.
because
I understand that, but I mean in 2D, still the expectation would be that it's weakly confined and not deconfined, right? So
it is weakly confined, absolutely. So I'm not saying it's deconfined.
So why do you say that it's fractionally charged? I mean,
it's just fractionally charged because these individual fluxes, right? These flux tubes, they carry fractional charge. So as opposed to the Wilson-like theory, right? If you had a Wilson theory, you would not see these 4 things at all. You would just see one tube. Right?
No, that part I understand. Yeah, that part I understand. Okay, maybe I'll ask you for the
maybe Arnav, you guys can take it.
Sure.
Sorry. There's one question, that's the last question, and then we'll go to the next talk. So Suminan.
Hi. So I was wondering, I guess, previous slide, the cube slide. So recently there have been these quantum Monte Carlo studies by algorithm to study quantum dimer models.
Yes.
But they showed that there is a mixed phase histogram, they called it. But so your study is deep in the columnar or something like that, or what?
No, this is So I would like to point out that these studies are not very unanimous. So I am aware of the study that you're talking about, but there have also been studies by Stephen Powell and all who conclude that there is no columnar phase and they go to very low temperatures. So I'm unsure as to what to make of it. What is clear is that the quantum Monte Carlo algorithms, in the case of the quantum link model, they work perfectly. In the case of quantum diamond model, we know that there are some inefficiencies in the algorithm. Right? We've tried to address them as much as we can, but it's you have to go to humongously large lattices, and we've been to 144 square.
Okay. And do you have anything to say? Sorry, may I? I'll see just one quick thing.
Sumiran, we are quite late in time.
I'll
maybe
ask
you can take it up with Devashish one-on-one.
Perhaps we should talk later.
Thank you.
Thank you. Thanks a lot for the question.
Yeah, let's thank Devashish for this very nice talk. And let's move on to the next talk, which is by Sumiran Pujari of IIT Bombay. And he's going to tell us about stability of Coulomb phases in bilayer dimer models.
Okay, thank you. Am I audible?
Yeah.
And my mouse and screen is visible, right?
Yeah.
I hope
you want to make it a full screen, or this is the full screen?
Okay, let me try it. Is it full screen now?
Yeah.
Okay, thank you for the introduction, Rajdeep, and thank you to the organizers for giving me this chance to present some recent results. So my talk is going to be about Coulomb phase physics, which was alluded to in the previous talk sheets as well. But I'll restrict myself to the classical context, which is more related to XY model literature, if you wish. And we have found some new interesting results, which I would like to share as much as possible in this limited time. So this work, so the title, as you say, has the word bilayer. So the word bilayer leads to a stable, what is called purely dipolar Coulomb phase in 2 dimensions. So the purely dipolar I might not be able to cover and maybe comment at the end, but the stability is also an interesting feature. It was not clear whether this phase would be stable or not, and now we understand it. So I would like to share that. This work was done in collaboration with Nishita Desai, who is a postdoc at TIFR right now, and Kedar Damle at TIFR. And the work is published in PRE, and you can look for more details. So I'll focus on one specific part of the story. This is a big story. I'll focus on one part of the story which is closer to my heart. And it turns out that I had shared very preliminary version of the story a few years ago at this same forum, which actually facilitated conversations with Kedar. But now we have much more understanding of the problem. So the basic outline is I'll give a brief introduction to Coulomb phases, which was already mentioned in the previous talk, and then our problem statement in the bilayer context. And I'll give a simple description of what is this bilayer Coulomb phase in a simple-minded way. And hopefully this will reach to many of you. And then I'll go to the numerical results, and then I'll come to this issue of, after describing the phases, this issue of stability and the phase transition or crossover, and in particular, how to describe this. And with that, I'll conclude. So what are dimers? So dimers, so I'm thinking in a classical statistical physics context, it is some object on a lattice that connects to nearest neighbor lattice sites. And in dimer models, we impose this constraint that no 2 dimers can touch on a single site, as shown on the right panel. So the left panel is how it should be. They should all be distinct. So these are hard local constraints, but they lead to a lot of degeneracy in 2 dimensions. And so the number of states grows exponentially in system size. And so there's a lot of entropic freedom, and that leads to these Coulomb phase or Coulomb correlations. So these dimer models are interesting. They can be exactly solved in 2D planar graphs using some techniques, but this bilayer model is not a planar graph, and so therefore these techniques are not applicable. They are related to some interesting Ising models, which is another motivation to study dimer models. And on bipartite lattices, we expect what is called the Coulomb phase. So the Coulomb phase, the way you see is you map these timers to a configuration of lattice fluxes, so that once you do this mapping, the details are given here, but we can skip the details. These lattice fluxes then obey a hardcore divergence-free constraint on the lattice. And these arrows are called lattice fluxes. And there are other models, ICE models, which was also alluded to in the previous talk. These are a different way of obtaining the hardcore lattice divergence-free constraint. And these have some realizations in real materials, which is why these dynamo models are interesting to us. So the basic idea of the Coulomb phase is follows. So once you do the mapping on the lattice to these lattice fluxes, you coarse-grain them. And in the continuum, now you have a regular divergence constraint that is familiar to us from electrostatics. And I write down an effective lowest order effective action. And then I use techniques familiar from electrostatics to solve this statistical mechanics problem. So in 2D, I can solve this constraint, divergence constraint, using a height mapping. And in 3D, I can use the standard curl of a vector field. When you put all this together, what you find is the correlations of these lattice fluxes in momentum space have what's called a pinch point structure. So this is how it looks mathematically. And in real space, it leads to dipolar correlations. In particular, this 1 by r to the power d in d dimensions. And you also have this structure of the dipolar form. So the dimers are effectively like charged dipoles, microscopically speaking. And these pinch point structures in momentum space have been seen in experiments in I6. So I'll focus to square lattice dimer model. So this is a Monte Carlo simulation. And in a Monte Carlo simulation, this is the structure factor of the lattice fluxes measured on the lattice. And this is a particular cut. You see that pinch point structure, which is also visible here in the full two-dimensional Pilwan zone. And so this is how you can confirm it in the Monte Carlo simulation. So the purely dipolar issue that I had mentioned in the on the title slide is related to this peak that we see at pi 0 wave vector, which is related to actually columnar correlations. So in the square lattice dimer model, there are also power law columnar correlations. And in the bilayer model, it turns out they actually are not present. So this 1 by r square in 2 dimensions, you can also verify by measuring real space correlators. This is an example of that. So it turns out for square lattice dimer model, this 1 by r square dimer correlations has both a dipolar component and a columnar component. The dipolar component is due to this pinch point drop at 0, 0 wave vector. And also this peak at pi 0 also contributes to this 1 by r square. And you have to carefully separate them out in numerical simulations if you want to see them separately. So in 3 dimensions, as I mentioned, you have the 3-dimensional version of electrostatics. And then you may ask what happens if one direction is finite. Do you somehow cross over from 3 dimensions to 2 dimensions, in the sense that once you are below the length scale of the finite width, you see 2-dimensional electrostatics, and once you are above that scale, you see the 3-dimensional electrostatics. And so are these 2 different points of view? So we want to consider one extreme case where we already can see something interesting, which is I just have one particular layer. So this figure shows that just 2 layers. So I'll come to this slide. So the first point is like I have a 3-dimensional model that I constrain by unit length in one direction. But the second viewpoint would be that I have 2 square lattice dimer models. And I also allow for these vertical dimers. And now you can tune the fugacity of these vertical dimers, and you can ask, as you tune the relative fugacity of the vertical dimers and the horizontal dimers, do you get sort of different phases, or are they the same phase? And we want to understand that. So this is the model, and you tune the relative fugacities of these horizontal and vertical dimers. So here, again, we can do the electrostatic description. In the interest of time, I will skip the details. So here, as before, now since we have 2 layers, we get 2 coarse-grained lattice flux fields, P1 and P2. But because we have these vertical dimers, the vertical dimers are like charged dipole defects, just as the horizontal dimers are, we understood, were charged dipoles. Effectively, these are charged dipole defects vertically when looking from the point of view of a single layer. So they lead to 2 extra fields, rho 1 and rho 2, and then the constraint is modified. You don't have a hardcore like a divergence free constraint, but rather it's modified to have these defects in them. But the vertical dimer nature reflects as ρ1 has to equal minus ρ2. And then you play the same game and set up the field theory. And when you work out the details, what you find is that now the structure factor actually changes in a very singular way and very qualitatively different way. The intra-layer structure factor doesn't have the exact same pinch point form that we saw for a single layer, but there is this extra factor of half, and the interlayer structure factor also has this factor of half. These two, the relation between these two factor of half is a singular limit, in the sense as soon as you turn on the vertical dimer fugacity, you just go over to this. It's a singular limit. And you can also show that in real space it is 1 by r square, and the charge dipole defect correlations go as exponential minus r. So you can understand it in a slightly different way, which explains a different property of this model, which is instead of looking at the P1, P2, I can linearly combine them in this way such that P plus, P minus, such that the constraints in terms of P plus and P minus, for P plus to have a divergence free constraint as before. So this is like a Coulomb channel, if you wish. And for P minus, you have all these defects floating around. So this is kind of a capped featureless channel. And when you rewrite the action in terms of this, you get an extra factor of half. And this factor of half actually is important to the story. So please keep it in mind. And you can solve these constraints using techniques from familiar to us from electrostatics. And you can recover the phenomenology that I described here, all this phenomenology, by just doing this rewriting. And also all of the above is doable in the height model way, which I'll come to maybe later. So these alternate viewpoints are really the same thing, and they give us different ways of understanding different things. But this rewriting, this factor of half, helps us to understand one little feature, which is for the experts in the audience, one might be familiar with this inverse relation between the monomer correlations and dimer correlation power law. It is 0.5 and 2. So 1 by r square we talked about, and the monomer correlation, which are correlations of test charges in the soup of these fluctuating timers, they have a 1 by r to the square root of r. And it turns out actually monomer correlations and columnar correlations are inversely related. And due to this business of vertex terms, I'll skip the details. This equation fundamentally captures the fact that the columnar correlations go as 1 by kappa, where kappa is the stiffness to the height field fluctuations, whereas the monomer correlations goes as kappa. So this essentially leads to that inverse relation. But this factor of half, actually, because in the monomer correlator kappa enters like this, that factor of half leads to the monomer correlator being suppressed to 0.25, whereas in the monolayer it was 0.5. And you see this in numerics, which was not that easy to understand from the previous electrostatic analysis. So here I'll go through the numerical results quickly. So for low fugacities, I now see the bilayer version of the pinch point. So you see a pinch point in this cut plots at the dipolar wave vector, and the size of this pinch point drop in the interlayer and intralayer structure factor nicely reproduces this relation of half and half that I described before. So you can confirm this structure immediately as you turn on the fugacity, you see this immediately. And as I said, if you add up the two lattice flux fields, then you recover the old single layer things at the pinch point drop and vanishing structure factors. You can also verify some other predictions of the theory. And you can do a much more detailed analysis of all this on the lattice. So the previous was all field theoretic in the continuum limit, and you can derive formulas on the lattice with the lattice factors correctly account, and you can account for this theory quite nicely, turns out. And this shows the 1 by r square behavior of the bilayer Coulomb phase. At high fugacities in numerical simulations, I don't see any pinch points anymore. And so you would think that all the these vertical dimers have proliferated and they've killed the Coulomb phase correlations. And so the fitting forms of the Coulomb phase, the bilayer Coulomb phase, also don't explain the data anymore as expected. In high fugacities, everything is exponentially correlated. So remember, in the Coulomb phase, the correlator, the dimer correlator was 1 by r square form. In this phase, in the high fugacity side, it's all exponentially correlated, decaying. So it's a somewhat of a mystery what is happening as we crank up the fugacity, because all the previous arguments in some sense work for any fugacity. So what has led to this destruction of Coulomb phase? This transition from a Coulomb phase to a non-Coulomb phase, we can monitor it through different quantities. For example, the pinch point drop. So let's focus on this. This is the intra-layer pinch point drop. And you see this is the singular limit nature of this bilayer Coulomb phase. As soon as I turn on the fugacity, it goes to half the value, which is that factor of half that I pointed out. And then as you crank up the fugacity, it just goes down. But there is no order in the interlayer dimers. They are just exponentially decaying. So the interlayer dimers are not correlated at all because there is no interaction to stabilize any order between the interlayer dimers. There are other ways to quantify or characterize Coulomb phases. One is, in particular, the winding numbers. Winding numbers, if you wish, is just the net electric flux in the whole lattice. And in a Coulomb phase, because the dimers are all fluctuating all over the place, the net flux in the lattice also fluctuates. So Coulomb phase has winding number fluctuations. This is a way of implementing that. But the important thing is these winding fluctuations are also related to the stiffness kappa of the fluctuating lattice fluxes or the fluctuating height field. So we can use, we can measure this quite easily in the Monte Carlo simulations, and we can use this to extract the height field stiffness or the stiffness to characterize the theory. And if I look at winding number fluctuations, I also again see this transition behavior. At low fugacity, it extrapolates numerically to the larger sizes to a finite limit, whereas as fugacity increases, it goes to zero. Similarly, I can also look at monomer correlations that I mentioned briefly before, which is I put two test charges in this soup of dimers, and I can look at their correlations. And by the electrostatic analogy, they are essentially described by effective log potentials, the interaction energy between them, which leads to their correlations going as 1 by r to the kappa by 2 pi, as I mentioned before. And I can use the monomer correlators in Monte Carlo simulations to get an independent estimate of this height field stiffness. And it turns out these monomer correlators can be collected with very high quality in Monte Carlo simulations for some technical reasons. And so we get two independent estimates for this height field stiffness, and they should agree with each other if you are in a valid Coulomb phase, and we can do this check in our Monte Carlo simulations. On the other hand, on the high fugacity side, the monomers are not described by power laws. We sometimes say they are confined in the high fugacity phase. And so it looks like from the numerical simulations that at low fugacities, the monomers are deconfined, and as you crank up the fugacity, it gets confined. It's like a confinement deconfinement transition. So, for all practical purposes, it looks like a continuous transition. All the winding number probabilities, the histograms, they don't do anything funny. It looks like a continuous transition. And so the question was, what is the description of this transition? And so this is where collaboration with Kedar really helped us.
So,
and
Sumiran, just want to point out you have 2 more minutes, and then we have a 5-minute question answer.
Yes. Yeah. So, so this is the sort of one of the interesting pieces of this story. How to describe this transition? So from numerical simulations, we see that at low fugacities, I see all the signatures that one routinely measures in a Monte Carlo simulation of a Coulomb phase. At high fugacities, none of them are present. So how to describe this transition? So first of all, one might guess that it is probably some kind of percolation transition of the interlayer dimers. As I crank up the fugacity of the vertical dimers, they percolate through the lattice, and therefore the intra-layer dimers, the horizontal dimers, don't even get a chance to sort of flow through the lattice fluxes and establish the Coulomb correlations. But this cannot be correct because even in the high fugacity phase, the density of the vertical dimers is much less than the population threshold. There is one way, there is one theory of how to describe such transition, which is in presence of interactions. So this is again goes back to monolayer. So if you have monolayers but the dimers are now allowed to interact in this way. So if you have parallel dimers, you gain some energy. And so these has two phases. One is when there is no interaction energy, you get the Coulomb phase, the single layer, monolayer Coulomb phase. Whereas if you crank up this interaction energy, you actually get columnar order, because in this limit, we can see that the columnar order, the figures were shown by Devashish, which I should have included. They are the lowest energy configurations if this attractive interactions is cranked up to infinity. So these are two phases, and to understand, and this is a valid transition, and to understand this, we need the height model description is useful. So the height model has this height field fluctuations, or the lattice polarization fluctuation piece, but in 2 dimensions, there's this new special business of vertex terms, which relates the inverse relation between the monomer correlation and columnar correlations. So this vertex terms are needed to understand this transition properly. And it turns out that the Z4 symmetry of the columnar order, which to implement it, the height field has to satisfy, like the action has to be, should not be transformed under this transformation, leads to vertex terms, which are these cosine 2 pi ph, where p has to be multiples of 4, 8, and so on. So one can now do an RG analysis of this sine Gordon model, and at tree level already you can argue that these vertex terms are relevant when the stiffness is greater than p squared by 4, or stiffness by 2 pi is greater than p squared by 4, which explains why the zero interaction, where g is actually half, recall the power laws of 2, so that corresponds to g equals half, implies vertex terms are just a second, are irrelevant, and you get a stable Coulomb phase. And as you crank up the interactions, actually what you do is you end up tuning this g, and once the g becomes greater than p squared by 4 with p equals 4, which is the lowest order term, you transition out of the Coulomb phase into a columnar phase. This leads to a costless transition, and it's also called a roughening smoothing transition. Roughening, the Coulomb phase is like a rough phase, and the other phase is a smooth phase.
Shumiran, you are 2 minutes over, so can you try to wrap up?
Yes, yeah. So for bilayer, it turns out it is not a roughening transition. I'll skip this slide. The basic point is that the Z4 vertex terms favor anisotropy, columnar order, whereas the interlayer dimers are dipole defects. They rather favor vortices and anti-vortices pair across the in the 2 layers. And so we have to handle this effect carefully in this height model description. And the way it works out is now you have this new vertex term in the bilayer model. So in the bilayer, you have 2 height fields, H1 and H2, and you have to write down the vertex terms consistent with the symmetries of the model. And apart from the usual monolayer vertex terms, you get a new vertex term where P actually equals 1. And it turns out even at non-interacting limit, this term is marginal. And then one loop calculation shows it to be marginally relevant. So the understanding that we have now is this: a previous transition was actually a crossover, and it looks like a transition because it's a really long crossover at this non-interacting limit. And so this is what we established numerically, that this is indeed the case. This was close to my heart, but I'll skip it, and I'll come to my conclusions. So basically, the main conclusion is that this bilayer Coulomb phase.
Shumiran, maybe you can just leave the conclusion slides, and we can get to the questions. We are already 3-4 minutes over. Is that okay with you?
Yeah, that's fine with me. I'll just flash the next slide. There's lots more to the story than what I covered. So I just took the full phase diagram. I just covered the small piece, and I didn't cover the purely dipolar nature, which relates because of the fact that this bilayer model has one Coulomb channel and one cap channel, and how it connects to the columnar correlations. If you work out, you see that the power law columnar order is absent. There are other perspectives which are covered in the paper, so if you're interested, you can have a look. Here is my thank you slide.
Thanks, Shumiran. So questions, we can take probably a couple of questions very quick. Anybody has questions, please raise their hands. Okay. Okay.
Let me just ask
yeah.
a very quick question.
Yeah.
So,
Go ahead.
Sumilin, regarding this phase diagram, I assume that now you're disordering this problem. Is that correct? Or
disordering in the sense of
sorry. So, what is this new axis in this phase diagram?
this axis?
Oh, this is the fugacity,
This
right?
is the fugacity of the particle diagram.
Right, right. So, why does this have this extended KT region here?
This one?
Yeah, this gray shaded thing. Why is it extended?
So at zero interaction, as I described, it was actually never a transition, but a crossover, right? What happens is that when you turn on repulsive intra-layer interactions, you tune the height field stiffness such that actually the new vertex term, the cosine 2 pi h1 minus h2 actually becomes irrelevant. So then the bilayer Coulomb phase actually becomes a stable phase. And then when you crank up the fugacity, you again start tuning that stiffness such that eventually the vertex term becomes relevant and you transition out of it. So that's what gives you this transition.
I see.
You see
Okay,
that?
good. Now, now I understand your new axis. You have put some interacting terms in your diamond. Good,
Yes.
Yeah,
So
got
to
it.
really expose the full structure, you have to put some interactions.
Yeah, got it. Whereas your rest of the slides were just the pure diamond.
Yes.
Okay.
Oh, okay. Let's thank Sumiran and let us go on for the next talk. The next talk is by Ritvik. He is going to Ritvik Mandal, who is going to tell us about ultra-fast terahertz nutation dynamics in magnets. Ritvik, after you. Yeah. Go ahead.
Okay, can you hear me now?
Yeah, we can hear you. Yeah, you can.
Okay. Oops, sorry. I did share a different screen. I think that one. Oops. Okay. Thank you, the organizers, for initiating this great platform. So I'll talk about from a different perspective of what has been told until now. So I'll talk about terahertz nutation dynamics in magnets, which is really ultra-fast process. So, normally this spin dynamics is described by phenomenological lambda ellipsis Gilbert equation, which was proposed long back, so 1935, for example, you see here, and which has basically two terms. So you have one term that basically describes the spin precision of the spins around the effective field, and the second term basically leads to transverse damping, basically the energy dissipation of the system, of the spin system, let's say. Now, this has been described, or this has been used to describe several experimental features also in the ultra-fast timescales. For example, you see here one of the earlier experiment where they saw that if you come with a laser pulse, femtosecond laser pulse of 100 femtosecond pulse width, then actually you can demagnetize a nickel sample up to 50% within few hundreds of femtosecond. So then also you can also describe using that equation, for example, you can also describe a switching in ferrimagnetic system, which is here iron and gadolinium, and then shown that basically iron goes from +1 towards -1 upon irradiation of a laser pulse of few hundreds of femtosecond. Also, gadolinium goes from -1 towards +1. And actually, we actually use this equation in computers, hard drives nowadays, in a magnetic data storage devices. But actually, if you go on, then you find that actually LHC spin dynamics is fundamentally wrong. And even though we use it for, let's say, last 50, 60 years, but this is completely wrong. And actually, Gilbert, this last person here, this Gilbert, when he derived this Gilbert damping, he also said that, this is his paper, he said that one can show that the inertial tensor must have a single non-zero term corresponding to the rotational inertia of the rotation about the principal axis. What he meant is that basically when I have a rigid body system, then of course I have the inertia in the system, which is a matrix now. Now, he said that, of course, you have to put I1 to 0, I2 to 0, and having only this single non-zero term that is basically I3. And if you keep this term, then, of course, the angular momentum in the system, which is basically proportional to the magnetic moment. Now he also said that I was unable to conceive a physical object with an inertial tensor of this kind. That means that you do not get any physical object for which you have I1 to 0, I2 to 0, and having only third term, single non-zero term, which exists. So then what is the solution? The solution is basically you have to take the full matrix here, which is I1, I2, and I3. And then if you do that and you do the same derivation here, then you find out that L is not proportional to the M, but you have an extra term, which is here depends on I1. So now you see that if I1 is 0, then of course you get back to that proportionality. And this is exactly the reason why this spin mutation basically originates. And then, of course, the magnetic moment in the dynamics, the magnetic moment not only rotates around the effective field, now the magnetic moment will start rotating around the angular momentum because their direction are not the same. And this basically leads to the spin mutation. I will not go into the details, but then actually additionally you get another term here, which is basically a second order dynamics, so D2M dt2. Now that basically introduces, as I said, this basically introduces the spin moment. Initially, it rotates around the angular momentum, and then basically the spin mutation dies out, and then you get this precision and damping as you had before. So the question is, can we derive such equation from fundamental principles? So we started actually asking this question ourselves, and then we started from a Dirac equation, which is now excited by laser pulse that takes into account with this magnetic vector potential, which is A. Now we are interested in of course in particles, so because this contains particle, antiparticles, and so on. But we are interested in the particles, so then we decouple, and then we get basically within electrons theory, then we get normal spin orbit coupling, which has basically this formula, and this can be shown that this leads to basically normal L dot S spin orbit coupling that we use in electronic structure theory. But also we get this higher order spin orbit coupling. So which is, you see here, this is 1 over c squared, this spin orbit coupling, with this higher order spin orbit coupling as 1 over c power 4. And also here there is this time dependency which is involved here. Now, the way we derive the spin dynamics is basically using those Hamiltonians that I showed, and then of course using this Heisenberg equation of motion, that you take the commutator between the spin angular momentum with the Hamiltonian, and then you can derive the dynamics. So if you do that, then basically the Zeeman-like spin field coupling that derives the spin precision, as was also done before. But what is interesting that we found is that you can actually, from the spin orbit coupling Hamiltonian, we can derive this normal Gilbert damping. And now the more important thing is the damping is a tensor, even though originally was proposed by Landau and Lipschitz, this damping is a scalar quantity. We also found that this higher order relativistic spin orbit coupling, this derives basically the spin mutation, which has basically this form, and notably also this inertia is a tensor. But from the dimension analysis, one can show that this alpha has dimensionless, alpha is a dimensionless quantity, but this eta has a dimension of time now, which has been suggested to be at the ultra fast time scales around let's say femtosecond to picosecond time scales. So now we have this equation of motion. Of course, we can derive this from Dirac theory, and let's look at what it gives in the linear response theory. So if we do the linear response theory of this equation, this inertial Landau-Lipschitz Gilbert equation, then actually we can derive the susceptibility, which has this form, which is rather straightforward, I would say. And then we can calculate the dissipated power using this this formula. And if we do that, then we see this, let's say, this ferromagnetic resonance spectrum. And in the ferromagnetic resonance spectrum, what we see that this orange curve, this shows without the inertial term. That means you have only this ferromagnetic resonance around certain gigahertz, let's say 50, 60 gigahertz or so, a peak, of course. But then if you include this inertial term, which has 100 femtosecond time scale, then you see another peak, which is appearing at a higher frequency. So that is basically a terahertz frequency. So that is another resonance peak, which appears only purely due to the nutation here. Now the question is why this is negative sign, negative frequency. The question is that if the answer is that if I calculate now the eigenmodes of these two FMR and also the nutation resonance, then what I see that the FMR has basically rotates anti-clockwise direction, which is normal. But then if I do it the same for nutation resonance, then I see that this basically rotates clockwise. So they have basically different or opposite handedness. With that, we can also calculate, this was actually experimentally found recently in this year. In this work, for example, they found even that we have this FMR, but also we have this nutation resonance. And they found this nutation resonance somehow occurs around 0.4 terahertz to 0.6 terahertz in these two sublattice magnets, this cobalt iron boron. But recently also what they found is the same group actually, they post another paper on arXiv, and then they also found that this FCC cobalt and BCC cobalt, they even found not only these nutation resonances, which is higher frequencies like terahertz, but also they found higher harmonics of nutations, for example. So this is, let's say, 2 times of this nutation resonance and maybe around 3 times, and so on. But this has not been confirmed yet. Okay, so what can we do with this spin nutation? So we can actually inject spin current from a ferromagnet to adjacent metal. So using this formula, so we can calculate this spin current, which basically is injected from a ferromagnet. And indeed, of course, at the gigahertz frequency, you see, of course, this injection of spin current to the adjacent metal, but also what you see on top of that, actually a negative spin current that appears at the nutation resonance. And why this is negative? Because of course the rotational sense in two resonances are completely opposite to each other. But what does it mean physically? What is negative? That means that it's something like a spin Hall effect in a sense, but at different frequencies. So in the spin Hall effect, of course, the spin up goes, let's say, one direction, and spin down goes in the other direction. But here exactly the similar things happen. So the spins at the precision frequency goes in one direction, and the spins at the nutation frequency goes in the other direction. But of course the frequencies are different here. So we can calculate the ratios between those two currents, and you can, as you would expect, that with the nutation, so the time scales with this eta parameter, then actually it increases linearly more or less, but at the higher eta, this actually diverges from the linearity. We can do the same in antiferromagnet, but it is something interesting in antiferromagnet. What happens in antiferromagnet, of course, you get two precision frequencies, which are basically opposite because you have two sublattices in antiferromagnet. So you get two precision frequencies which are basically suppressed, because you see here the y-axis, which is basically suppressed because this is 0.02, but the nutation frequencies, these are exchange enhanced. So so then actually one has better one can see these nutation resonance better detectable in the antiferromagnetic systems, let's say.
So Ritik, you have 1.5 minutes roughly, just to remind you. Yeah. Okay.
Yes, sure. So and if I look at the eigenmodes again in the antiferromagnet, then of course I know that I see that for the precision modes, of course they are almost anti-parallel to each other. So this theta and theta b, they are basically equal. However, in the nutation modes, this effectively behaves as a ferromagnet. So you have this theta a, which is much larger than theta b. So one sublattice is dominant in nutation resonance. So that's why that is actually visible in this spin current calculation. For example, you see that these intra-sublattice terms, these are intra-sublattice terms at the precision, they change sign for cross-sublattice terms, but this nutation, they do not change sign. So when you calculate the total injected spin current, then you see that they basically cancel with each other. However, this nutation spin currents, they adds up and giving rise to the fact that the nutation current is really exchange enhanced. With that, the take-home message would be that this LHC spin dynamics is completely wrong at ultra-fast timescales. However, you need to take into, when you take into account this nutation dynamics, then you see additional nutation resonance that is occurred at terahertz frequencies, and these are basically ultra-fast processes. And also this nutation resonance should be better predictable in the experiments. And finally, I would also like to say that the spin nutation mediated spin switching is yet to be explored. So this I would like to thank you for your attention.
Thank you, Ritwik. Any questions from the audience? I actually had a question for you. So when you are deriving this equation from the Dirac equation, let's say, is this that this is some sort of perturbative expansion, that if I really go to even ultra-fast timescales, there'll be higher order terms, or is it like this is all, you cannot have anything else?
No, you can have, actually you can have. So if you go to, I mean, you can expand it, I don't know, as long as you want, let's say. But the thing is that in the regime that we are in, let's say for this low energy regime, of course, the dominant term would be this spin orbit coupling. Of course, that's the first order correction, let's say, and this is basically the second order correction. Of course, this higher order spin orbit coupling, this is second order correction. You can have more. Actually, we are also trying to find out whether this higher order experimental observations, let's say this one's here, as I said. So this higher order, I don't know, the spin nucleation resonances, whether they can be explained by even more higher order terms. So we are currently investigating on that.
Looking at the higher order perturbations. Okay. Okay. Any other questions from anybody else? Yes, there's a question. Go ahead.
Hi Ritik, this is Ashish. It's a nice talk. So I have some naive question about this antiferrometric that one. Is it possible that there is a realization of kind of transient ferromagnetic state because of the nutation? Nutation dynamics, for example, since your two sublattices behave differently, so can I expect a transient ferromagnetic or ferromagnetic state?
I would say so. I mean, if you look at, if you look at individual modes, for example, if you just look at the nutation modes, individual mode, then actually you would see that this is a kind of transient ferrimagnetic, or let's say ferromagnetic mode. Only for nutation modes, but of course you are not, I mean, as an overall system, you are not looking at only nutation modes, you are also at precision mode. So then I don't know. But if you look at individual modes, of course, this is a ferrimagnetic like effective ferrimagnetic like mode.
Okay. No, is it possible to freeze them there and then just freeze those basically rotational mode, and then I can have a ferromagnetic state?
No, I don't think so. I don't think you can freeze. I don't know. I don't think you can freeze that.
Okay.
Okay, let's thank Ritik for a very nice talk. And the next speaker is Shantanu Pal from SN Bose Center in Kolkata. And he'll be talking about quantum phases of ferromagnetically coupled Shastri-Sutherland model.
Hi, am I audible?
Yeah.
Thanking the organizer for giving me the chance to present my work. So I will present on quantum phases of ferromagnetically coupled Shastri-Sutherland lattice. This work has been done with the collaboration with Melissa Chatterjee and Professor Noranjan Kumar at SN Bose. So Shastri-Sutherland lattice is a cornerstone model where you have a exact solution on some parameter regime, which also an interesting model in the sense of exactly solvable in the condensed matter context. And recent study further reveal interesting phases in the Shastri-Sutherland lattice in the antiferromagnetic coupling limit. As you can see here, that there is a dimer phase, and in the strong coupling limit there is a null phase, and in between there is a placket singlet state. So in the placket singlet state, you have a dimer in a square where you don't have the diagonal bond. And very recently, there is another interesting phases has been proposed that there is a possibilities of deconfined quantum critical phase in between the placket singlet and the nil state. So there is another interesting, very recent work where people basically predicted and spin liquid state, have the spin liquid state in between the placket singlet and antiferromagnetic phase. So antiferromagnetic model itself very interesting, and day by day it's revealing new phases. So, but there is another limit where you have considered such a Sutherland model in its ferromagnetic coupling, where in the X and Y direction you have antiferromagnetic and the diagonal bond is ferromagnetic. So this model has been less studied, but it's equally interesting because still you have frustration and it's revealed many interesting phases, quantum phases. For example, our DMRG analysis reveals 6 interesting phases, including 2 stipe phase, 2 spiral, 1 ferromagnetic, and 1 perfect dimer phase. So this model has been drawn recent attention due to the material, recent found material, where initially this material, which is copper CuCl LaNbO7, predicted as a square with frustration J1 J2 interaction, but recent another experiment suggested that this material properly modeled with the ferromagnetic Sutherland lattice. Also DFT studies predicting the same. So here you can see that the red bond is the antiferromagnetic diagonal bond, and the blue and the cyan color has the ferromagnetic coupling. And this material, it's a Jx, Jy almost equal, and belong to the dimer phase. So I'll discuss later. So, and another interesting recent theoretical study based on exerdiagonalization and Swinger boson Millfield theory predicted on the same model interesting phases, where they have performed exerdiagonalization on small cluster up to 24 lattice site, where they were able to predict ferromagnetic and dimer and stipe phase, but it was inefficient to predict any kind of spiral phase. And the magnetic phase is equally interesting in that particular coupling regime. There is a sudden basically jump in the magnetization from 0 to saturation magnetization. There is another regime where the magnetization process is it's continuous. So, but there is no plateau in the antiferromagnetic, in the ferromagnetic coupling cases. There is half magnetization plateau if you have in the antiferromagnetic regime. Swinger boson Millfield study, on the other hand, predicted spiral phases. So then we have basically performed a DMRG study to unified small cluster DD and the Millfield kind of theory. So, and we have found 6 phases, as I already pointed out, but the phase diagram is quite different from the Millfield analysis. As you can see here, the dimer singlet phase is burdened in the Millfield theory, but whereas a perfect dimer singlet line we have found, and this perfect dimer line extended up to the ferromagnetic regime, and there are stipe phase and the spiral phase. So this phase diagram we have constructed from the ground state energy analysis and the spin-spin correlation. So as you can see here, in the ground state energy, so there is a sharp transition between the ferromagnetic and the spiral phase. So this is first order kind of phase transition. On the other hand, other phase transition is continuous. So there is no sharp signature of phase transition. So we have calculated spin correlation along different direction to confirm different quantum phases in that particular model. So if you see the correlation calculation on the x direction, and if you are state, let's say, parameter regime in the stipe phase phi 0, So then along the x direction, the spin correlation shows. So there is a sign change in the consecutive side. So which basically antiferromagnetic spin correlation, but along the y direction, you have just a ferromagnetic spin configuration. So which represents a spin configuration with wave vector pi0, which is the type pi0 phase. So one pose can have another type phase if you are sitting in that particular parameter region. So whenever you have the Jx and Jy exactly equal, the perfect diagonal line, as I already mentioned, so the spin correlation along the x direction and y direction is exactly 0, whereas the spin correlation in the diagonal bond only exactly equals to minus 0.25, where it's forming exact dimer state in the diagonal bond. Just away from the perfect diagonal line, if you calculate the spin correlation, then there is a finite correlation apart from the diagonal bond. So that's why we call this line as a perfect dimer phase. So in the spiral regime, if you calculate the spin correlation, then the pink line is showing that the spin correlation is changing its signs, which is not commensurate with the lattice. So there is a incommensuration happening in the spin correlation. So a non-collinear spiral phase sets in that particular parameter region. And the spin correlation along in the ferromagnetic state is showing that the spin correlation along all direction, x direction and y direction, it sets in a ferromagnetic spin correlation. We further calculated pitch angle in different regime of the parameter space, where we can see there is a variation of the pitch angle in the x spiral regime from 0 to pi, and ultimately enter into a type phase which have a pitch angle of pi. So we have compared the pitch angle with the classical analysis, where the trend of the pitch angle variation with respect to the parameter is showing the same, but the classical value of the spin pitch angle is very small here. So with that, the ground state energy calculation and the spin correlation confirms our different phases, and basically explain the possible existence of a non-collinear spin state in the ferromagnetically coupled Sasti-Southerton lattice. So with that, I would like to conclude that our YIMQCMT analysis on ferromagnetically coupled Sasti-Southerton lattice has revealed a plethora of phase triagram, which is mostly short range in correlation. That's why YIMQCMT analysis work well in that particular system. And we have confirmed the existence of the non-collinear spiral phase in that particular model. So the finite field behavior of the magnet and the magnetic state of that particular model is yet to understand. With that, I would like to thanks everyone.
Thank you, Shantanu. So any questions from anyone?
Can I ask a question?
Yeah, go ahead.
Shantanu, so yeah, this is Ravi Chandra from NICER.
Hi.
So this perfect dimer phase that you had, I mean, if I understand from your phase diagram correctly, it seems to be nearly perfectly the Jx equal to Jy line. Is that correct?
Yeah, that is correct. So whenever you have Jx equals to Jy and Jx Jy is less than J, the diagonal coupling, you would expect a perfect diagonal line. Yeah.
And I mean, is it possible to, did you check the energies to see if there are some simple numbers or something, and if the state can actually be written down explicitly? Because I mean, it is, since it is exactly all through, maybe it is some simple state that you can.
Yeah. I got your point. Yeah, indeed, you can write down a state where this is combination of just a dimer on the diagonal bond. Yeah, it is kind of the dimer phase in the antiferromagnetic cases. Whenever you have Jx equals to Jy, you would expect that kind of exert state. Yeah.
Okay.
Okay. Any other questions? If not, let's thank Shantanu for a very nice talk. And that brings us to the end of this session. So I would hand it over back to the hosts if they have any announcements and how they want to.
So let me thank Rajdeep for chairing this session and the speakers for nice talks. So as we wrote in the email, at the moment, the next session, of course, will start at 2 p.m. And the poster presenters should stick around if there are questions as to how posters are to be presented through this Frames platform. So I think others, the moderators of the poster session should also stay around. Others, I mean, I know people want to go for lunch. If people who are going to visit the posters want to stick around, can stick around. I mean, just to familiarize with the thing. But in my personal view, it's a bit too much as a platform for poster presentation. But we are testing it for the first time, so let's see how it goes. Yeah, so that's the announcement. So Rajdeep, thanks once more for sharing the session.
Thank
you.
you.
We'll see you in the talk as well. Okay, sure. So, bye. So students, you guys are around. So anybody, so Rijit, I can see, I see the video is from that thing, not from our laptops, I see.
Which one?
No, the video, our video is the full room, not the, that's okay, it doesn't matter.
Yeah, we can see the full room and both of you.
Yeah, the point is, this is a sort of a big screen thing that is projecting the talk. So I think there is one way to get the camera out, but at the moment I don't know how to do it. All right, so how many are the students there? So a couple of things. A few of you are a bit apprehensive about splitting the poster into 4 pieces or 9 pieces of slides. So that was just a suggestion. The point is, whichever way you present, when somebody views your poster on a computer screen and the poster is of the dimension of a large poster intended for printing, so you have 2 options: either make it slide by slide and go over them. That is what we suggested. The other option is, of course, you can scroll up and down in your poster as you have designed it in its logical flow and present it. Okay. So that's just about the poster, the visual representation of the poster. With regards to the audio and interaction with the audience of the poster. So the audience generally will are supposed to be close to the poster boards, because there is this thing called spatial audio in this particular software, which becomes louder as you come close to a poster, because otherwise different posters with different people talking to the presenters would create a mess. So you generally have to navigate how to navigate. Those instructions were sent in a PDF file. It's like, think of it as a video game, and you go back and forward on the landscape. You should pan around and look for the poster boards and go towards the poster. By default, the presenter's microphone will be on, and if you speak, there should be a two-way channel of communication that should automatically be open. And for the students who are presenting, use the share screen option and not the video cam option. Okay, so that's another aspect of the thing. Yeah, so I think that's about Kush. Was there anything else? This is about it, right? Okay, so any of you guys have questions, you can go ahead and ask.
But are they going to check with
Anna, tomorrow we are going to check, right, with the posters.
No, the poster session is tomorrow.
Yeah. So, I mean, anything to test before that? Because your email, I think, mentioned something.
No, there's no testing. We are supposed to discuss this. Many of the students have tested it
Okay.
yesterday.
Okay.
I mean, because this is an open platform. Once you have the link, so that is the thing. So the file that is shared with everyone yesterday, with the Excel file with the links. If anyone wants to see a particular poster, you should just click on the poster, and it will directly jump to that particular poster. You move around, go close to the poster, and you can interact with that particular poster. So a few students had some issues that we sort of worked out with the Frames team yesterday. So far as we had asked for issues, apart from 2-3 people who had issues that we already clarified, we didn't find any issues. One thing that I also forgot to mention, that each session, each poster, so we five or six of them of the posters are grouped into something called a room, and each room has a moderator. A moderator is a faculty member. So Arijit here is one of them, and there are other moderators as well. So I mean, if there is some instruction from the moderator, please pay attention to that. Okay, so I think from my side, that was the input that I wanted to give. Students, if you have any apprehension, please one by one person. So let's say Anand Vijay, I see you have unmuted, so go ahead.
Yeah, so hi, sir. Yeah, so I have this, just want to clarify that we have to put the poster for the full 2 hours, and then in each room, everybody
just like a poster.
just like a poster session, offline.
Yeah, so you basically have to wait around. As people come in, they will ask for the 2 hours. Yes, that's correct.
Yeah, okay, fine. Thank you.
Sure.
Anybody else? As a moderator, I mean, should I be in the one session? I mean, like I have the 5 students. Should I be?
Yeah, so you will. So you are the moderator of one particular room. Okay, and in that particular room, basically there are 5 posters, I believe.
Yes.
So so the 5 poster presenters have a member level permission, which means that they can see the share screen option, and they can share their screen. The other members who will just see the poster will be anonymous people who will come in and out. If there are issues, I mean, so I think a general standing instruction that all of the moderators should tell people to keep the megaphone switched off. The megaphone is switched off. Microphone is for two-way communication. So if you are near a poster and somebody is talking to a student, this we have checked yesterday with 4 or 5 people here that it is working. Then it will work. The megaphone is for you as the moderator to make announcements. If you speak on the megaphone, so all the poster presenters, all the people attending all the posters will simultaneously hear it. Okay, so no presenter should keep it on, because then his voice will be sort of interfering with everybody else.
Yes.
Okay, so that is the other thing.
And the moderator also switch off the megaphone, right? At least, or switch.
So the moderator, if he or she wants to make some announcements,
then
that is fine.
Yeah.
Okay, so
like for example, if I want to hear any of the poster, so among the 5, so I'll be able to hear them automatically. Like when
no, so moderators will come. You still have to go navigate towards. So you go from that go to button, or you click the link in the list. So you, so like everybody else, even the moderator, if he wants to see a particular poster, you basically have to use the link, or within your room you can use the go to button.
I can use the go to button.
Yeah, but the go to button is a bit. I mean, because it does not allow you to change rooms. That's why we didn't. That's why I gave the list to everyone, so that from that link you can go to any room regardless by clicking the links.
Okay.
Okay.
Nimitra.
Ravi. Go ahead.
checking that was done both by the students who are presenting, and you also allowed some visitors to come and see. Both aspects have been checked.
Yeah. So yeah. So yesterday we tested the entire afternoon. We kind of tested this. So we got the students here to act as presenters, visitors of the poster.
So as moderators, we only have to add. I mean, only the presenters have to be added as members. Anybody with the link.
No, you don't. At the moment, you don't have to do anything. I mean, until unless there is some issue, you just have to be present in your room. That's all.
Okay.
Anything that if there isn't some untoward issue, then maybe we'll get in touch with this Ravneet person from Friends. Other than that, yeah, it's like if somebody suddenly switches on the micro megaphone, so maybe you can mute people, etc. The similar kind of things we have in Zoom as a host.
The person from Frames is the same person for all the frames, or is it different people? It's a single person, right?
The technical person, yes, one person.
One person. Okay. Okay.
One person. Yeah. I mean, see, I am not a session chair, but all of this is through my email ID. So if there is any issue, I will make this Ravneet as the sort of one of the admins in all the sessions, so that if there is a technical issue, she can handle it in real time.
Okay. Thanks.
Yeah. So that is what it is. So students, anything else? Anybody? There is a raised hand by somebody.
Sir, I do have one question. How do you can move? Hello?
How do you? Go ahead.
Am I audible?
Yeah.
How we can move around different rooms? Can you repeat?
Different rooms. Yeah. So I mean, the simplest way is to use the file that we have shared yesterday, with the Excel file with all the names and the links. You must have received it.
Yeah, we have received it. So for every room we have separate rooms, right?
Sorry?
Is there
I couldn't
any
hear
general? Is there any general?
No, that
link?
is the general. No, that is the general way. You have to click on the link and do it.
Okay, sure.
You just click on the link, it will directly jump to. Otherwise, you have to manually change rooms by hand. That kind of is harder. I mean, you have to change things in the address bar. It's much easier to just click on the link because it will amount to the same thing.
Okay, thank you.
Okay. So, Ramita, I see a raised hand.
Yeah. Can you hear me?
Yeah, go ahead. It's a bit, there is an echo, but go.
What I wanted to ask is that how do we understand if there is a visitor in our room and we are supposed to present to the visitor?
No, so if somebody comes close to your poster, okay, so they will ask you to present. They'll ask you what you have done in the poster. They might have a look at the poster because
they can share the poster first, right?
No. So yeah, so the posters you have to share and keep it on for somebody is asking. You keep the poster shared at all times for the entire 2 hours. If somebody, no, I think what she's asking is, I mean, she's not able to, as a presenter, she's not able to see the person who is coming to the poster. So how does she know that she's supposed to present or not? The point is, anybody who comes to the poster, because it's a virtual poster, will probably introduce themselves and ask you to present what you have done. Okay, it's not like people won't. I mean, because everyone, I mean, it's difficult for you to see somebody approaching because in the VR. Okay, so that you don't worry about it. Before the poster session, we will make this announcement that if somebody wants to interact, they should first speak up because the presenter would not know otherwise.
Yeah, I mean, the person who wants to view the poster, once they click on the go to with a particular name and get to the poster, and if they use their microphone, they'll probably be audible only to that particular poster.
Yeah, but they still have to speak, right? Otherwise, the presenter would not know. I mean, somebody can just look at this poster and decide not to ask a question. That is also possible. But if they want to ask a question, etc., then you should, I mean, they should sort of initiate the conversation.
Yeah.
Okay. Anybody else? Is there another raised hand? No, that's Ramita. Who else? Okay, a lot of people are here, but yeah. So if there is any lingering last minute questions. Okay, so if not, then we can close the session now. Anyway, we have to go for lunch and to come back by 2. So okay, so again, so tomorrow in the morning we will again tell all the sort of people who we are going to visit the posters about how to do it in briefly. So as students, don't worry about people not you not knowing that somebody is coming to a poster. We'll make sure that that bit works. And in case in the session, say let's say while the session is going on, you have an issue. Then you should just write your information, write the issue in the chat box. So this is a point I wanted to talk to the moderators about. So suppose somebody faces an issue. So I think the simplest thing they can do is just write in the chat box that will be visible to you as the moderator.
Right.
Yeah, because otherwise, see, if they use the megaphone, then it sort of creates a
superposition.
So I think it's if any of you have an issue while presenting, then you should simply write a chat message. The chat message is chat box is on the I believe the left top corner of the screen. So it should be visible to the moderator, and we will take actions accordingly. Okay. Okay then. So present well, and I hope you have a good poster session. All right. So people can log off for now. We'll meet at 2. Okay. Thanks. Okay.
We had other issues, and that's what we'll talk about briefly. So we are going to also show you our theory of the non-local conductance using the Kitaev chain. And we're going to consider 2 of these setups, one with disorder and one without disorder, and one with disorder where the potential kind of changes at the edges of the interface. So using our formalism, now you can show that the non-local conductance is related to the current operator, which now has 2 other processes. Earlier, you had only the enrave process at the contact. Now you have the crossed enrave process. You have the enrave and the crossed enrave process, and also a direct process, D. Direct is just electrons zipping through or holes zipping through. The standard transmission you have studied in quantum transport. Now, if you do some manipulation, you will get that the conductance, the LL is a local conductance and LR is a non-local conductance. Interestingly, the non-local conductance has a difference between the direct component and the crossed enrave component, which means it can become 0 at a phase transition that we are going to talk about. And that is the origin of the closing of the non-local conductance gap. And what we showed is that we are able to see that the local and the non-local kind of close you see this is the gap closing, and this is the topological regime. As you can see, the 2e square by h happens to the left. You can see the white bright. And the non-local also closes at the local, because we are talking about a pristine nanowire. Now, if you go to a disordered system, we clearly see that the local and the non-local do not close at the same point. And the non-local is a better indicator of the topological phase transition. As you can see, that due to the disorder, there are zero modes close to the origin. I'm sorry, zero energies, and they are all showing as if they are Majorana modes. But this one is showing a more reliable indicator. However, as the experiments noted, as the size of the nanowire decreases, as we saw, even the non-local starts to fail because the gap of the non-local also closes earlier to the phase transition happening. So the field is in a bit of a quagmire about how and when this kind of a thing can happen. And there are several causes through which the non-local or the local conductance spectroscopy will fail to detect the actual Majorana zero modes. So with this, I'm going to introduce a new idea we have been working on, which is called the von Neumann entanglement entropy, which is based on some of the works of Hatsugai. So whenever you have disorder or without disorder, you can characterize the end modes or the bulk edge correspondence using an entanglement entropy concept. And that's the idea. So when you have a system, it's basically A plus B, right? You want to partition it in whichever space, real space, imaginary space, sorry, momentum space. So in general, you have, if the states are entangled, that means A and B are somehow coupled, like for example, you have a bulk edge correspondence. Then what you see as a density matrix in the full space, if you go down to the reduced, you will see a mixed state. And that's the idea of von Neumann entropy in general, okay? Now you can apply it to topological systems by taking the correlator average and seeing how the correlator average, when you take a truncated correlator matrix, you want to see if it's coupled to the B part. And that's one indicates whether the topology exists between the edge states and the bulk edge correspondence. So when we form the correlator matrix and find its eigenstates, we can write the entanglement entropy or the topological von Neumann entropy using this simple formula based on the values of the eigenvalues of the spectrum. So one of the things we can show is that the topological entanglement entropy, for instance, it peaks at the phase transition and it clearly drops down to zero in the trivial phase. In the topological phase, it reaches a peak or it has some value and then it falls down, right? So this we are using as an indicator, and we could clearly show, for instance, this is a work in progress, that when the actual phase transition happens, the topological von Neumann entropy starts to drop down. And this is with disorder, right? So this provides a nice numerical technique to see whether the topological phase transition is happening or not. And this is a work in progress, and this is the present situation we are in terms of understanding our understanding of detecting the Majorana zero modes. So I'll try to summarize at this stage. So in order to detect Majorana zero modes, we only have the spectroscopic techniques, which is based on conductance spectroscopy. The conductance spectroscopy, theoretically, we evaluate based on the local and the non-local spectroscopy. And we have these expressions, and the non-local is a promising thing. The fact that the direct and cross-standard processes are a negating sign, they actually become zero and they close their gap and open up again. And that's the indicator of the topological phase transition. So basically, the status of the field now is there are many issues regarding false positives. The local conductance is prone to many such false positives, but the non-local conductance can possibly lead to a conclusive sightings, but there is no conclusive experiments yet. Non-local, and we are suggesting possible clues from entropic arguments, and possibly entropy could be related to other concepts that include thermoelectrics and various signatures. So with this, I'd like to kind of quickly go through some of our works. We are also doing serious nanowire device modeling, the Rashba nanowire, which is slightly different from the Kitar model, but can be done easily with our numerical techniques. And one of the important things is when you model the nanowire, you see what is called the Majorana zero mode oscillations. And as the length increases, the oscillation kind of goes away.
You have only 2 minutes.
Yes. And then we have also quite worked on the surface confinement of the nanowires.
and the fact that of introducing disorder and phase breaking into this system in great detail. And so these are some of our works you can note down on this. And of course, we have a lot of works on how to introduce dephasing into the system, especially the momentum relaxation. And one of the important things we notice is that the Majorana zero mode nature does not change due to dephasing, although the conductance signature does. So yeah, so with this, I will end my talk and give credits to various people who have been involved in the funding agencies. I have collaborated some of these projects with both IQC Waterloo and Regensburg, Germany. And these are all my students who have spearheaded some of these works. Some of them are already not around, but we do have a couple who are working with us now. And it's very good to see that the undergrads have, in IIT Bombay, have spearheaded my entire Majorana efforts here. And Dr. Adip Agarwala from ICTS has also been involved with us working on entanglement, entropy, and other concepts. So with this, I'd end my talk, and thank you very much.
Thank you for a nice talk. Now, talk is open for questions. Question, comments?
There are a few who have raised their hand.
I can't see any of those.
Okay, can I go ahead and ask a
Please
question?
go ahead. Please go ahead.
Yeah. Hi, Bhaskaran. Very nice
Hello.
talk.
Thank you.
Yeah.
Who's? Hello, Diptiman.
Diptiman, yeah. Right.
Yes, sir. Hi.
So, can you say a bit more about how we can use entropy to figure out the presence of Majaranas? I didn't quite get.
So this is a work in progress. So this is the von Neumann entropy introduced by Ryu and Hatsugai. So the bulk edge correspondence can be connected to the von Neumann entropy. So what happens is you can partition the system, like let's say you just split it into two, right? The non-local correlations exist. So even if you take the reduced density matrix, calculated via the correlators and not the higher order correlators. We are assuming the Wick's theorem at this level, right?
Okay.
And then we are using the, just the 2-point correlators and their eigenvalues to detect the presence of these modes. I'm sorry, to detect the phase transition. So if you can see in the pristine case, it precisely peaks at 2 log 2, and then it drops down. And we can we showed in this, we have a lecture series we put on archive, where we showed this for the SSH chain.
Okay.
And we applied this to the Majorana, to the Kitaev model, where the ground state, you have to calculate it carefully with the ground state and various things.
Okay. So that's okay. So I guess I wanted to know how you would actually measure this von Neumann entropy.
Yes, that's my width exactly. That I do not know of a signature. That's why I kind of saw in the conclusion. Yes, possibly there is a way to do it. I've been thinking if there's any conductance signature. My answer is I don't think so.
Okay.
Possibly there can be a thermopower signature, because finally thermopower is related to close to the ground state entropy, right?
Right.
But it's not the von Neumann entropy, but there may be a ground state SLR, non-local or local thermopower. I'm just thinking on those lines.
Okay.
But
okay, fine.
It's not clear to me. It's just a theoretical tool yet.
Okay. Yeah. Okay. Thanks.
Thank you.
Can I?
Yeah, please.
So I had a question. You mentioned about this direct and indirect gap, right? Did you mean, so you had this proposal where the indirect gap was showing the topological transition in presence of disorder, but the direct was not. You made a statement like that. Is that correct? Am I understanding it correctly?
Yeah. So this is whatever I was saying is about the direct and non-direct, not direct. The word is local and non-local.
Local and non-local, right. So I think what I had in mind is, right. So I think if I remember correctly, unless you have the tails of the two Majorana overlapping, you really do not get cross-standard reflection, which basically means that if your chain is long enough, you're not going to get this signature at all. Right?
No, it happens. It is there. We do have a cross-standard even for longer chains.
No, but did you look at the tail of the Majorana wave function? Because if the Majorana wave function do not overlap, I think it will not happen. It's just a theoretical statement that this process will not take place.
Yeah, possible.
Unless your Majorana tails overlap.
Yeah, possibly the direct and cross-standard become zero. Yeah.
Yes, absolutely. That's what happens. So now my question is, if you are in the long chain limit, does it mean that you will not be able to, this is not a diagnostic, should I say that, or you need something else?
So, but it's interesting. Thank you for this question. I need to think and get back. But the proposal that was made by Akhmerov, right, back in 2018, was done in the long chain limit. And this is what was the conclusive signal they showed, that it exactly crosses and at little higher voltages, it becomes negative and positive. This is a negative differential conductance. But exactly at the point of crossing, this conductance becomes zero, which could either mean that the direct and cross rendezvous are both becoming zero, or they exactly cancel out due to the fact that they are highly non-local. Now, this is where my understanding is, but I'd like to.
Maybe I'll communicate with. The other question
yes,
is,
we should talk about it.
Yeah.
Yeah.
The other question is regarding what Diptiman asked, and I'm also curious. I remember there was this work by Levitov et al. Long ago, I think 2008 or 9, where they connected essentially, if you quench a quantum Hall point contact, then they could show that the noise correlation actually is related to the entanglement entropy.
That's
so
fantastic.
It will be very curious if, in general, one would not be able to connect this to transport, but I think if you quench it and then look at the noise, the AC noise, not the DC noise, then probably there are correlations which we can tell you about.
Thank you for this suggestion. I'm
it's
noting
like
it
saying
down.
that you have a connected system and you suddenly disconnect it, then it has information about the entanglement entropy in terms of fluctuations. Yeah.
Very good. Very good.
Okay.
Thank you. I haven't thought about it.
I
want to note down. Yeah.
Oh, thank you.
Hello, sir. I have one question regarding the entropy. When you say that the entropy, there is a peak for this transition non-trivial to trivial.
Yes.
So I want to ask that of whether it's any of the non-trivial cases or it matters, because there are many pairing where it differs when you're taking the non-trivial cases. Because you're saying the cross and rift thing, so that will vary for different to different pairing symmetry. So I'm asking that when you are calculating this Van Neumann entropy for the non-trivial, means the phase transition, so will it vary for will it depend on the pairing potential with the different pairing symmetries, or what, for the non-trivial cases, like the topological cases?
Yes, actually, to my knowledge, again, we are just about a few months investigating this. Thank you for the question. In our knowledge, the bulk boundary correspondence itself can be related to the von Neumann entropy. It simply means that you, regardless of the interior aspects of the Hamiltonian, all I'm saying, all Hatsugai was saying that, look, there's a Berry phase, and in fact, there is a Jacques phase associated with the 1D system, right? And in fact, for a discrete system, regardless of, you can use something called the twist operator to get it, okay? Even without getting into the integrals and all. So that is related to the entanglement entropy, was something shown by Ryo and Hatsugai, this paper, please note down. So what they're saying is to partition the system somehow, the non-local correlations denoting the edge state should kind of stand out, because you take a partitioned correlator matrix, 2-point correlators. That's the logic.
Okay, so irrespective of the pairing potential of the unconventional means non-trivial or trivial superconductors,
it should work.
Means you can distinguish the phase transition.
I think so.
Okay, so thank you. Let's thank the speaker for nice talk. Our next speaker is Swagatam Nayak from Nizer Bhubaneswar, and he is going to talk about pairing symmetries. Okay. Pairing symmetries in G-man coupled extended attractive Hubbard model. Swagatam, please go ahead.
Hello.
Yeah, we can hear you.
Yeah. Good afternoon, everyone. So this is Swagatam. Currently, I'm working as a postdoctoral fellow at Nizer Bhubaneswar. So today I'm going to talk about superconducting pairing symmetries in a G-man coupled extended attractive Hubbard model. So this work was done with Dr. Sanjeev Kumar and Navketan Batra. Currently, Navketan is a doctoral student at the Brown University, and Dr. Kumar is a faculty at IIT Mohali. So recently, this work was accepted by scientific reports. So yeah, so let's start with the pairing symmetry. So understanding the pairing symmetry of a superconductor is crucial to gain insight to the pairing mechanism behind the superconductivity. And this is very relevant to understand the nature of different unconventional superconductors discovered in past few decades. So theoretically, the information of the pairing symmetry is encoded in the entity called the gap function or the pairing function. The general form of the pairing function looks like this. So the pairing function of the system with spatial, orbital, and spin degrees of freedom. So it can be expressed as a product of momentum space, orbital space, and spin space-based function. So here psi is the coefficient. This one is the coefficient which decides the specific form of pairing. Now, because of the antisymmetry of the wave function, the pairing function holds this character. And now, for a single orbital case, which is of our interest, the pairing function or the gap function takes this familiar matrix form. And although it's easier to define the pairing symmetry theoretically, determining the pairing symmetry of a superconductor with experimental probes is not a simple task. So there's a series of experimental probes which are used to confirm the pairing symmetry of superconductor. So these are one of those. So, but again, the cumulative result is important to decide the pairing symmetry. So I would like to mention an article by Peter Hirschfeld, and so it discusses the possibility of different pairing symmetries in iron-based superconductors. So the general consensus is that the iron-based superconductors are singlet superconductors with the possibility of S-wave and D-wave pairing that's also of different kind. So in these superconductors, interaction can be actually tuned by pressure, doping, and disorder, and the system is quite sensitive to that. So you can see here by these, by the picture presented here. So these are the possible symmetries present, can be present in the system with S plus minus and F and D type superconductors. Now, depending on the which system parameters, they can choose, the system can choose to be in one of the symmetries. So, so the pairing mechanism and the pairing symmetry depend on these factors. So other than this, there are also studies confirming the presence of triplet and mixed parity pairing symmetries. So our goal is to find an effective model which allows the possibility of multiple pairing symmetries. So these are some references. So first two includes the review of this pairing symmetry, and these two are related to the pairing symmetries in the cuplets and the triplet from ESA to ARISO. Yeah. So following our goal, so we start with a model which is an attractive, extended attractive Howard model. So the model has an on-site attraction and intersite attraction. The on-site attraction can give rise to the on-site conventional S-wave character, where the intersite attraction can give rise to different pairing symmetries that we will show. So we define the model on a square lattice, and we follow a BDG mean field method. So we take our Hamiltonian, these are the parameters that we have, we decouple it in pairing channel, and then we use the translation invariance of the pairing correlations and project the system into a Fourier space, and then we diagonalize using the Bogdanov transformation to get some pairing correlations, which we call the deltas, and we do it self-consistently to ultimately calculate the final converged gap function. So with that gap function, we decode some information using this transformation. So this character kind of decide the spin information of the order parameter actually, and these are some information which encodes the spatial information of the order parameter. We will be using these two things in our results, and for this particular talk, we'll stick to the order parameter defined by the singlet and triplet D naught and D. So D naught actually represents the singlet one, and D represents the triplet one, and we summed over the Bridge zone to get a finite order parameter. So yeah, So going to the results. So yeah, so we'll start with the ground state phase diagram. So to do that, as we said earlier, our order parameter, we define our order parameter is like delta singlet phase and delta triplet phase. So when one of these is, so if delta ST is finite, then it means that there's a single component to it. Similarly, if delta TP is finite, there's a triplet component to it. If both are finite, then it would only mean that there's a mixed parity phase. So following that, we plot our order parameter versus density, and the colors, the red corresponds to the singlet order parameter, and the green corresponds to the triplet, and the blue corresponds to the mixed parity. So we see, for different values of intersite attraction. So for this result, we kept the on-site attraction to be T. And for the intersite attraction, which actually, as I said earlier, gives rise to this different pairing symmetries. So we varied V to be 0.4, 1.6, and kept on increasing. And this way we can see how the different orders survive in different doping regions. So following this, this leads to us the ground state phase diagram. We draw a V in phase diagram where we can see most of the region is occupied by the singlet phase, and there's a small slice of triplet phase near the quarter filling and near the half filling, and beyond particular strength of intersite attraction, the mixed parity phase actually means the game. Yeah, so doing that. So then what we do was that, remember in our model, we have also included a magnetic field. So we incorporate a magnetic field which is in plane, so that we don't have to worry about the orbital component of the it. So it's then so this is the V in phase diagram we got for the zero field. So then we'd like to see what if we switch on the Zeeman field, the in-plane magnetic field, and what happens to the V in phase diagram. So we can see there's a particular region below around V is equal to 1. This is the non-superconducting region appears, and then the slice which we found at the B0, it gets kind of broadened, and the triplet state occupies huge space here. Although MP, which is a mixed parity, and the singlet phase remains on the half fill region, and the singlet phase remains on the low density region. And we also find a region of phase separation. And yeah, so with that, we also draw a B in phase diagram to exactly. So the B in phase diagram is drawn, taken from this slice of the V in phase diagram, where we take this slice and as if we include a third axis, which is B, and then we plot the phase diagram. So we can see that if the magnetic field is increased quite a bit, then the whole phase diagram is dominated by the triplet phase. And in our other characterizing results, we found that this triplet phase is actually of the ESP type and beyond a certain point of B. And but at the B0, it retains both the phases, three of the phases, the singlet, mixed parity, and the triple phase. Yeah. So these are the main results. And now that we have this phase diagrams, different phases in this phase diagrams, we
Swagatam, you have 3 minutes.
Okay, so we try to plot the gas structure at the different Fermi surfaces. Now that you remember that we included an in-plane magnetic field, so a magnetic field which kind of splits the non-interacting spectrum, and it creates to two different Fermi surfaces that corresponds to spin up and spin down. So here what we see, let me first tell you that the red one corresponds to magnetic field 0. The magenta corresponds to B is equal to 0.12 T, and the cyan corresponds to 0.60. So the cyan corresponds to a high magnetic field, and this is a moderate magnetic field, magenta. And the red one is the zero magnetic field. So we tried to, and the C and F are the Fermi surfaces drawn for these magnetic field values. This one is for the upspin and this one is for the downspin. So we can see at the B is equal to 0, both upspin and downspin, the red one, they are the same if you look at the scale. But if we increase the magnetic field, it changes the value. The sign is different. So now what we do, we so as if there are two superconducting gaps corresponding to two different pseudo spins. So we plot that. So this is gap 1, this is gap 2, and we plot this gap 1 and gap 2 at the Fermi surface, at the up Fermi surface, and we do the same here for the down Fermi surfaces. And the different colors represent the different magnetic field. What happens to the gap structure, to the different magnetic field. So we can see that at B is equal to 0, there's a D wave character to the Fermi surface, sorry, the one of the gaps. In fact, both of the gaps has a D wave character. Basically, it will be the same because there's a degeneracy in there. When we switch on the B, now that the degeneracy is lifted, so we get a different shape of the two different gaps out of the two different zero spins. And when magnetic field is quite strong, one of the gap becomes isotropic while the other retains the character, which is a chiral P wave. So that can be seen that when we calculate the gaps involve the expression of linear combination of different multiple symmetries. So when the magnetic field strength is quite high, one of the contribution gets cancelled so that we get an isotropic gap. So that's the story for the gap structure. And we have so to do now I'll summarize the thing. So we find the extended retractive Hubble model as an effective model to describe superconducting orders in multiple pairing symmetries. And we see an interplay of singlet, triplet, and mixed parity superconducting phases driven by doping and the Zeeman field. We study the gap structure to reveal the nature of the superconducting order furthermore. With increasing Zeeman field, the system collapses to more stable ESP triplet superconducting order. And we see the presence of TRS broken, that is time reversal symmetry broken, that I have not mentioned, I will show you one. Time reversal symmetry broken, non-unitary superconducting phases too. And there's a transition from unitary to non-unitary superconducting phase tuned by doping. So, I will, regarding the time reversal symmetry, I will mention this phase. So there's an extra plot I have.
You have to wrap up. You are already exceeded the time.
That is all actually. So I just wanted to mention that we calculate the non-unitary amount of non-unitary and the time reversal is broken or not. So this cyan is time reversal preserved superconducting phase, and this is breaking superconducting phase, time reversal symmetry breaking phase. So I just wanted to, that will be all. These are some references which you can follow. And so
okay, thank you. Thank you. Now, question, comments? Rajdeep?
Yeah, very nice talk, Swagatam. I was just, I had a couple of questions for you, I guess. One was that all your studies seem to be at a case where the nearest neighbor coupling interaction V is much larger, or all the interesting phases seem to be in V much larger than the local pairing attractive interaction. So you are having V equal to 2T and
exactly. So
is that a reasonable thing for pnictides or anything else?
No, so I mentioned first I should say that I mentioned the idea of that article by Peter Hirschfeld of the iron superconductors, but this model that I have shown is the idea was to take the different mixed parity phases. So there's a short time, so I didn't have much to. So the idea was to find with the play with this possible different multiple order superconductors. where they can compete with each other. And so I'm clearly saying this model is not like for the hierarchical vectors.
I understand. And
Yeah.
the other question, short question was, have you looked for the fact that, when you put magnetic fields, you can have phase separation, or have you only looked for uniform solutions?
No, we get a phase separated solution here.
You
So
do get a phase
you
separation.
did it.
But I see. Okay. Sure.
Yeah.
Thank you.
Oh, actually, I can show you this thing captures the phase separation, this plot.
Thanks.
Yeah.
Subro.
Hi. So all these things are on square lattice, right?
Yes.
So maybe you can. So your triplet superconductor doesn't break any lattice symmetry. So that's one question. And the other question is that, do you understand why the triplet superconductor shows up, or any kind of understanding why the triplet superconductor shows up at zero magnetic field near this n equal to 0.5? Why is it favored in that region? So these are the two questions.
Okay, so I will answer the second question first. So maybe you were asking why we are getting at this triplet as quarter phase.
If you go to your zero magnetic field phase diagram,
this contains the zero magnetic. Yeah. So I mean, this is this, but that's actually we'll have the same taken from this. So anyway, so actually the way I understand is that the study is energetically driven. So we let the phases compete, and somehow it finds the minimum energy because this is an energy minimization we have used using self-resistancy. But other than that, we tried to see what happens to the Fermi surface when we tune the doping, and whether there's a relation to that. But actually, we couldn't find a proper, parallel between these two. That when we tune the doping, what happens to the Fermi surface, is that responsible for this thing happening? So we couldn't find an exact parallel. Probably, I don't know. In terms of using the GL theory, group theoretical approaches and all, there could be some symmetry arguments. So basically, I don't have an honest answer for this.
That's fine. That sounds very interesting, though.
Yeah. So,
okay.
Yeah.
Any other question? Okay, so I'll ask last question. I mean, can you tell us that what is the length scale, superconducting length scale you have in large V limit?
Okay. Length scale means coherence length you are asking about.
Coherence length, yeah. I mean, if you have calculated pair correlation, you might be seeing that.
Actually, I did this a while back and I forgot. This coherence length actually I've calculated. So right now I don't remember, but it would be.
Okay, that's fine. That's fine.
It would be on the smaller limit probably, because its strength is quite strong.
Okay. Yeah. Yeah. Okay. So let's thank the speaker for nice talk.
Thank you.
Yeah. So our next speaker is Archana Misra from Police Academy of Science, and she is going to talk about Siva Rushniov qubits.
Thank you. And can you see my screen? Hello?
Your voice is breaking. Can you please?
Can you hear me? Hello?
Yeah, we can hear you.
Okay. So this. Okay. Good afternoon, and thank you very much for the opportunity to present my work here. So I'll be talking on a novel qubit which we have proposed based on the Yusheva-Rusinov states, the Yusheva-Rusinov qubit. And this work is an archive and is under publication in PRX Quantum. So this work is done in collaboration with Mircea Trif and Timo Hayat from MacTub, Poland, and Aalto University, Finland, and Pascal Simon from France. Before going into the details, I would first give an overview of my talk. So Majorana zero modes are promising candidates for topological quantum computation, but coherently manipulating them is still a distant goal. And in this roadmap towards topological quantum computation, we put the first step by proposing a new type of qubit based on the U-Shiva-Rusnov states. Basically, they are the bound state that emerge within the superconducting gap due to the coupling of the magnetic impurities with the superconductor. So we call it as the U-Shiva-Rusnov qubit or YSI qubit. And we basically harness the dynamics of this magnetic impurities to control and read out the qubit states. So why the YSI states are interesting? As in the previous talk by Professor Bhaskaran, he very nicely explained one way of seeing Majorana zero modes through the proximity effect of superconductor and Rathbun nanowire. There is another viable setup where we consider a chain of magnetic impurities on superconductor, which is a viable setup for topological superconductivity. So when we consider a chain of magnetic impurities, the YSI state from this magnetic impurities, they hybridize to form YSI band, and they can effectively act as a p wave superconductor, which can be driven to under certain regime to topological superconductivity, hosting Majorana zero modes at the end of the chain. And this was experimentally first seen by this group, where they considered a chain of iron atoms on lead superconductor. And by studying the differential conductance at the end of the chain and shown by this red curve, and at the middle of the chain shown by this blue curve, they see that there is a zero bias peak at the end of the chain, which is absent at the middle of the chain. And also from the differential conductance map as a function of energy, they see the differential conductance will be peaking at the end of the chain at zero energy. All of this, which gives the evidence which suggests that the Majorana zero modes exist at the end of the chain. And with final resolution experiments, with the advancement and experiments, people are becoming more and more thinking that Majorana zero modes can be found in these systems. Another advancement in this field was given by this Wiesenberger group, where they did the atom by atom fabrication of the magnetic. And this is a big advancement because this can help in tuning the atoms and also can help in creating complex arrangements and also manipulate the Majorana edge modes. And there also they showed that there is a prominent peak at the end of the chain when the length of the chain is above a critical length, so which is around 12 iron atoms. And this is again suggesting that Majorana zero modes might exist at the end of the magnetic chain on the superconductor. So now that we have a hope that we can find Majorana zero modes, the next goal will be how to use it in topological quantum computation. But that is still a distant, that is an ambitious but distant goal, because till now, no quantum coherent degree of freedom has yet been associated in this system. And so far, as Professor Bhaskaran has also mentioned, that so far the signature is only the peaks in the differential conductance, and we need new methods to scrutinize this Majorana fermions. And for that, we need to first find some quantum coherent degree of freedom in these Shiba states. And we put the first step by showing a two-level system emerging from the quantum system corresponding to the Shiba state pertaining from the two magnetic impurities on the superconductor. And we name it as the YSI qubit. And so now our aim is to build this YSI qubit. Sorry, that occurs a mirror. Okay. Yeah. So single impurity is not enough, because that will give just one single Shiba state, and we need at least two Shiba states to form a qubit. So the basic unit will be two magnetic impurities on the superconductor, which is the Shiba dimer. And this is similar to its close relative, the Andrew qubits, which is formed from the Andrew bound states, where the even parity states from the spin qubit states. So this is basically the schematic picture of our system, where the Shiba dimer is placed on the superconductor, SWF superconductor, and they are separated by distance r. And the coupling of this magnetic impurities to the superconductor leads to a double well potential. And the asymmetry in the double well potential is because of the difference in the coupling of these magnetic impurities to the superconductor. And the tunneling, HT is the tunneling Hamiltonian between the Shiba state localized to each of these magnetic impurities. So for each parity, we will have a parity state. For each parity, we will have a pair of in-gap states. And we consider the odd parity in-gap states to form the qubit states. And we consider this blue spin as the test spin, which is allowed to process, which is driven resonantly with the qubit splitting. It can be used for the manipulation purpose. While the red spin, we consider it as the target spin, which is driven off resonantly and can be used for the readout purpose. And the crux of the qubit, this YZ qubit, is that the dynamics of this magnetic impurities, it biases the double well potential, which is analogous to the voltage bias in double quantum dot. And then because of this precision of the magnetic impurities, there is a shift in the frequency, the renormalized frequency, renormalized resonant frequency, and that is a probe to the occupation, the Shiba occupancy. And this is analogous to the quantum non-demolition readout in the cavity QET setups. So this is the Hamiltonian that describes our system. H0 is the BTG Hamiltonian of the SWF superconductor, and the coupling of the magnetic impurities to the superconductor is given by this H impurity. And our goal is to find the effective two-level qubit Hamiltonian, which the recipe is basically to project this Hamiltonian to the in-gap states under the because we consider the coupling of the magnetic impurities to the superconductor strong enough such that the in-gap states are close to the Fermi level and away from the bulk states. So we can project the Hamiltonian to these in-gap states. And then here I show the single particle energy spectrum and the many body energy spectrum. And as I mentioned, we consider the odd parity states to form the qubit states. So, sorry, when the coupling strength is same for the two magnetic impurities, then we have a degeneracy at theta equal to pi. And this is because of the reflection symmetry. But as the coupling strength is different, as we increase the difference between the coupling strength, then we find the energy spectrum to be weakly dependent on theta. And the qubit Hamiltonian can be written in this form, where the qubit splitting is given here. Where the qubit splitting contains two terms. One is the difference in the coupling strength of the two magnetic impurities to the superconductor here. And then the other term is dependent on the tunneling Hamiltonian, tunneling term. So if the delta alpha is much greater than TH, then the qubit basis will be basically the left-right Shiba states. And if delta alpha is much less than TH, then the qubit basis will be the symmetric and antisymmetric superposition of these states. So now that we have established the qubit Hamiltonian, we would like to see how to read out this qubit state. And that is achieved through the dynamics of the magnetic impurities. So in our previous work, we had shown that if we consider a single precessing magnetic impurity on the SWF superconductor, then there is a torque acting back on the impurity because of the Shiba electrons in the superconductor. And that torque is a universal torque type of SWF superconductor we are considering. It depends only on the precession frequency of the magnetic impurity and the occupancy of the Shiba state. And this has also a geometrical interpretation where it is connected to the radial Berry curvature from the Shiba state. And thus, this torque, it can normalize the resonant frequency, and we can probe the Shiba occupancy through a non-invasive technique like FMR method. So this is the story for a single precessing impurity. Now, if we have two magnetic impurities, the source of there are two sources of torque. One is so for the readout purpose, we start with both the spins aligned parallelly. And then we allow the target spin to align slightly away from the z-axis and then precess. So because of the precision, we have the dynamic curve, which is related to the very curvature. And then because of this misalignment between the two spins, we have a static torque also. So we plot this static and dynamic torque as a function of delta alpha here for each of the qubit state. And the because the torque is different for each of the qubit state, it renormalizes the resonant frequency differently. And this difference in the resonant frequency between the two qubit state, that can be measured and is the proof for the readout of the qubit state. So what is a good qubit regime where we should work? So the good qubit regime is that the qubit should be insensitive to fluctuation, and that is when the dynamic torque should be dominant, and because it will make the qubit more robust. And then the difference in the frequency, we should be able to resolve the resonant frequencies. So basically delta gamma, omega should be greater than 0.1 gigahertz following this paper. And we see that this gray portion is the regime where the qubit can operate very nicely, and where the frequency resolution can also be achieved. And the measurement can be done by the ST laser technique.
Archana, you have 4 minutes, less than 4 minutes.
Okay, I'll finish it. So next step is how to perform coherent manipulation of the qubit. So for the coherent manipulation, again, the spin dynamics leads the role for the coherent rotation of the qubit. And because of the dynamics, the qubit Hamiltonian becomes time dependent. And this time dependent beta, so sigma here is basically in the qubit basis. And beta z term, it basically shifts the potential well, while the beta x and beta y term, they are responsible for the coherent rotation of the qubit. So for the coherent manipulation, we start with the antiparallel alignment of the two spins, and that is because in this antiparallel alignment, Rabi time period and Rabi frequency are well within the experimentally measurable regime. And this is not this alignment is not alien, because it has also been reported in the experiments where references are given here. So the time evolution operator can be written in this form, and under a sequence of pulse. So basically, if we start with both the spins aligned parallelly, we give a adiabatic theta pulse. Adiabatic in the sense that this time t is much greater than the time corresponding to the qubit splitting. So this theta pulse, it basically makes the both the spin align antiparallelly, and then we allow the test spin to align slightly away from the antiparallel alignment, recess, and come back to the antiparallel alignment through this spiral pulse. And then we bring back it to parallel position for the readout purpose. And under this sequence of pulse, we see a perfect Rabi oscillation between the two qubit states. So I will give the numbers in a bit. So we need the coherence time to be much less than the decoherence time, so that we can manipulate the qubit. So for that, we need to calculate the decoherence time also. And the decoherence of the qubit has many sources, like the quasi-particle positioning, phonon, and spin fluctuation. But in the antiparallel alignment, the only source, the main source, is basically the spin fluctuations. So basically, what the spin dynamics, which is responsible for the coherent manipulation, is also cause of decoherence. And by considering the Landau-Lifshitz-Gilbert equation in the presence of stochastic field, we can evaluate for the classical spin, we can evaluate the correlators for the stochastic field and the noise correlators for the magnetization. And from that, we can evaluate the relaxation time. Sorry that there is some problem in the slide. I'll just check. Okay.
You have to wrap up. Your time is over, actually.
Yeah. I'll just wrap up. I'm just almost at the end.
You're exceeding the time, actually.
Sorry. So maybe I'm not able to show the. show the estimates. Somehow the slide is not showing. So estimates are basically the Rabi oscillation around 8.55 nanoseconds, and the relaxation time is around 7 microseconds. And so we can see almost 800 Rabi oscillations. And just to show the importance of ISR qubit, while it can be used for, it may be used for quantum, but more importantly, it can be integrated with the Majorana zero modes at the end of the Shiba chain to form a hybrid qubit, and can be implemented for universal quantum gates. And this is easily achievable on superconductor. To summarize, we have shown a novel YSR qubit which can be encoded in Shiba dimers, and whose readout and control can be done through the dynamics of the impurities. And this qubit is robust for a wide range of experimental parameters. And some future prospects are that we can extend it to Shiba chain and Shiba island. And this dynamics of the magnetic impurities may be used for the manipulation and detection of the Majorana edge modes, where they can have their fingerprints in the STM ESR signal. And then also the microscopics of the hybrid qubit is interesting to see how we can implement the universal quantum computation. And for some more realistic approach, we have to include the spin orbit coupling, anisotropies, etc. So with that, I would like to thank you.
Okay, thank you. Question, comments? Please go ahead. Any question?
Okay.
So I'll ask.
Yeah. Okay, Manu, please go ahead. I
No, please go ahead. Surinder, please go ahead.
In the previous slide, you made a mention about this universal.
Yeah.
Universal.
Yes, there is some problem in my slide. Sorry, not even. Yes.
Where is that? Yeah. You said universal quantum computation is possible. Of course, with Majorana, it is not possible. We know that.
Yes,
why
yes.
are you making this claim that with YSR plus this Majorana, it will make? Can you make a short comment on it? Why are you making this claim?
Yes. So with Majorana, yes, obviously it's not possible. But there has been recent proposal that with spin qubit integrated with this Majorana qubit, so hybrid qubit consisting of the spin qubit from the quantum dots and Majorana qubit, that can be used as hybrid qubit, where they have shown that even the gate can be achieved. So basically, they swap the Majorana qubit state to the spin qubit, and then after performing the gate operation, this back to the Majorana qubit. So that is proposed for the spin qubit, but because this wire qubit is more natural in the superconductor, so we believe that the YSR qubit and Majorana qubit hybrid can also be used for universal quantum computing, and this is something which we are planning to.
Okay. Is there a thank you for the answer? Is there a reference to this? Where this has been shown that spin
Yes,
plus Majorana? This is the reference. Okay, fine.
This is the reference. Yes.
Okay. Thank you.
Okay, so I mean, let's thank the speaker. Let's thank all three speakers at this end of the session, and thank you very much, all speakers. And now over to organizers.
Hi everyone. Thank you, Manu, for chairing the session and speakers. So the next session maybe we'll start. We're running a bit late, but it's also a last session, so we may start in 5 minutes time. So it's 3:12, maybe in 3 minutes. Let's just start at 3:15. So I request Saurabh, who will chair the session, Saurabh Ghosh.
Yes.
Maybe.
Yes,
Yeah.
I'm here.
So I'll make you. Hi. So I will make you a co-host. Just a second.
But I'll not record the meeting. I'll just chair the session.
Yeah, sure. Okay. Yeah. And Amrita. So
Yeah, I am here.
Yeah, I'll make all the speakers co-host in a go.
Hi.
Shurabda, can you see my screen?
Yeah.
Yeah, I'm just looking for Shashwat. I saw him here.
I think he's in the meeting.
He was there. I probably yes. The rest of the speakers, Amrita, Mukul, and Navneet, I have made them co-hosts. So maybe we will start in a minute, and if when Shashwata joins in, I'll make him a co-host.
Hi, is it okay if I just quickly check my presentation?
Yeah, I'll unshare.
Thanks.
Yeah, sure.
So it's visible, right?
Yeah, it's visible. Yeah.
Okay, thanks.
Can I also quickly check? This is Mukul here. Hi, Anamitra.
Please go ahead. So Mukul, sorry, we couldn't upload your title, so I have mentioned it to the session chair. He will read it out.
Oh, okay, no problem. No problem.
Hello, Mukulda. Good to hear your voice.
Oh, yeah. Hi, how are you?
You didn't. I mean, you are still behind the cloud, but we can hear your voice. So.
Okay, so
Mukul's title was tight binding approximation. Mukul, you can hear me, right?
How are you?
Hey man, how are you?
No, I have this. You can take
I'm sure. Yeah. I think it's okay.
So, Saurav, I'll sort of leave the floor to you. You can take over from now.
Okay, so Amita, you can share again your screen.
Just sharing.
Tanmay, you said something.
Yes. He's saying something tight binding.
No, I said Mukul's title read to me like tight binding approximation.
Okay, TBA. Okay. Okay, so I welcome you all to the last session of this conference, the first day, last session. So we have 4 invited speakers in this session. So we have Dr. Amrita Bhattacharya from IIT Bombay, Dr. Mukul Kabir from IISER Pune, Dr. Shashwata Bhattacharya from IIT Delhi, and Dr. Navneet K. Ravichandran from IIT Bangalore. Our first speaker is Dr. Amrita Bhattacharya. She is now an associate professor in the Department of Metallurgical Engineering and Material Science, IIT Bombay. And she will be talking regarding combining statistical learning with first principles to analyze the charge and heat transport in thermoelectric materials. So you're going to hear a wonderful talk on thermoelectric materials. I know Amrita personally, and I know how wonderful she talks about her research. So with that, I request Amrita to start her lecture. Amrita, stage is yours.
Yeah, thank you, Shurabda. So our association really goes long back. So we started in the same lab.
So, and I thank thank the organizers for inviting me in here. So this is the second time I'm presenting in this particular young investigator meeting. So I hope I'm loud enough. So this is going to be a little bit different talk from what you have been hearing. So this, mostly because this is mostly application of quantum mechanical methods. So I will go ahead. So we work in different areas. So not only thermoelectrics, but different areas like defect in semiconductors, spintronic materials. But we are going to focus on this particular problem, which is thermoelectric materials, where the charge and heat transport play a very major role. And this is the work that I have been doing for the last 4 years after joining IIT Bombay. So I will go ahead. So thermoelectrics are materials that can convert a temperature difference into useful voltage. However, the efficiency is not very great. The reason is the presence of this term ZT, which limits the thermoelectric efficiency. Here I have plotted the thermoelectric efficiency of a tentative material as a function of ZT. And you can see that in order to derive anything meaningful, you need to go like beyond 4 of ZT, and which is not very trivial, not for any material. That is because in this ZT, all the microscopic transport coefficient, the electrical as well as thermal, play major role. And all these electrical ones, the S, the sigma, which is the Seebeck, the electrical conductivity due to electrons, and electrical conductivity, so the thermal conductivity due to electrons, all these are related to each other. So you cannot optimize them separately. So only thing that you can to some extent play with is this kph independently, and you can try to tune the other 3 parameters somehow dependently. So therefore, we are going to kind of figure out conjectures or some, methods through which we can, really do some calculations and predict good thermoelectrics material for their applications in laboratory. So with this sort of introduction, I'm going ahead. So we are going to perform a lot of high throughput calculations. You're going to see the high throughput loops. I'm not going to show you all the high throughput loops that we have run, but we are going to show the main highlights. So we start with, looking at the thermodynamic stability of the material. So we calculate the free energies of formation, and then we see like which of the materials are stable. Then we perform band engineering, which I will briefly say now. And then like we figure out which are the materials which have the signatures so that like we can investigate them further. And those materials only, we calculate the transport coefficient and the thermal transport coefficients eventually. And then we predict the efficient thermoelectrics. So there in this picture, we are showing a FCC kind of crystal, not a FCC crystal. You can think like it's a fictitious crystal, which we want to, design. And in this particular crystal, you can see like there are many degenerate values in the conduction band minimum. And not only the degeneracy, band degeneracy is very high, there is a lot of K-point degeneracies in all the, all these values that you see around. And there are multiple bands also at the same time. So this is the fictitious picture. We want to achieve such kind of picture in the laboratory. So if we can, figure out with our computer simulation, which kind of alloying, which kind of alloying can do that, then we can, pretty much go ahead and do doping. And without affecting these band degeneracies, we can dope the system and we can achieve such kind of, material for thermoelectric applications. But this is only a conjecture. We are going to see like what are the, challenges in doing that, and what can, really disrupt the thermal transport and electronic transport, how to achieve a synergy between the two. So we are proceeding further. So the method is a first principles density functional theory, not going into the heart of that because this is a forum where people understand this. So in principle, we do a lot of optimization and then we calculate the transport coefficient. In this transport coefficient, you need the band structure. From the band structure, you can calculate the group velocity of electrons, the equilibrium Fermi population, and then this tau is the electron scattering lifetime. However, this is very hard to calculate from first principles. In this particular approximation, which I am going to show, because we are doing high throughput calculation, we are taking this as constant. and then we are proceeding. However, for the thermal conductivity calculation, this occurs at a higher length and time scale than this particular electron-electron scattering. Therefore, we are going to calculate this tau explicitly, and we can you can be rest assured that this is not also very easy trivial calculation, because there, even if symmetries are taken into account, you will have to do a lot of calculations. Even if you are doing density functional perturbation theory calculations or finite displacement, you'll have to take a lot of force, calculate a lot of force constant, which will require a lot of structures. So with this much introduction, I move ahead. So I will show three different works in the same material. So this is the row that we would be concentrating on. So all these elements X, Y, Z in the half Heisler compound will give a stable configuration, because this will give rise to 18 valence electron count, and therefore this will be a stable material. So this isoelectric compositions we are going to substitute, and you can see the mass is varying at each row. So therefore, because of this, the mass effect will be there, and then there can be effect in bonding and chemistry. So we do a lot of high throughput calculations to start with. So high throughput calculations means we are not doing anything special for anyone. We are just substituting, and we are looking at some of the properties. In this case, we see the band gap, because these are the pristine ones. They were all found to be stable and having similar kind of band gap between 0.3 to 0.1 electron volt. And therefore, we choose the earth abundant and non-toxic ones and go ahead with the substitution. And then we look into all the substitutional space and then detect which one is good. And then we find that this 0.5 composition with X substitution or for Z substitution retains a very high degeneracy, band degeneracy. You can see in the N-type region there is a very high degeneracy. However, the Z side substitution, so this is X side and this is the Z side. But the Y side substitution, which has been shown, is very detrimental, because you see the band degeneracy is broken. And this happens due to a symmetry breaking, a global symmetry breaking in the lattice, a tetragonal type of symmetry appears. And because of this, this band is broken. And because of this breaking in band in this P-type and N-type region both, it is not good for thermoelectric application. And if one can go and with this signature, one can just identify which one would be a good thermoelectric material or not. And you can see the one which has been Y side substituted is not very good for thermoelectric application, because if you are doping it, you are always going to get a lower power factor in this regime or this regime. So then, what is to be done? And then the KL is plotted over here. You can see that one with both X as well as Z substitution done is better for has the lowest KL and therefore can give you the maximum ZT. But then we moved forward because we wanted to look what is the next step, how to lower the KL further from here. So we, while we were working in this area, the experimentalist always found this 0.033% doping in any material, not only in half Heisler, but most of the materials, very small kind of doping leads to very drastic lowering in the lattice thermal conductivity. And the effect doesn't arise from the electrons, but from the phonons. So in this particular material, you can see this is the experimental curve which is shown, and we looked into it in further details. So I'll just show you the plot. So although we have taken into account of the thermodynamics and everything, and we have found which compositions to look at and all that. So here you can see with 3% doping, what happens is there is an extra peak which comes in the acoustic region. So the acoustic region originally was until here, but due to this extra atom which has been in the put in the lattice site, so you can see that in the full Heisler lattice site, the empty lattice site, because of this could not bond to the other environment. So this becomes a rattling kind of mode, and because of that, there is a disruption in the phonon conduction. And this particular disruption basically leads to drastic lowering in the lattice thermal conductivity. And then if you put more atoms, like more Y-site elements, then it just vanishes, because it again hybridizes and it retains makes a good acoustic mode over here. So we looked into this phenomena. We saw if this can be, universal, it can be, extended to other Feisler class, other materials in the Feisler class or not. And therefore, we looked into this particular, compositional space without changing the total valence electron count, which was kept to 18. And you can see, like with increase in Y-side impurity, in all cases, there is a very drastic lowering at about 3% or something. So there is a very drastic lowering in the lattice thermal conductivity. And all these calculations are anharmonic, taking into account of all the anharmonic 3-phonon scattering. So therefore, you can see, like if we stick to this regime, which is about 1%, 0 to 10% doping, then you can be rest assured that the lattice thermal conductivity will be very low in this material. And then you can see what is the implication in the electronic transport. So here, this is the phenomena, therefore, we suggested is like if you are looking at this particular regime, say like about 12.5% until that, then you have the rattling mode, which appears in the acoustic band. So for this, which is PD, which is Ni, and however, if the, like this is cobalt, which is somehow it has some different, phenomena also going on. And therefore, where it's and also not so heavy. So therefore, you can see like the peak is coming over here of this particular atom. So the extra atom, the peak is coming in the optical regime. And because of that, this spectrum is all, scattered. The spectrum is also scattered. The scattering rates are shown. However, here this phonon, the spectrum is retained. And therefore, we could say like, okay, this is the regime we are going to work on. So which is up to 12.5%, and we can see like whether there is anything in the electronic transport or not. So when we looked into the electronic transport, what we found is that this extra atom, when you bring into the system, then it will bring mid-gap state, and mid-gap states are flat, and therefore this will also disrupt the electronic transport. So if you are doping in this particular regime in here, then you are not going to gain any thermal transport like power factors, thermo power. So therefore, this is going to be very detrimental for both Ni as well as PD. Although you will gain some in the lattice part, but you are going to lose a lot in the electronic part. So therefore, further we showed like, okay, but in this case of cobalt, here this doping, which is lowering the lattice transport, is also, doing some light doping of the system, and hence will be very useful for gaining the thermoelectric power factor. And that is what we show in here. This is of course scaled by the tau. So one has to, calculate this tau explicitly to give a better picture. But here with the high throughput, you can say like, this particular picture, which is, with cobalt dope to 12.5%, is definitely giving a very high power factor along with a very low KL, lattice thermal conductivity. So although like, I am, towards the ending of the talk, but I will still show you the last thing that I wanted to show you. So these calculations of lattice thermal conductivity is not very trivial, because you will have to do a lot of, phonon displacement replicas. You will have to calculate the force, have to calculate the force constant, and then again, calculate the scattering lifetime, and it goes on. So therefore, we thought of, why don't we design, one particular code using machine learning, so that like we can already have a model and we can just put any material to say which one is the lowest lattice thermal, has the lowest lattice thermal conductivity. So therefore, we generated a data set. The data set, in fact, looks like this, which is like these are the materials, all will be half Feislers, because this we are doing for the parent, not for the doped one yet. And then like there would be descriptors. Descriptors are some properties pertaining to the elements as well as the compound. So those can be the descriptors, and then the outcome is the lattice thermal conductivity, which you just put in the data set. And then you can calculate, you can do some classification. If it is a binary thing, like whether high or low, then you can do some classification. But we are doing some regression where we try to fit a model to get KL. And this KL are already calculated through first principles. So here we have 150 sample points where all the calculations are performed from first principles and harmonic calculations to calculate the KL. And then like we have explicitly calculated, so these are the elemental features which are readily available pertaining to each of the elements. But for the compound as well as compound thermal features, we have calculated all the different, available or not available, features. So the bulk modulus, compound density, bond distances, these are, for instance, some of them. So we calculate for all of the, elements, as well as for these are for the compounds. So there will be only one of such, but for these elements, you will have to acquire. And then we build the model. And when we build the model, what we see is like even if you combine all of them, so like in this case, elemental, compound and thermal are combined into a single data, a single one, and this is the model. But this is the one, the blue one is the model with only the elemental ones. So you can just see the elemental ones are as good as the combined ones, and therefore like we can use only the elemental ones to predict the lattice thermal conductivity. So that before even going towards that, so what I need to mention there, like if you like have 150 features, then you can give a model, so there is nothing big deal about it. But then like you will have to find a space which is enough compressed, so that like in this type of complex space, you can still give the point. Like in this case, there may be like 150 dimensions, and you are giving a point, like whether you are doing a linear regression for the point. But if in this case, like there is only 2 dimension, but you are still giving a model. So therefore you will have to also like compressed sensing is always a good way to look at the problem, and it gives you many vital information. So we also did compressed sensing using this this code written by Runghai et al. So and then like what we figured out is this, like in case of the compound descriptors, the distance between 2 atoms, which is this two distance between the X and Y atom, is very important. And this basically gives more or less like shows a linear correlation with the lattice thermal conductivity. Same thing happens for the elemental descriptors also, where you can see this is the volume of the X element, and this is the volume of the Y element. This in principle gives you the distance between X and Y element, and this also plays the same role. You can see a linear kind of relation with the lattice thermal conductivity. Therefore, you find a model. So this model kind of depicts which would be the optimal distance between X and Y that you should look at for getting a meaningful lattice or lower lattice thermal conductivity in a material already. So and then like with 7 reduced descriptors only, we can already achieve a R-square score, which is pretty much very high. So therefore, I will just summarize like whatever I have told until now. So one can use this, calculations, the density functional theory calculations to predict thermoelectric material. Either you can, do the tuning of the, electronic band structure, or you can also play and tune the lattice thermal conductivity, so the descriptors for getting a meaningful lattice thermal conductivity, and together you can build a model for predicting good thermoelectric materials. So with this I end the talk. I thank all my students. So most of the work that I have shown in here is done by these 2 girls. So although others are also working in different areas, I thank the I thank my funding agencies, I thank the organizer, and I thank IIT Bombay and the IRCC here for all the generous funding. Thank you very much for your attention.
Thank you, Amrita. Again, it's a nice talk. And then the session is open for the question and answers. So please, yeah, so after that, please unmute yourself and ask your question.
Yeah, hi, Amrita. Nice talk.
Thank you, Aptabda.
Yeah. So just minor query on your zirconium nickel tin systems. These small excess, like 3% or 10%. These come just as a doping, or it also impacts the structure? Does it impact the underlying structure of the parent compound?
So it's going to impact and change the parent structure. Because it changes the parent structure, you will see a lot of change in the band structure also. So like even if you are having small doping, so it will change, it will hybridize with the electronic band structure, it will change a lot of things everywhere. So
no, but your calculations are in the parent structure where you are just Is that right?
No, actually we are optimizing it also at every step. Like even if we are putting one impurity, we are also, looking at the changes in the structure because of that impurity.
So does it change the cubic symmetry? Which is
So
what is
the
this?
thing is, like in this case, like when you are doping, this is not doping. When you are looking at the first stage, like with the substitution, like 0.5, 0.5 at the same site, then this is like a kind of alloying, and it doesn't disrupt the symmetry. So that is
that I understand. I'm
yeah,
asking
but
about the
for
small,
that
3%.
small thing that is there, that lowers the lattice thermal conductivity, but also disrupts the electronic band structure, and also has some minute changes on the structure. Yes.
So it does. Okay. Okay. Thanks.
So, any other question? Please raise your hand. Any questions from the students? Okay, I have one. So,
yes.
how your data? I mean, you showed the machine learning. You have a column of the data. I think there are different features. So how your features are correlated to each other? I mean, how your features are dependent on each other. So,
I got your query. So you wanted to ask
so my question is that simple correlation will be enough to understand that, or you need to go beyond of the correlation model, like causal relation and stuff like that? Do you think that will be more important here?
Yes. So actually at each stage, like when we added the elemental descriptors, we saw whether these elemental descriptors are related to each other or not at the first step. So then like we already got rid of the correlated features, and then we added more features. When we got the compound ones in, then again we saw like which of the features are are correlated to each other. Then we dropped the low-lying ones, like low-level simple descriptors. We dropped mostly, and we retained the complex descriptors because we thought like they might be more meaningful to be kept. So at every step, we got rid of a lot of elemental descriptors, and then we proceeded on at the later stage. And also in the process, many of the compound descriptors which are correlated to each other got dropped.
So basically, you gone through a feature ranking, and then they discard the features which are not used. In that is that you said it is
it's
not
not
important.
only like feature ranking. So it's also there. You can do a lot of different things to check which features are very much related to each other. We also checked that, and we also scored them, and we also dropped them simultaneously.
Okay.
Any other question? Sure of that?
Yeah, so I'm thinking this. So basically, what I'm asking is that suppose you have a target property and you want to go to the target property. You have different features. You have a feature space. So do you really think that to get to the target property with different feature space, which correlated path? So can you map the paths? So suppose I want to go to that particular target property. So I'll go to that feature. From that feature, I'll tune first. From that tuning, I'll go to the next feature. That feature I'll tune, and then I'll directly go to the target property. So you can basically think about building some causal model, which is a dynamical change in the feature space. So that can you give you a direct that correlation between the target and how the features are correlated with each other.
Okay. Yeah, so that can be also done, but mostly like when we do compressed sensing at the end, so it also does probably the same thing. It also combines the different space and then sees like which is the most correlated feature space. So you can go through probably this work given by done by Runhai et al. So Runhai Wang. So this was built in FHI. So this particular code probably takes into account of that. So initially we feed everything. So while we build our model parallelly, we also do compressed sensing. So each of the descriptor spaces combined with each other, and then you get this kind of space which has been shown. So this one.
Yeah. Yeah. So I have one question in the chat box actually. Nikhil asked that in your initial slide, you said you assume electron lifetime as constant for electrical conductivity. So my question is, well, this assumption predicts how well is this assumption predicts the electrical conductivity?
So actually, we did not get we did not really predict the electrical conductivity. So we just predicted trends, like which one of those will be good, which one of those will be bad. This was because like we are already giving this power factor divided by tau. So we are never, like if I have to give like electrical conductivity, I can only give you sigma by tau. So we exactly do not know what the tau is going to be. So that we can only know if we compare with some experiment or we do other calculations, intricate ones. So therefore, these are only trends that we see around in here, but the real calculations may be, different. It may be still very different.
Okay. So any other questions? Okay, so if not, then please thank the speaker, Amrita, for giving a nice presentation, nice lecture. Thank you.
Thank you, Saurabh.
And I think we can clap here, but I think there should be some emoji, right? We can flow the emojis. Okay. So the next talk will be given by Dr. Mukul Kabir. Dr. Mukul Kabir is currently an associate professor in Department of Physics, ISAR Pune. So he'll be talking about room temperature ferromagnetism in 2 dimension with a question mark. So I request Mukulda, please deliver your lecture. Stage is yours. Mukulda?
Sure. Thank you, Saurabh. First of all, let me thank the organizers, especially Anamitra, for the invitation. So in this talk, I'll talk about the possibility of room temperature ferromagnetism in 2 dimension. Since maybe we are all aware that, like, the room temperature ferromagnetism is available since last 2-3 years experimentally. However, the room temperature one is still elusive. Okay, there are a couple of results, but like they still pose a big question mark. Okay, so this talk will evolve around that fact. Okay, so one second, get a pointer. Yeah. So since we understand that that magnetism is 2 dimension is one of the most sought after quantum state due to its enormous possibility. However, we also understand that, like, we could have just taken a ferromagnet which has a very high temperature high ordering temperature, and we can bring it down to at least quasi 2D and use that as our technological purpose. However, that is not the fact, since you bring it down to quasi 2D, your TC decreases enormously. For example, here your elemental cobalt has a TC which is of the order of 1400 Kelvin, but it falls below 100 Kelvin when you bring it down to 1 monolayer thick thing. Okay, so this is one of the biggest challenge to have a ferromagnet which can operate around room temperature. On top of this problem, you also have a couple of other problems when you think about monolayers of this type of bulk material, is that there is a strong substrate dependence on your TC. Okay, and also have a problem of growing this type of samples like due to the surface roughness and all these issues. Okay, so maybe in this regard, the magnetic van der Waals material might be a way to discuss and investigate. Okay. 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 So what I'll talk about in this in next 15 minutes is that I'll talk about various magnetic models and where these real materials fall in this picture. Okay, and I'll talk about if electrical manipulation is possible. In this talk, I will talk about only how one can electrically manipulate the TC. Okay, and I will leave out a lot of important analysis. Okay, and the interested people might look into this to recent papers. So this work we are doing for last 1.5 years now, and some of you might have seen some of the preliminary results in some other conferences, but yeah. So here I'll try to give a complete picture, basically summarizing these two papers. Okay. Okay. When you think about magnetism in 2D, okay, you think that, like, the Weinberg-Marmin-Wagner theorem tells you that there is no ordering, okay, in 2 dimension or in 1 dimension. Okay, that you also can see from this isotropic Heisenberg model, that if you due to the isotropy of the spins, okay, there will be no ordering. However, we all know from the textbooks that, like, if you have Ising spins, okay, then there is a magnetic phase transition at some temperature. Okay, however, in the context of real materials that I am going to talk about, the Ising model would be very, very unrealistic. Okay, since it is intrinsically, you can think the Ising model as a system with infinite anisotropy. Okay. However, in real material, and due to the energy scale, the very small energy scale of spin orbit coupling, okay, your magnetic anisotropy is small. Okay, so that's why the real materials would be better described, okay, rather than a isotropic Heisenberg or a pure Ising spin or a pure XY type of model. The real materials are more or less like, anisotropic Heisenberg model or weak XY type. Okay, depending on the direction of the single point anisotropy. So what we proposed in our first paper that okay, anisotropic Heisenberg model is the way to go, but that may not be enough to realistically describe these materials, and one needs to go beyond the first nearest neighbor interactions. Okay, and we find that for the spins arranged in a honeycomb lattice, one needs to consider all the 3 nearest neighbors and the on-site anisotropic term. Okay, so here, so this would be the Hamiltonian that we'll be using okay, later on. In this Hamiltonian, what we have neglected is the DM interactions, and which is like, your inversion symmetry in this material is preserved. So your DM interaction goes to 0. Okay. However, there is a catch also. Once you bring in the spin orbit coupling, then your second nearest neighbor DM interaction might be finite. Okay, but that the value of that interaction is very, very small. Okay. And also this anisotropic exchange are similar to the Kitaev type of interactions. And we have also seen that the such off-diagonal interactions are very, very small. So we also have neglected that. Okay. So all these parameters in this anisotropic and long-range Heisenberg model are calculated from the first principle DFT calculations, and then we feed all those parameters calculated from the first principle fidelity, okay, to Heisenberg Monte Carlo and calculate the ordering temperature. Okay. Okay. So here is a one slide test that how this model performs on a realistic material. So here we apply it to two-dimensional single layer CRI3. Okay, and we calculate all the J's that I had said. And if you do a Ising calculation, okay, if you don't look into don't consider your system to be an isotropic Heisenberg, but Ising model, then you get a TC which is of the order of 135 Kelvin. Okay, whereas your experimental TC is 45 Kelvin. Okay, so you can understand that you know, just putting this system into the Ising would be a wrong description. Okay. And what our model predicts is a TC which is 42.5, which is very close to the experimental one. Okay, and also we see that the importance of the second nearest neighbor and the third nearest neighbor interaction until you take all the first, second, and third nearest neighbor interactions, your estimation of TC is far away from the experiment. Okay. One important fact is also to look into the critical exponent. Okay, what we find for the real materials is of the order of 0.2 and 0.21 to 0.23, which is in between the 2D Ising model and the 3D Heisenberg model. Okay. So this gives us a confidence that, like, you know, now we can go ahead and use this model to predict which isn't experimentally observed yet. Okay. So there is another test. What we can do is that we can use the Holstein-Primakov prescription, okay, and look into the spin wave spectrum. Okay. And since due to the anisotropy, there would be the spin excitation gap, and we calculate that excitation gap to be 0.53 MeV. Okay, now you can match this number with the experimental inelastic neutron scattering, okay, for this material, and which is of the order of 0.3 to 0.4 MeV, and we find that our results are matching with the experiment. So this gives us another layer of confidence in our model. Then what we intended to do, since the intrinsic material has a TC which is 45 Kelvin. Okay, so our question was whether we can manipulate this TC to somewhere near the room temperature. Okay. So to do that, so we have taken some clues from the experiment, okay, where they have seen that the magnetism can be electrically manipulated in these materials. Okay, so one of the experiment had showed that you can switch the interlayer antiferromagnetic coupling to an interlayer ferromagnetic coupling by tuning the gate voltage. Okay, and in another paper, they also see that this orange curve is that you can also manipulate the TC, okay, by tuning your gate voltage. Okay, and it is important to observe here that if you dope hole, okay, which is like negative gate voltage, then your TC increases. And if you dope electron, okay, your TC would decrease. So it would be another important test that whether our model can also predict that qualitatively. Okay. But before going to that, there is another experiment in a different 2D material, but it is not perfectly single layer and perfectly 2D, but it's a 3 layer. So it's a you can consider this as quasi 2D material. There, they also have manipulated the TC from 100 Kelvin to 300 degree Kelvin by tuning the gate voltage. Okay, but we will see that. I'll probably not talk about that, but this is not very universal. This is very, very material dependent, that whether you would be able to tune your TC or not, that's not universal. Okay, so then what we see as the experiment had shown, that as we increase the hole density, our TC increases, but the TC increase is not monotonic in CRI3. Okay, and when we do dope electron instead of hole, then the TC also decreases, but the decrease is minute and the increase is huge. Okay, so it goes from 45 Kelvin to 225. Okay, which is still far away from the room temperature, but this gives us some confidence that there might be some other material which can have the room temperature TC. Okay. Now from this these two features, we can see that it is exactly mimicking what experiment had told us, that with electron doping your TC will decrease, and with hole doping your TC would increase. Okay. Then when we applied the same methodology to another material which is very close cousin of CRI3, which is CRBr3. Okay, and we see that CRBr3 with hole doping, the TC actually monotonically increases. There is no two slope like and what we see for CRI3. Okay, and we see at a certain hole density, okay, you observe the room temperature varieties. Okay. Okay. Now one might ask that this hole density is little high, on the higher side, but I can promise that this type of hole density is achievable in experiments and already achieved in some other material, in some other context. Okay, by liquid ionic liquid getting, or by the femtosecond laser pulse. Okay. Another thing would be interesting to see is once we look into the critical exponent, that critical exponent actually decreases as you increase the hole density. Okay, so if you remember, your 2D Ising limit is here, which is like 1/8. Okay, so as you increase the hole density, it goes towards that, but very, very slowly. Okay, and we'll see that why that happens in a minute. Okay. Okay. So to tell you why that happens, so we also looked into various isotropic exchange interactions and various anisotropic interactions as a function of electron density and hole density. I'm not showing you the electron density because that is not that interesting as the hole densities are. Okay, so you see that the on-site anisotropy, okay, increases very sharply as you increase the hole density. Okay, and you can think of that it is approaching towards the Ising limit. Okay, but it's far away from the Ising limit, but you can quote unquote think like that. Okay, and what we see in the isotropic exchanges, that your J3, the third nearest neighbor interaction, has a drastic effect on the hole density. Okay, and these numbers in combination with all the anisotropic interactions, okay, give rise to the increase in TC. Okay. Okay. So what happens is that once you dope carrier, okay, in the form of hole or electron, okay, your orbital occupancy changes. Okay, your local and orbital moment also change. Okay, your on-site spin orbit coupling energies change. Okay, and also it may induce a little bit of strain. Okay, in the lattice. Okay, so to decipher that, okay, whether this is a purely strain effect or whether this is happening due to some orbital occupancies and all these things, we looked into the case for strain. Okay, and we see that as we like, you know, for both type of tensile and both type of stresses, okay, your TC decreases. Okay, so this figure tells us that the effect that we have seen earlier as a function of charge doping is not related to the strain. Okay, so it is only coming from the electronic contribution of this material. Okay, so now let us try to understand qualitatively that why you know, your hole doping or electron doping increases or decreases your TC. Okay, before that, let us first understand the undoped case. So your CR +3 has a electronic configuration of T2G3 and EZ0. Okay, so you understand that, like, you know, your T2G, the half-filled T2G and the half-filled T2G interaction will be antiferromagnetic, and the interaction between T2G3 and the empty EG would be ferromagnetic. And in this material, this interaction, like, you know, is stronger than the AFM interaction, and you have a ferromagnetic solution. Now, when you dope hole, then you dope a hole in the T2G level. So your AFM interaction destabilizes, but your AFM interaction remains what it is. So since your AFM interaction is destabilized right now, okay, so you get a stronger ferromagnetism and your TC increases. Okay. In the contrary, in the electron doping, your electron goes to the T2G level. So your T2G interaction remains AFM, okay, but your T2G and the partially filled EG level, your AFM interaction gets destabilized. Okay, so you get a weaker ferromagnetism and your TC decreases. Okay. Okay, so so in this thing, we also have looked into the phase diagram. Okay, and where you stand in this phase diagram. Okay, as you dope electrons and holes. Okay, so this will give you a complete picture. So this is a neutral CRBr3. Okay, which has a ferromagnetic ground state, but that ferromagnetic ground state lives very near to the to a helical solution. Okay, so you don't know what would happen once. Huh?
3-4 minutes, Mukunda.
Okay, I'll be done in 2 minutes. Okay, so so now so once you put your neutral CRBr3, you don't know, like, you know, once you dope, once you part of the system, which way it would move. Okay, so what we see is that when you dope hole, okay, your J2 over J1, J2 and J1 changes, but the ratio almost remains same. Okay, however, your J3 over J1, as I told you earlier, that J3 increases very rapidly. So your J3 increases very rapidly, okay, and your TC increases monotonically in CRBr3. Okay, So, but interesting thing happens when you dope electron, which is not what we want as our technological purpose, but scientifically very interesting. Okay, so once you dope electron, what happens? It remains ferromagnetic for small amount of electron doping, but your TC decreases. But then what happens is this field black triangle. Okay, they represent a ferromagnetic state, but here the spins, rather than being perpendicular to the surface, okay, they become in plane. Okay, so there is a directional change of the shear spins. Okay, and if you increase the electron density far beyond, then you are no longer in your ferromagnetic regime, and you predict a strip type of antiferromagnetic structure. Okay, so the details are in this recent archive paper. Okay, so what we conclude out of this thing, what we are doing for last 1.5 years, is that the real materials are far away from Ising or pure XY or isotropic Heisenberg system. Rather, they fall in between. Okay, and the proper treatment is necessary to reproduce the experimental results quantitatively and qualitatively and be predictive. Okay, and we also show that this carrier doping or gating or maybe an encouraging route to achieve room temperature ferromagnetism in 2D. Okay, which may open up a very exciting direction in quantum materials. Okay, so that's it, and thank you again for listening.
Thank you, Mukulda, for a very informative talk. And I can see one question is already there from School of Physics.
Hi, Mukul. So this is Anamitra. So yeah, I mean, we have the common login. So a nice talk. I just wanted to ask two questions about the material, particularly the EG-T2G sort of scenario that you were looking at. So I was thinking of you in the manganites. A very similar thing happens where you have 3/2 T2G Hunts coupled moments. And in that case, if there are electrons in the EG, that increases the TC. That's sort of the double exchange model. That structure of the model is 1 plus, I believe, 1 plus square root of 1 plus SI dot SJ by 2 or something like that. Okay, the course spin this thing. So here you're saying kind of the opposite situation because that's one part. Maybe you can correct me. I'm just trying to understand. The second thing is when you hold up the system, when the T2Gs are partially filled, what keeps the system insulated? In the manganites, of course, there is electron-phonon coupling, which plays a role, and the T2Gs never get empty there. The EGs play a role. So maybe you can comment on this. Yeah.
Right. So let me tell you the answer of your second question first. So this doesn't remain insulating any longer. Okay. So there is a very small metallicity is induced. Okay, but very tiny. Okay, so the
you're saying that the bandwidth will be too small to it will get localized in the material.
Yes. So it has two facet of answers. A is your density of state at the Fermi level is very tiny. Okay, A, and the B is that you can still represent the system with the localized moments. Okay, so I haven't shown that analysis here. So as I dope electrons and hole, and if I calculate the localized moment localized at the CRI3 within a sphere, okay, that kind of remains intact. Okay, so your moment is still localized, so you can in that case still use this type of models.
But if sorry to interject, but if I put a small field, for example, what prevents the two colored, so you have these two electrons which are sitting in the T2G to conduct, because the third level is kind of quasi very close to it in energy. Is it that the Hund's coupling is still strong enough that it tries to keep the two electrons still aligned, and then there is no phase space of hopping to the next side?
So one more thing that I tell you. So this electron, okay. So this electron this electron or hole, whatever. I should not say is a hole. This is a partial hole, right? This is not one hole per atom. It is far away from that.
So you're saying that the Sure, I understand. So you are saying that the moment is kind of spread, it's not to think of it's like a core spin moment anymore when it's partially, but nonetheless the moment survives.
Yes, so moments are local, and you know, my drawing might seem that like there is one hole per atom. It's not one hole per atom. It's the density is far less. Okay.
Yeah, I understand.
Yeah. Okay.
And this thing about the double comparison with double exchange for the electron.
So it is not double exchange. It is super exchange still. Okay, here. Okay. So your every chromium is in the same state. Okay. So it's not like, you know, one chromium has a charge state which is different from other chromium. It is not that.
No, but Mukul, see in this right side picture, if I were to draw the Fermi energy, nominally it will lie in the EG. Is that a correct statement?
Yes.
So there is a super exchange component coming from the T2Gs, of course, that will not change. But then the EGs, won't it give it a metallic property? See, in the manganites, this doesn't happen because there is electron phonon, there is a Jean-Taylor splitting. So but here, is there a Jean-Taylor splitting also, because it's a half-filled EG with a symmetric structure? So structurally,
it's again not half-filled. So it's again very tiny amount of electron density.
So I see. You mean okay? I see. You mean okay?
Right.
I agree.
Right. So it's not
partially filled, but
yes. So partially, but not with one electron. It's very tiny.
Yeah.
Right.
Very low.
Still, it's low doping, but doesn't it still make it metallic, because the Fermi energy would be there, right?
It is. But as I said, that it's still metallic with a very tiny density of.
Okay, even here the same argument holds. Okay, sure.
Yes.
Thanks. Sure. Thank you.
Any other questions from the students, or any other other questions? You can raise your hand or type in the chat box. So anything is fine.
Unfortunately, on my laptop, I'm not getting the raise hand feature. So can I go ahead and ask?
Sure. Please go ahead. Please. Yeah.
Hi, Mukul. Could we please go back to the slide where you showed the anisotropy parameters in one plot and the isotropic?
So this one, you mean?
So if I understand correctly, in the last phase diagram that you showed, we are in the delta equals 0 limit. Right? In these, if I in the final slide when you're showing the phase diagram, so we are in the delta equals 0 limit. Is that correct?
No, actually. So delta equal to 0 is your this dot. Okay, and as you increase your delta hole density, you get this plot.
So as we go up along the blue dots here,
yes, you increase the hole density.
So no, your color scale is showing TC. So if I go
color,
from one blue,
so you look into this arrow. So this arrow tells you that I am increasing my hole density on this way. Okay, and the color plot gives you the TC.
Okay. So the lowest dot is delta equals 0, and as I
delta equal to 0 up,
so
your delta H increases, and also if you go along this path, your electron density increases.
Okay. So now, so I wanted to clarify that. So now, if we could go back to the plots with the
sure.
two. No, the previous.
Here, right? You want this one?
Yes. So I suppose the point that you want to make in your talk is that your ordering is because of the parameters on the left, right? I mean, if you only had the isotropic, you won't have ordering, even though they are slightly more than nearest neighbor. As long as they are short range, you shouldn't be getting an order.
Yes.
So if you take the anisotropy parameters along any of these lines, so you did spin wave calculations you mentioned, right? With Holstein-Primakov. So typically what will happen is that if you start from some semi-classical ordered states and do a spin wave calculation with these anisotropy parameters present, they will give rise to some small gap scale. Okay, you won't get standard Goldstone bosons or anything, but you will find some gap scale which will ultimately tell you what your ordering temperature, when your ordering will ultimately be destroyed as you raise the temperature.
Yeah.
So using these, using whatever delta is appropriate in the final slide that you showed at any point, if you try to extract such an ordering temperature using these anisotropies, are the two numbers consistent?
No, we haven't done that. So our TC is calculated from the Monte Carlo. Okay. We haven't calculated our TC using the Holstein-Primakov one. Okay. We only calculated the gap here. Okay. And we found that that using this gap equation, you can also, you're right, you can also calculate your TC, but it has been shown in few papers that doesn't match very well. Okay, so I don't know. So rather than that approach, rather than that approach, we have taken these parameters, feed in the Monte Carlo, and we calculate the TC, which I believe is a better way to calculate TC in this type of materials.
Okay. Thank you.
Okay, so thank you. It's a very nice talk and very nice interaction. So if we can take another last question. If anyone want to ask any question, please unmute and ask, or maybe put in the chat box. Okay, if there is no other question, I have a very small query. Kulda, maybe I missed that part.
Sure.
If you dope electron hole, do you expect localized charge ordering in this two-dimensional lattice?
Charge ordering?
Yeah, localized. Your doping constant is very less, I understand, but still, don't you expect them to be localized charge ordering in different regions?
I do not expect, but I haven't looked into that perspective yet. But my guess is there won't be any charge ordering.
Okay, and do you think any particular reason behind that?
No, no, that is only my hunch. I haven't looked into that type of charge ordering or something. It won't be, because like it is a small, and the charge I am interested mostly in are localized. Okay, so I do not think there will be a charge ordering. Okay. But that's only my hunch. Yeah.
Thank you, Mukulda. Thank you very much for this nice, informative talk and very in-depth discussions. Thank you, Mukulda. Let's thank the speaker.
Yeah.
Thank you. So our next speaker is Dr. Shashwata Bhattacharya. Shashwata is already here. Hi, Shashwata. He is currently Associate Professor, Department of Physics, Indian Institute of Technology, Delhi, and we have long association. So Shashwata is going to talk on exploring optical properties in perovskite-based solar cells, theoretical insights from hybrid DFT, GW, and BSC. So with that, I request Shashwata, please deliver your lecture.
Thank you, Shorabda, and thanks to the organizer. My screen is visible, right? Can you confirm if you can see my screen?
Yeah, now it's came. Yeah.
Perfect. So let me take the pointer and let me minimize this one. Okay, so thanks once again for inviting me, a nice introduction. So earlier I thought to deliver something else, and that's why I have put a very general title. And then in this morning, I had decided something else, and basically I'm going to talk something. It's much smaller part of this whole talk. So anyway, I'm talking about optical properties. That is what you can understand clearly that I will talk about mostly excited state properties. And then I will show that how the usual conventional DFT miserably fell, and you really need to go to a much advanced theory to address those properties. Now, let us start with a very well-known perovskite, which is humongously well-studied material, and that is MAPBI3. That is this is the methyl ammonium sitting in the middle, and this is a lead iodide gauge. Now, experimentally, this material is synthesized, and its band gap is predicted around this. Now, from DFT perspective, if you do a simple PV calculation, you get a very nice match. Like you see, this is your experimental number, and this is your GGA number. So people may think that, okay, there is no complexity in this particular material. So it's a very straightforward material. And if you are doing simple DFT with, say, conventional semi-local functional, then you get a nice mismatch. But the situation is not that actually simple if you dig deeper into this particular material. For example, you can understand that this has a lead. Now, if you have a lead, then there should be some spin-orbit interaction. So the moment you include the spin-orbit coupling, then your band gap gets reduced to very absurd, like 0.5, something like that. At the same time, this material has AVZ lead and also iodine and many other electrons. So conventionally, it should have some electron self-interactions error, which PB should be unable to capture in principle. So if you include it, like if you do hybrid functional, where you include the some portion of the Hartree-Fock exact exchange, then you get something which is kind of overestimated. So now you can understand that the spin-orbit interaction and the electron self-interaction error, they are actually equal and opposite in the both the directions. So that's why, and they get cancelled out, and that's why once you are doing simple PBE, then you are getting nice results. But that is a pure accident. Now, if you want to make things better, that with HAC plus SOC, you get somewhat like this. You sort of try to tune your alpha parameter so that you can actually reproduce the experimental band gap. Now, if you want to make it better, you add up GW on top of this, then things are even better. Now, if you want to exactly reproduce the experiment, then you solve the Bethe-Salpeter equation. I will come in a minute what I mean by Bethe-Salpeter equation. And then only you can reproduce the experimental situation very accurately. Now, this is the whole situation. You see that this is sort of very crude, and this was also predicting something close to experiment. And this is also very accurate, and this is also predicting something very close to the experiment. Now let us try to understand the band alignment. Now, why it is happening. So once you are doing simple PBE, then this is the location of your conduction band, and this is the location of your valence band. The moment you include the spin orbit coupling, your conduction band gets splitted and it comes down, and you hugely underestimate the band gap. Now, once you include the self-interaction error, so then your valence band comes down, and once you sort of tune the alpha parameter, you actually end up getting the correct situation. So you can clearly understand that the position of the valence band and the conduction band are very wrong from your DFT calculations with semi-local functional, and that is quite obvious, because if you go to the basics of DFT, so this is your pure interacting system, and this is a purely fictitious non-interacting system. You try to sort of mimic these two by ensuring that they have a same density. You sort of get to calculate things, but at the cost of losing the interpretability of these eigenstates. So that makes no sense, and that's exactly what is happening on. Now, if you want to sort of probe the band, you need to go one level up. And if you try to understand a photo emission experiment, for example, so that you shine light, you remove electron from the top of the valence band, and that's how you probe at the valence band top. At the same time, if you want to do the inverse photo emission experiment, that you bring electron from infinite, and then you bring it at the conduction level, and then also you detect the light. So if you want to understand this type of experiment in theoretical part, so then you do both photo emission and inverse photo emission, and then you take the difference, that is the ionization potential and the affinity, and this gives you the gap, fundamental gap. That's how you can calculate, and this we calculate within the many-body perturbation theory. And this is the quasi-particle eigenstate, where what we do is that we start from this eigenstate surely, but here our self-energy operator, which keeps on sort of updated, and then we add it up with this one, that starting point from the DFT, and that's how we can calculate it. Now, let's try to understand what do I mean by quasi-particles, especially for the students. So once you shine light, the electron is moving from this situation, and then this hole is created, but this hole will not stay idle in its position. So it will create a time-dependent polarization, and as a matter of fact, it will be reorganized like this. And as a matter of fact, you can understand that this electron-hole interaction and this electron and these hole interactions are not actually same, because now this hole is screened. So if you want to compute that, and that is sort of the spin Coulomb interactions of the W in GW approximation, you can actually calculate this thing. And this is basically from your light matter interaction. So you can write your polarizability like this, and you truncate everything to the first order. And you can compute susceptibility, conductivity, dielectric tensor, and many other things. Now, but this has nothing to do with the spectra. So if you want to understand the spectra, so then you need to go one level up in this methodology. And this also comes within the many-body perturbation theory. But here we shine light, not as much energy as before. It's just that this electron moves to the conduction band, and then they form a bound state, and that is the electron-hole pair. Now, if you want to understand that, you have to solve a two-particle Schrodinger equation, where you have electron Schrodinger equation, this hole, and this electron-hole interaction. And this comes under Bethe-Salpeter equation. So now, of course, this summarizes like this. So if you want to understand sort of the difference between the ionization potential and the electron affinity, that is sort of your quasi-particle band gap, this you calculate under the GW approximations. But if you want to calculate the optical band gap, then you have to deduct this exciton binding energy that you have to compute. And this is only possible under the Bethe-Salpeter equation. So without solving that, you cannot do that. Now, fine. So this is what we are doing for many systems. I'm not going to details of any of these. I'm just trying to show you in this particular talk that what is the challenge in doing that. Of course, this is computationally expensive. There is no doubt about that. But still, even with reasonable computer resource, in principle, you can do that. But in some cases, you cannot really do that. And in such cases, what are the situations? Let me tell you. So I take an example, which is a recent perovskite, and chalcogenide perovskites. It is also experimentally synthesized in ISA Pune group by Anshuman Nag and others. Now, we have addressed this chalcogenide perovskites before. This is the bulk form. But I'm not going to talk about much on the bulk form, because in the bulk form there is not much challenge. The unit cell does not contain too many atoms. So the problem comes once you have a big supercell and you have too many atoms, then the convergence of BSC or GW become a real issue. So I'm talking about the Rudolph phase of this chalcogenide perovskites. And this is how the structure look like. So this is the n equal to 1 phase. You will see here you have only one layer. Now, if you go to second and third, that's how the size keeps on increasing. And this is these days, these RP phases in perovskites are hugely popular. And plenty of experimental results are available. Now, if you want to understand their excitonic property or the excited state property or all the optical parameters, then you need to do this computation at the level of GW or BSE calculations. But here is the challenge. Now, let us try to understand the challenge. You see, this is a simple plot of the imaginary part of the dielectric function. And as you see, I'm trying to converge it with respect to the number of vacant orbitals. So you can understand that once I will excite the electron will move from the valence band to the conduction band. And in principle, in the conduction band, I should have infinite number of vacant states. But that's not logical. You cannot ensure there are infinite number of vacant states. So what we do is that we try to converge with respect to number of bands. And then at some point of time, if we see that, okay, the number of bands are converged, then we sort of say that, okay, we can safely calculate everything with this many number of states. Now you see that this number of, on increasing the number of bands, this peak is getting shifted back. And of course, you also can understand that as you increase the number of bands, your computation is also becoming more expensive. I mean, almost next to impossible to some extent at some point of time. And at the same time, you need to compute it with good number of K points also. So here also, you see, if you keep on increasing the number of K points, like 444, 441, 661, so on, this peak is getting shifted. So you can clearly understand that this is, I mean, satisfying both simultaneously is something next to impossible. And I can tell you, for reasonable supercell size, like more than 20, 30 atoms, and doing it at the level of 800 states and 444 beyond, doing BSE is almost next to impossible. But if you do not do that, then you will end up calculating this peak wrongly. And as a matter of fact, once you take the difference of the GW peak vis-a-vis the BSE peak, then you will get a wrong number, and that will be your exciton binding energy, and that will be not correct. So somehow or the other, what you need to do is that you need to do this peak get converged. Otherwise, without that, it makes no sense to do the computation. So what we do is that we, instead of BSE, in this particular system, this is not possible. I mean, you see that the number of atoms in these systems are so many that you cannot really compute straightforward BSE. GW is possible, but BSE is just next to impossible. This is not possible. So that's why in this system, what we did is that we have done it is using a model BSE approach. What we do is that this is sort of my quasi-particle equation, and this is my self-energy operator. And this portion is, if I write down this portion in a greater detail, so this is sort of the Green's function, and this is the cell screen-Coulomb interaction. This is the W. And instead of computing this dielectric tensor at the level of RPA level, what we did is that we computed this with a parameter-based model. So this is sort of, this is called dielectric, clamped dielectric constant. This is also a constant, and lambda is also parameter. Now what we did is that then we tried to fit this with our GW calculations, just by fitting this with respect to different G values. And after that, what we showed that this accuracy is as good as the BSE accuracy. But the advantage is that using BSE, you cannot really compute more than 441 K points or something like that. But with MBSE, we could actually afford 881 or even further, like 1212 or something like that. So this sort of helps this type of computation orders of magnitude, and also without any cost of the accuracy. Now, another important part is that if you are doing simply the GW, then you see that this exciton nature is completely missing here. So you do not have this exciton peak in any of these n equal to 1, n equal to 2, or n equal to 3 type of Rudolphson proper phases. But once you do it with model BSE, then only you get to capture this excitonic peak. That is also something very interesting. And of course, this system is pretty big. You cannot do a full-fledged BSE. So using MBSE, we could get that particular peak. And then somehow, if you compute, even if your peak is not converged with the exciton binding energy using BSE, you get these numbers, which are, you can clearly see that this is not correct. But once you do it with MBSE with a higher KMS, once you converge the peak absolutely at that particular position, then only you get to know these numbers very correctly. So these are the very correct numbers. Now we have seen there are cases that even if you do everything at the MBSE level, then also the peak is not getting converged. I mean, the size of the system is even bigger, but your neither BSE nor MBSE work. So in such system, what you are supposed to do? So that's why here we are giving another method, and we have actually computed using this method also. That is called one-year mod approach to compute the exciton binding energy. So this is the formula for 2D kind of structures to compute the exciton binding energy. And this is your dielectric constant. Now, what we do is that we compute the dielectric constant, the electronic part at the GW level, and the ionic part we compute using density functional perturbation theory. And then by solving this integral, we can calculate this epsilon effective. By putting it here, we can get some number to compute the exciton binding energy. Now you can clearly understand that here you will get some range. Like if you are talking about the ionic part, which is, if it is a predominant one, then you will get the lower bound of the exciton binding energy. And if you are computing with the electronic part, then you will get the higher bound of the exciton binding energy. So this is exactly what we did, that this is the dielectric constant. And if you see, this is the electronic part and this is the ionic part. So once you are talking about the ionic part, you get the lower limit of the exciton binding energy, which is of the order of MeV. And if you are computing everything at the electronic part, where the ionic part is not included, and then you get the higher limit of this. And this is pretty much within the level that we have computed directly from taking the difference of the MBSE peak vis-a-vis the GW peak. So that is quite in line to this. Okay, so then the next part is computing the exciton lifetime. So here also, if you get to converge your BSE or MBSE approach, then it is very good. You can sort of take the FWHM of this particular peak, and you can clearly say that what will be the exciton lifetime. So they have a clear understanding from this exciton peak. But in case you are not able to compute the BSE peak or MBSE peak for system, which is sort of very big, in that cases, you can calculate those things from your one-year mod approach, where you compute this wave function of the electron hole zero separation mode. And this is actually directly proportional to the exciton lifetime. So you can compute directly by taking the inverse. There is a relation between that. And using that, you can comment for this particular system. You see the exciton lifetime is the highest one as you keep on increasing the size. I mean, the number of layers. So n equal to 1, 2, 3, and so on and so forth. Now, and also we have shown that if you keep on increasing that at the bulk limit, this is sort of the highest. So now the final part, since this material works mostly in solar cell, so you need to compute the electron hole mobility also. For these things, what we do is that first we compute the simple dielectric constant, and that is what the simple calculations using just with changing the lattice, you compute this one. And then you monitor the positions of the valence band and the conduction band and how they are getting changed with respect to the lattice vector. So here also the role of computing very accurate positions of the conduction band and the valence band is very important, because if you're doing everything at the DFT level, so those levels are not really correct, that I showed in few slides back. So once you do that, you can put this value here once you take the slope of this, and then in principle you can calculate the electron hole mobility and from this deformation potential approach. Now this has nothing to do with the polarons. So if you want to include the polarons also, then you have to actually include the electron phonon coupling to include the optical phonons. So this is what we did, and we have actually calculated. Yeah, I'm already more or less done. So electron phonon coupling we have calculated from this Froelich model, and if you see that, then you see that the polaron numbers, and if you compare these numbers with these numbers, the electron hole mobility, then you can clearly understand that there is huge effect from the optical phonons. That means so here you include actually the acoustic phonons, and once you include the optical phonons, you can actually talk about the polaron mobility. So okay, so let me conclude. So this whole part, the exciton binding energy decreases on increasing the thickness of the perovskite layer. The significance of the ionic contribution to the dielectric function decreases on increasing n, and the charge carrier mobility is maximum for n equal to 1 phase and decreases with increase of n. So these are somewhat the standard conclusion from this work, but the main message I would like to give is this one, that to address the excited states, one needs to go way beyond DFT. So if you do not really take care of all this interaction, then things are absolutely wrong. And all these methodological developments are given in these two particular paper, and all the applications are included in this paper. So these are mostly application in various different types of perovskites. Okay, so with this, let me thank my PhD students. Presently, she is a postdoc in France, and she actually started developing this particular field alongside of Manish. He is also about to finish his PhD. And the most of these works, the last part of these works are done by Deepika and all my students. I'm extremely thankful for their sincere efforts, and of course, the funding agency. Without their generous support, we cannot do real research. And if you have any questions, which is not possible to cover up here during this short time, you can feel free to write me here. And if you want to understand in details regarding the whole optical properties and the works that we are currently doing right now, 5% of that I have talked here. So you can see in my webpage under the research part. So thank you for your kind attention.
Thank you, Shashwata, for a very informative talk. So the session is open for questions. Please feel free to ask questions. You can raise your hand, put in the chat box, or just unmute and ask. Any questions? I mean, you can just unmute and ask, shouldn't be any problem.
So Saurabh, can I ask one question?
Yeah,
Also,
sure.
I can ask, separately. That is also fine.
No,
So,
you ask, right.
yeah. So, can you just show me like the slide where you showed the convergence versus K points and yeah.
This one?
Yeah. So, can you just give me an idea of how much is the computational power which was invested in terms of time, course?
Well, for 12.12.1, I guess you need roughly 200 processor for maybe 6 days maximum for this particular system. Yeah, I mean, these are computationally expensive. There is no doubt about that. And for 4.4.1, maybe 2-3 days, maybe something like that.
Okay.
Using more than 100 processors, sure. And for this N-band 900, I do not know, maybe it is also roughly 1 week with 200 processors or something like that.
So, and then like, okay, this is fine. So I understand the computation is pretty much expensive. So can you just like, also comment like which model, like you have shown 2 different ways of calculating the electron phonon. Yeah.
Yeah, the idea is that if you can somehow converge your sort of BSC peak, then you can compute exciton binding energy straightforward. There is no problem. But if your supercell size goes up more than 40-50 atoms, then almost converging this is very difficult, because you can, if you increase the K points, the peak gets moved and moved and moved. So that is the big problem. And as a matter of fact, what happens that you at some point of time, even with the fastest supercomputer, you cannot really do it simply. So this is the big challenge. It's not like that in IIT Delhi we do not have a good computing resource. It is very good, I would say. But even with anywhere in the world, you cannot really do that. So then what you need to do is that then you have to address it qualitatively. And that is why I went to the 1-year MOT approach, where you can address it, but you can comment the exciton binding energy, but within a range. But this is also not very bad, because if you are trying to compute the same thing from experiment, then also you can match whether this is falling within the range or not. But the problem of this is that it is not giving you a pinpoint value that this is the value. For example, here we could calculate this exact value that this is the exciton binding energy, and for bulk actually we have compared it with the experiment. There is one experiment and where people did it, and we found exactly the same value. But if you cannot do these things, I mean, model BSc is computationally less expensive than BSc, surely, but still it is expensive. It is also not like that it is very easy. I mean, you can do as you do DFT, but still sometimes what happens that especially if your system is sensitive to spin orbit interactions, so sometimes model BSc is also very much computationally expensive. So in that case, even with MBSE, you keep on getting this problem that your peak gets shifted abnormally. And as a matter of fact, what you need to do, you have to calculate everything qualitatively. You cannot calculate quantitatively just like.
Thank you very much.
Thank you. So any other questions? You can have one question. Any questions? Just unmute and ask. Okay, so if there is no other questions, let's thank the speaker again. Thank you, Sashwata, for giving a really informative talk. Thank you.
Thank you, sir, Saurabh. Thank you very much.
Okay, so now we are at the last. This is the last talk of this session. So the speaker is Dr. Navnithan Vichandan from IISc Bangalore. He is currently assistant professor in the Department of mechanical energy. And the title of his talk is Tuning the Phonon Thermal Conductivity of Semiconductors Using Scattering Selection Rules. So with that, I request Dr. Dr. Navneet, please deliver your talk.
Thanks for the introduction, and thanks for the organizers for inviting me to give a talk. So this is my second time in this Young Investigators Meet. I gave a talk last year also, so it's very good to be back talking about what I have been doing for the past few years. So today I will be talking about how we are using selection rules for phonon scattering processes to tune the thermal conductivity, the phonon thermal conductivity of semiconductors. So some part of this work was supported, basically it's a work that has been extending from my postdoctoral work. So that part of the work was supported by a couple of graduate fellowships when I was at Caltech, and also the postdoctoral support from Office of Naval Research and Department of Energy Frontier Research Center in the US. The current work for the past couple of years is being supported by the SERB Core Research Grant and also a seed grant from IAC's Quantum Technologies Initiative. Okay, so what do we do in our lab? So my lab's name is Nanoscale Energy Transport Lab, NetLab to be short. So we develop new computational and experimental tools to probe the microscopic interactions among energy carriers like phonons and electrons in solids. And using these, after we probe them, we use the information to predict the macroscopic transport properties such as electrical conductivity, electronic mobility, thermal conductivity, and so on. We also developed experimental tools to probe these interactions at the microscopic level directly in the material. So using these tools, I have worked on developing computational ab initio first principles framework to discover new materials that perform exceptionally well under extreme environments. So for example, I'm showing pictures of two new materials, boron arsenide and isotopically enriched boron nitride, whose these are ultra high thermal conductivity materials, and we were able to quantitatively predict their thermal conductivities using this first principles framework without any adjustable parameters. You can read more about these two materials and also some of their interesting thermal transport properties in these papers. We also work, as I said, on probing the microscopic interactions among energy carriers in real materials using experiments. So with that, we have worked on, for example, looking at how phonons scatter at atomically rough surfaces of nanoscale thin silicon films. That is one application. So you can read more about the experimental part of my work in these three papers. So today I will focus on the first principles prediction of material properties and really tuning the thermal conductivity of materials using these selection rules. So using this first principles framework, to give you an overview, I have worked on these problems. Sorry, there is some problem with the animation. So some of the problems that I have worked on are related to the accurately predicting the ultra high thermal conductivity of boron arsenide, and also really discovering its very unusual pressure dependence for the thermal conductivity of boron arsenide and also boron phosphide. These are two new ultra high thermal conductivity materials. I've also looked at the effect of higher order scattering among 4 phonons. So the conventional picture of 3 phonon scattering is not sufficient for a large number of materials to predict their thermal conductivities. We find that even among common 3-5 semiconductors, it is important to consider accurately the effect of 4 phonon scattering to predict their thermal conductivities. So sorry you cannot see the last 2 figures. They are essentially talking about the giant isotope effect on the thermal conductivity of boron nitride, and also a very strong anharmonicity driven phonon renormalization, a many body renormalization of the phonon properties that drive a very unusual thermodynamic properties in the strongly anharmonic material sodium chloride. So this is a broad overview of the applications of my first principles framework. I will focus on the results on the left side, which is not hidden. So I will talk about some of the results on this part of the work. So just to give you a quick overview, I am sure everyone in this audience is aware of what phonons are. So these are really just the eigenmodes of a perfectly harmonic crystal, normal modes of a harmonic crystal. They are the collective quantized lattice vibrations of the crystal lattice, and they go around by using these plane wave mathematical expressions. So the phonons have specific properties. So I'm sure all of you are familiar with the dispersion relations, which connect the frequencies to the wave vector of these normal modes, eigenmodes. You can define the speed at which phonons carry energy, in this case heat, through the crystal, which is given by the group velocity, which is just the slope of these curves. In an ideal harmonic crystal, there is no scattering among phonons because these are the eigenmodes. But in a real material where there is anharmonicity, these eigenmodes of the harmonic crystal will start interacting with each other, resulting in the damping of the eigenmodes, and that causes, that's the consequence of intrinsic phonon scattering. You can sum up the effects of all of these scattering events that a phonon undergoes in a crystal with a single number called the scattering rate, given by this gamma, and it depends on, and it changes from one phonon mode to the other. So the index Q and J, where Q is the wave vector and J is the polarization. So in the figure on your left is there are 6 lines, so there are 6 polarizations. This represents a phonon, and you can have different scattering rates for different phonons. So once we have these a good understanding of these phonon properties in a material, you can invoke the expression from kinetic theory for thermal conductivity, which is shown here, and then you can essentially calculate the thermal conductivity of any material. So the expression here is written as a sum over all phonon modes, sum over the wave vector and sum over the polarization of C, which is the heat capacity that depends on the dispersion and temperature. You have the group velocity here, V squared, and then the scattering rate at the denominator. So the idea is, if you know these microscopic phonon specific quantities, you can get the thermal conductivity of any material. The challenge is, how do we get these phonon specific quantities? So the recent advances in the previous talks in this young investigator meets have shown the power of the predictive first principles framework to really predict the phonon properties of any material. So to just give you an overview, in this method, we start with the information about the crystal structure, that is the atoms that go into the crystal and the geometry of the crystal, and also a representation of the electrons in the crystal. That's it. With just this information, you can crank it through the density functional theory machinery along with the Boltzmann transport equation to study transport properties and effectively get properties such as phonon dispersion. You can actually get the free energy, which gives you the equilibrium lattice constant. You can get the phonon scattering rates, which gives you a measure of the anharmonicity or damping of different phonon eigenmodes. And with these three things, you can put them together into this kinetic theory expression and calculate the thermal conductivity of any material. The key point is there is no adjustable parameters in this recipe. So all that you need to know is the geometry of the crystal structure and the electronic distribution. And from that, you can go all the way to predicting quantitatively the thermal conductivity of any material. So the plot that you see in this red box is one of the first works by my postdoctoral advisor, Professor David Broido, where he used this framework to calculate the thermal conductivity of silicon and germanium and found excellent quantitative agreement with measurements over this broad temperature range. So my work basically is extending that framework to include higher order phonon scattering. So for example, if I go back to that slide, so this plot here of silicon and germanium included only 3 phonon scattering rates, which was actually the conventional framework to calculate thermal conductivity of materials for a long time. And over the past few years, I have developed computational techniques to include higher order phonon scattering, that is 4 phonon scattering processes. And we found using this improved framework that materials such as boron arsenide have a very strong effect of 4 phonon scattering on their thermal conductivity. So this is a collaborative experimental and computational work plot from this work, where we show that the solid black line, which is kappa calculated with both 3 and 4 phonon scattering process, matches well with the experimental data. But the dashed line that you see, which is using the conventional 3 phonon picture for thermal conductivity, is predicting that the thermal conductivity should be significantly high, which is not seen in the experiment. And this work was actually confirmed by 2 other independent research groups as well around the same time. And they all showed that the importance of 4 phonon scattering in boron arsenide. So this particular work where I included this higher order 4 phonon scattering processes into the calculation, into the first principles calculation, led to the discovery of this new ultra high thermal conductivity material. So this material's thermal conductivity is more than 1000 watt per meter Kelvin at room temperature. To give you some context, silicon's thermal conductivity is only around 140 watt per meter Kelvin. So the reason for boron arsenide having such high thermal conductivity and also strong 4 phonon scattering is related to the way in which different phonon scattering mechanisms are forbidden in the case of this particular material. So to give you a more detailed perspective, so let's look at the phonon dispersions for boron arsenide. So in the case of boron arsenide, boron is a light atom and arsenic is a very heavy atom. So because of this large mass ratio, there's a large gap in the frequency between the acoustic and optic phonons. So if you look at any typical 3 phonon scattering process, a conventional 3 phonon scattering process, that's what I have shown here, that this is a process which involves 2 acoustic phonons scattering into an optic phonon. And if you have done these calculations before, you will realize immediately that this is one of the most dominant or strong scattering mechanism in most common semiconductors that causes resistance to heat flow. So any scattering process should necessarily satisfy satisfy 2 constraints. One is the momentum or the quasi-momentum conservation. Here I am showing these 3 phonons are chosen in such a way that this equation is automatically satisfied. So the x-axis Q1 plus Q2 is equal to Q3. The other constraint is the energy conservation. That is, the frequencies have to add up. So nu1 plus nu2 should be equal to nu3. But because of this large mass ratio between the acoustic and optic phonons, this process can never occur in the case of boron arsenide. So this is one particular channel, that is an entire channel involving scattering between acoustic and optic phonons is completely forbidden in the case of boron arsenide. This we will call as a selection rule because it particularly selects and eliminates a whole channel of scattering processes which are actually quite strong in most other materials. So there are also other such selection rules. For example, in this dispersion plot, you can see that the second and the third branch of phonons from the bottom are very close to each other towards the right hand end of the axis. And this is called something called acoustic bunching. And this also reduces the number of allowed scattering channels in a phonon system. So these selection rules systematically eliminate or forbid several scattering channels in boron arsenide. So you have fewer scattering events, and therefore the thermal conductivity of the material is quite high. But it also means that in the case of 3 phonon scattering, these channels are forbidden. But obviously, the natural question is you can have one more phonon in the mix and basically allow scattering across the acoustic optic channel. And but the key point to keep in mind is this higher order scattering is a higher order in perturbation theory, so their magnitude is weak. So you have many more allowed channels which are all weaker in magnitude. But because the lower order scattering is completely zero for certain channels, this higher order scattering becomes important specifically in boron arsenide. So to give you a more quantitative perspective, so I'm just showing you how the scattering rates among 3 and 4 phonon processes compare. This is the 3 phonon scattering rates of boron arsenide calculated using this first principles framework at room temperature. The sharp dip in the scattering rates of these phonons are caused both by the bunching that I talked about and also the fact that these phonons cannot scatter with an optic phonon. And because these have very low scattering rates, these have very small, these particular terms have very small denominator. So they have the largest contribution to the thermal conductivity of boron arsenide in the 3 phonon limit. But it turns out that if you overlay the 4 phonon scattering rates also calculated in this framework, you will see that 4 phonon scattering rates are the strongest precisely in the frequency range, where the 3 phonon scattering rates are the weakest. So if you combine the two using this common Mathiasen rule kind of picture, you see that in the case of 3 phonon only, the scattering rates are very low. But if you combine 3 plus 4 phonon scattering processes, the total scattering rates go up by a factor of 4 or 5. So the denominator goes up. So the contribution to the thermal conductivity, that is the contribution in this expression to thermal conductivity, is going down. That's why in this case of boron arsenide, while the 3 phonon prediction gives you a value exceeding 2000 watt per meter Kelvin at room temperature, when you include this 4 phonon higher order processes in boron arsenide alone, the thermal conductivity drops by several factors. At room temperature, it drops down by a factor of 2. At higher temperature, it drops down by a factor of 5. So clearly in this special material boron arsenide, 4 phonon scattering, higher order scattering is playing an important role. So the natural question is boron arsenide very unique because of this particular feature of the phonon dispersion that you see in boron arsenide, or is this importance of 4 phonon effect ubiquitous in other materials as well? To get this argument started, we did this calculation for diamond, which is also a very high thermal conductivity material. But it turns out in diamond, 4 phonon scattering is not playing an important role on thermal conductivity. So in this plot, the dashed line are the conventional 3 phonon calculations, and the solid lines are the 3 plus 4 phonon calculations. You can hardly make out the difference between the two curves. And most importantly, all the curves are matching very well with the experimental data, which means our calculations are right. So in diamond, at least the 4 phonon effect is not important. So can we make some intelligent guesses for which materials will have the strong 4 phonon effect on its thermal conductivity without actually doing such expensive calculations? So remember that the 4 phonon scattering calculation involves identifying the combinations of phonons taken 4 at a time. So it's combinatorically significantly more expensive to compute than the conventional 3 phonon picture. So can we make some guesses without doing such expensive calculations was the goal of the last 2 years of my work. So we did find out that there are some general guidelines that you can draw only by looking at the phonon dispersions, which are like very easy to compute. There are some general guidelines that you can draw to predict whether a material is likely to show strong 4 phonon effect on its thermal conductivity or not. So these we call as selection rules. We saw a couple of them already. There is a gap between the acoustic and optic phonons when you have a large mass ratio of atoms in the material. And there are also certain features in the dispersion whenever there is a degeneracy or branch touching between two different polarizations. The scattering rates in the 3 phonon case for those phonons are becoming negligibly small. That is, so these rules are basically driven by the energy and momentum conservation that come in the 3 phonon picture. So this is the expression for the scattering rates. Essentially, I have opened up the Fermi's golden rule for 3 phonon scattering. This V element is the strength of the scattering, and N terms are the Bose factors. You have momentum conservation, which is given by this delta function, and the energy conservation given by this Dirac delta function. So these two terms put together Sorry. Okay, so these two terms put together can give us important insights into which particular phonons can have very low vanishing scattering rates just by looking at the phonon dispersion. So, for example, if the modes are touching each other in this spectrum, and the green and the yellow lines, that causes a very sharp reduction in the scattering rates in this frequency range. That prediction can be made by just looking at these phonon dispersion relations. And these dispersion-driven selection rules cause weak 3-phonon scattering. And once the lower order scattering is weak, then the effect of 4-phonon scattering can start showing up in the thermal conductivity. So using this framework, we were able to pick out materials among commonly used semiconductors where this effect is likely to show up. And we found out that our selection rule-based framework is exactly able to predict which materials will have strong 4-phonon effect and which will not. So in these materials that I have chosen, the mass ratio of the atoms are very large, and also the dispersions have those specific highlighted features. And the 3-phonon values of thermal conductivity shown by the dashed lines are significantly far away from the solid lines, which include both 3 and 4-phonon calculations. So in these materials, the 4-phonon scattering plays an important role in thermal conductivity. And more importantly, the experiments are lying top of the solid curves, which means our predictions are also quantitatively seconded by experimental measurements in the literature. There are also the other extreme cases where the effect of 4-phonon scattering is negligible. For example, in these materials, boron phosphide, gallium arsenide, and silicon carbide, the mass ratio is not that high. And also the other features in the dispersion that we saw are not applicable. And because of that, the effect of 4-phonon scattering is basically not there. So the solid and the dashed lines are overlapping within the experimental error bar. And also we have excellent quantitative agreement with the experiments. So just to put everything together, we plotted this as a histogram to see.
Sorry, there are 2 minutes.
Yeah, sure. So we put together all of the calculations with 3 and 3-phonon scattering, and we found a section of the 3-5 group materials where the 4-phonon scattering is very strong. I mean, the effect of 4-phonon scattering is very strong. And also we were able to predict it from the dispersion relations. And also the other end of the spectrum where we found that interestingly, the compounds containing boron, nitrogen, and carbon have the weakest 4-phonon effect on the thermal conductivity, precisely because they have very strong bonds and their anharmonicity is very weak. So finally, we also were able to use this framework to predict unusual pressure dependencies of the thermal conductivity in boron phosphide and boron arsenide. So conventionally, when you compress a material, the thermal conductivity has to increase with pressure. This is because the phonons become stiffer with pressure. So the group velocities will go up. So the thermal conductivity goes up. But in materials that I have listed, boron phosphide and boron arsenide, the thermal conductivity takes a non-monotonic trend. And you can read more about these results in this paper. So this is really driven once again by the selection rules, more specifically the competition between different phonon scattering channels in these materials. So for the case of boron phosphide, as you see in the dispersion relation, with pressure, the optic phonons become stiffer and stiffer, and so do the acoustic phonons. But because of the gap that widens between the acoustic and the optic phonons, the scattering between two acoustic and optic channels, just like in boron arsenide, becomes weaker and weaker, and that causes the thermal conductivity to go up. But it also releases the bunching that I'm showing in the red circle, which means the scattering among the acoustic phonons, that is the AAA scattering, which is given by the red points, are also becoming stronger. So one channel of scattering is becoming weaker and the other channel is becoming stronger. And this competition with pressure is causing a non-monotonic pressure dependence. In the case of boron arsenide, something even more crazy happens. The 3-phonon scattering rates become stiffer with pressure, but the 4-phonon scattering rates become weaker with pressure. So once again, you have two channels which have opposite trends with pressure, and these opposing trends drive increasing and then decreasing thermal conductivity trend with pressure. So in summary, I hope I have shown that we have identified selection rules based only on the phonon dispersion relations, which are fairly easy to compute, to predict whether a material is likely to have important higher order phonon scattering effects that affect the thermal conductivity or not. And we have also used these selection rules to discover rare thermal conductivity behaviors of materials under extreme conditions like very high pressures and also very high temperatures. So thanks for your attention. I would be happy to take any questions.
Yeah, thank you for the nice talk. So the session is open for the questions. Please unmute yourself and ask questions. Also, you can put in the chat box.
Hi, Saurabh. This is Aftab.
Yeah, please. Yeah.
Hi, Navneet. Very nice talk. So, if I understand correctly, all these thermal conductivities are only phonon contribution. Is that right?
Yeah. So I have considered reasonably large band gap semiconductors, and also I have not considered any doping.
So, what is the order of magnitude of electronic thermal conductivity?
In these materials, I think they are negligible.
They're very small, right?
Yeah.
So for narrow band gap semiconductor, are there any examples where we observe such high phonon conductivity?
So,
because all your examples are gallium arsenide, indium phosphide, they are reasonably large band gap compound, right?
Yeah. So there is one recent paper, I don't remember I think it's tantalum arsenide. It recently came in PRL. They predicted, it's a semi-metal. So they predicted very high thermal conductivity. That's because of some interplay between electron phonon scattering and phonon phonon scattering in that material. So they predicted a very high lattice thermal conductivity, if I'm correct.
Yeah, so that's where I'm coming. I mean, are there any specific electron phonon coupling or the electronic degrees of freedom which is mediating this kind of a high thermal conductivity in those kinds of compounds?
Okay. So we did actually, like when we were searching for other candidates for high thermal conductivity, we did look at metals. It always turns out that whenever you have weak phonon-phonon scattering in metals, it's probably because of some Fermi surface nesting or some weird feature, but that also causes a very strong electron-phonon coupling. I don't know if it is
and in
like
your system,
sorry.
No, go ahead.
Yeah, I don't know if it is a coincidence or if it's like if there is some physics behind that. So, for example, niobium carbide is one candidate which we thought was a promising candidate because niobium is very heavy and carbon is very light. So you would expect a large band gap. But it turns out, I mean, the material actually has Fermi surface nesting, so it has very strong electron phonon coupling. So so that was one candidate. So we tried lots of other candidates, but it was very difficult to find something that matches diamond or even boron arsenide or boron nitride.
So you did not came across any example where the system is a narrow band gap semiconductor, but it still have a high phonon transport.
This tantalum arsenide, I think, is one such candidate. It's a semi-metal. We missed it because I mean, we just missed it. Yeah.
Sure. Yeah.
Yeah.
Okay. Thanks.
Sure. Thanks.
Yeah. Any other questions from the students? Or you can also put in the chat box. So, any other questions from the audience? Yeah, any other questions from the audience?
Maybe Saurabh, just one more.
Yeah, sure.
So, usually we look for low thermal conductivity materials for applications like thermoelectrics and all.
Yeah.
What are the applications one can target
here with high
your kind of system?
Yeah. So you see, I mean, yeah, maybe so this boron arsenide, for example, right? It has a thermal conductivity of 1000 watt per meter Kelvin. There are also some works from my collaborators group where they have also studied the electronic properties of boron arsenide. It's actually very, very close to silicon. So you actually now have a material which is as good an electric conductor as silicon, doped silicon, but it's 6 times a better heat conductor. So you can imagine, you can envision passively cooled electronics with this kind of system, even at room temperature. So you don't need a substrate. In fact, there is a paper on this particular application which came out like a month back. They tried to make a device out of boron arsenide, and they showed that it's actually pretty good at keeping the device cool by itself.
I see. I see. Thank you.
Yeah, sure. Thanks.
Oh, so any other questions? Okay. So if not, let's thank the speaker again. Thank you for a nice talk.
Thank you.
So now it's over to the organizers. Is any of them is available?
Yeah, hi. Thank you, Saurabh, for chairing the session, and all the speakers for very interesting talks and interesting questions that has happened all through. And especially, it's a good sign that at the end of the day, there is still a lot of enthusiasm for questions. That's always a good sign of the quality of talk and the participation. Okay, so thank you everybody for today. So we'll resume tomorrow.